Okay. Yeah. I think you don't need to just yet, but I'll keep your slides up.
So we will start on time.
I think in a couple of minutes. I think we'll just have a
I can wear this first.
Oh yeah, if you want to try that, yeah. I think Alice or Randall might have a quick announcement before your talk, but just like a minute or so.
Wear this anyway.
Sure. Yeah.
I can stand here.
I think so. I wanted to test. Okay, I was just testing that it works.
It's a little quiet, I think. I can speak louder. Yeah.
Yeah, and it does really help in the back, even if you don't hear it here.
Ah. Okay.
I'm sharing the second.
Yeah. My name is Jia Rui. Jia Rui. The foundation is same as Tom and Jerry. That's Jerry. You could. Yeah.
Just need to share your slides on Zoom.
More version of yeah. So I was thinking.
Share of anticipation. Thank you.
Thank you.
Okay, good morning, everyone. My name is Ryan Pimpin. I'm a postdoctoral researcher here at McGill, and this morning's session is on a topic that is near and dear to my heart, polarization. And to kick us off is Chauri Nui, who will be giving the overview talk on polarization.
Yeah, thank you very much. Good morning, everyone. I'm Jerry Niu from NAOC, and I'm postdoc in Weiwei's group. Today, my topic is about probing the origins of FRB through polarization observations. This slide shows the earliest FRB polarization observation. The sentence I like most in this paper is that new instrumentation can decrease the time between observation and discovery from years to seconds. And the PACS discovered this source in 2040, and they trigger follow-up observation. They first got the polarization observation result as shown in the figure, and they gave the limit of redshift less than 0.5. They didn't find any counterpart of the multi-wavelength observation. So 10 years later, what new insight do we have about FRB and what polarization observation can tell us? The most important problem is the possible origins of FRB. The milestone observation is that we found magnetite is one of the possible origins. This evidence is given by SGR 1935 and FRB 2004-28. The SGR-1935 is known for emitting short bursts of gamma ray and X-ray, and FRB2025 is the first FRB detected within the Milky Way and definitely linked to the SGR-1935. This left figure shows the timelines of the high energy and radio observation. And the middle two figures shows the radio burst detected by CHIME and FAST. After the FRB, several months later, the SGR-1935 enter a pulsar phase, as shown in the right figure. It shows the timing result of the in the pulsar phase. So the coincident radio and X-ray bursts strongly support that magneta are a source of FRB. And for active repeaters, regular repeaters and non-repeaters, they may not have one single origins. In Bin Zhang's review paper, he lists the possible origins of FRB. The light blue box shows the observational fact, and we can find the magneta channel is currently the only known pathway that can produce FRB. So how polarization can help us understand FRBs? The way the radio wave polarize can tell us where they come from, what surrounds them, and how they travel to us. So my talk will divide it into three topics, that is the radiation mechanism, the environment property, and the propagation effect. First is the radiation mechanism. There are two types of model, that is the pulsar-like model and the GRB-like model. For the pulsar-like model, the radiation is originated within the magnetosphere, and for the GRB-like model, it is related to the relativistic shock outside the magnetosphere. One thing these two models debate is that whether FRB can propagate from the magnetosphere. In Brodow's paper, he finds the cross-section of the electron scatter wave is very large when K perpendicular to B. But that is extreme saturation. Actually, FRB wave can propagate freely in the open field line. Details can be found in Yuan Hong's paper. In the left, I list some basic definition of polarization. And in CHIME's recent statistic result, they find there is no significant difference of repeater and non-repeater in terms of the linear polarization degree and RM. And in the early observation, the detected bursts always have high linear polarization and flat PA. But with the accumulation of data, we find some bursts with high circular polarization degree. As shown in this slide, these two figures both from one source, that is FRB 2020-11-24A. And the left figure result is from the PAX observation, and the right is from FAST observation. As shown in the right figure in Jing Chen's paper, he found very high circular polarization degree can reach unexpected 19%. So one key question is whether the circular polarization is intrinsic to the source or induced during the propagation. Actually, in FRB, circular polarization is relatively rare. As shown in this left figure, it shows the correlation of the linear polarization and the circular polarization degree. This green sector contains the burst of 68% of all the bursts. You can find most of the bursts have high linear polarization. The same is as in the entire astronomical phenomena. In the right figure, the x-axis shows the brightness temperature and the y-axis shows the circular polarization degree. The FRB are in the right region, both with the high brightness temperature and high circular polarization degree. And only solar bursts and Jupiter can reach such high circular polarization degree in the astronomical phenomena. And here I list some observation facts related to circular polarization. As shown in Jing Chen's paper, we found rapid polarization change as shown in this figure, both in PA and circular polarization degree in the time scale of 30 milliseconds. So the out of magnetosphere propagation effect can will both affect the linear and circular polarization. So for the extra plasma, it is difficult to cause such rapid change in polarization. And in the middle figure, we find no strong correlation between flux and circular polarization. For the off-beam viewing geometry, it can produce circular polarization, but this burst will have lower flux than other bursts. We didn't see that in observation. And in this right figure, we found circular polarization of some bursts is independent of the frequency. So this can't be explained by the Faraday conversion because Faraday conversion is frequency dependent. So the intrinsic radiation mechanism and the propagation effect both fail for the GRB-like model. As shown in Yuan Hong's paper, he discussed the radiation mechanism and the propagation effect both inside and outside the magnetosphere, including the curvature radiation, inverse Compton scatter, cyclotron absorption, and the Faraday conversion. The conclusion is that high circular polarization favors magnetospheric emission model. And the next observation related to radiation mechanism is PA swing and RVM. This is a well-known rotation vector model, and this formula can be derived from the spherical geometry. And the alpha is the inclination angle, beta is the impact parameters. In Lore's paper in 2020, they found some bursts have such PA swing, and in recent time result, they found FRB in a nearby host galaxy, and it shows 130-degree PA rotation in about 2.5 milliseconds. This PA swing and the S-shaped PA both support the magnetospheric origins. Consider the possible origins of neutron star. They can also rule out the very short period pulsar in this this source. And in repeating bursts, in Xiaohui Liu's recent paper, he found the PA variation are very fully consistent with RVM of total of 46 bursts in total 1,700 bursts from three active repeating FRB. This figure shows the RVM fit result and the observed PA. However, we found that these inferred parameters is inconsistent with each other, as shown in this left figure. The different colors shows different repeaters, and the violin plot represents the distribution of the parameter of period alpha and beta. So the most of the bursts have constant PA. It perhaps indicates that the central agent is an Allied rotator, or it has a very long spin period. But some of the bursts show significant PA variation and can be well fitted by RVM. And this tells us the magnetic configuration is dynamically evolving. This is my work about the sudden polarization angle jump. We found three bursts with PA jump in the time scale of millisecond in thousands of the bursts in FRB 2020-11-24A. The energy of these three bursts is higher than most any other burst. It perhaps indicates the same mechanism of pulsar and FRB, despite they have huge energy difference. And for the burst one, these bursts have a more complex methodology. As shown in this figure, we plot IQUV as a function of time and frequency. You can find it. This burst is consistent of the different components. If we cut frequency, as shown in this left panel, we will have flat PA with the PA jump shown in the lower frequency. But the total profile has a PA swing. This PA swing is composed of the superposition of different components. And another interesting thing is that we found in the lower frequency, this left peak and the right peak, it has a totally different RM. as shown in the right figure. If we derotate using the average RM shown in this black line, we will get the jump of the 66-degree jump shown in this black dot. And if we derotate using their own RM shown as this in this red line, we will get a 19-degree polarization angle jump shown in the red dot. So RM can change very large in such short time scale in millisecond. And in Yuan Hong's paper, he discussed PA jump in detail, and the intrinsic mechanism is favored. The bifiltrance and plasma lensing is disfavored. So the PA jump in these three bursts can be explained by the incoherent superposition of the two orthogonal modes. The millisecond timescale observed in the PA jump impose a strong constraint on the emission region in a magnetized magnetosphere. So for radiation mechanism, our conclusion is that at least for some FRB, the mechanism is pulsar-like, and the radiation is inside the magnetosphere, and the magnetic configuration is dynamically evolving. And my next topic is the environment properties. Here is the background of the Faraday rotation and the Faraday conversion. If we assume that the income wave is 100% linear polarized, in the case of the B field is parallel to the line of sight, the plasma mode will divide it into two circular modes. One is left and another is right. And these two modes have different group velocity and phase. So for the outcoming wave, it will be linear polarized. That is, and the PA slightly rotates. That is a Faraday rotation. If we plot the Stokes parameters on the Poincare sphere, the trajectory will be a circle around the v-axis. And in the situation of B field is perpendicular to the line of sight, the plasma mode will divide it into two linear mode, and one can image that the two orthogonal linear mode will generate the circular mode. That is a Faraday conversion. If we plot the Stokes parameter on the Poincare sphere, it will also a circle, but not around the v-axis. So RM quantifies how much plane of the linear polarization rotates, and the extreme RM indicates the presence of a highly magnetized dense plasma along the line of sight. As shown in this left figure, the highest RM observed in FRB is FRB2025. It can reach the 10 to the power of 5. Is larger than the magnetite and the galactic center pulsar. FAST observed this source for a long time, as shown in this red figure. We found that both RM and DM have decreased with time. This trend can be explained by the early phase supernova explosion, and the more observation perhaps strengthen the orange of the young magnetars. Except for FRB2011-02, multiple FRBs shows temporal variation in days. Combined with the data from the other paper, Cherry and G summarized the RM variation of the repeaters. The special one is the FRB 800916. It has a 16-day activity cycle as the RM variation shown in this figure. The RM evolution of this source lack periodicity correlation with the activity cycle. And in fast new result, in Li Ye's recent paper, we found RM flare. This RM change very large in time scale of days. And this RM flare suggests a dense magnetized clump moving across the line of sight. And this possibly caused by the coronal mass ejection, and it can be explained by the companion star that provide this stellar flare. Except the RM flare, in the earlier observation, they found RM period in 200 days, as shown in Yifang Liang's paper. This period is consistent with the RM flare predict. And also in Zhang Weishu's paper recently, he found RM period of 26 days in FRB 2020-11-24A. And he got this period using Lomscago and wavelet. You can find this period is mainly dominated by the first and third episode of this source, showing the black and the green region. Perhaps we need more active data to confirm this period, but this source turned off for a long time. In addition to the long time scale RM variation, RM also shows variation in milliseconds, both in repeating and non-repeating bursts. In fast results, we found in this consecutive burst with interval of 50 milliseconds, the RM change can reach 50. And as shown in Sherman's paper, they found the RM of non-repeating bursts of the subcomponent can variation with time, showing these scatters. RM also shows side change. In Cherry Ng's paper, she found two sources show side change of RM among the 26 repeating FRBs. And together with the previous published one, the FRB202520B, its RM twice changed its size. So RM side change indicated reversal in the direction of the magnetic field lines, perhaps can be explained by the binary model. So for the environment property, periodic and side change behavior in RM would support the binary model. The next is the propagation effect. In Xu Hong's paper, we found the evidence of the Faraday conversion. It shows oscillation in the linear polarization degree, circular polarization degree, and PA. And if we consider the linear to circular polarization conversion, one can extend the Faraday rotation to the generalized Faraday rotation, that is the GFR, using the parameter of spectral scaling index alpha. And Pawan using this method to test the observation of 180301A. And he got a good fit of the Stokes V and Q, but the V and U, but the Q have a relatively large residues. This also using the magnetized work. So for the homogeneous magnetized plasma medium, Wei Yang gets an analytical solution of the transformation equation. Compared with the GFR model, they offer some more physical description of FRB magnetic environment. Details can be found in his talk and Tiancong's talk. And another propagation effect is frequency-dependent depolarization. In Feng Yi's work, he observed 5 active repeaters in a very large frequency range, and he found the frequency-dependent depolarization as shown in this figure. This can be well modeled by the parameter sigma Rm. The depolarization Rm scatter can be read as that. This red figure shows the degree of linear polarization and Rm. For the repeater and non-repeater, they seem different, perhaps indicates they are in the different environment, but it still need more data to test. In DSA's results, they found 25 new FRB. 3 of them have total polarization consistent with 0. So according to their frequency and polarization degree, they find no significant RM in these 3 FRB. Disfavor multipace RM scattering in this source. The next propagation effect is the plasma bifurcance. In SCAP result, they find 2 bright polarized bursts with intra-burst RM variation showing the purple scatter. And they also found time-dependent linear to circular polarization conversion. This can be well modeled by the great circle on the Poincare sphere, and it's evidence of the plasma bifurcance. This is my summary slide for the propagation effect. We can get a physical description of FRB magnetic environment. And in my talk, the cited paper in blue are both from the FAST FRB K-Cent project. And we are open for collaboration. Thank you.
Okay, we have a few minutes at least for questions. Any questions from anyone? Adam?
Hi, thank you. I don't, I'm not an expert in polarizations. This might be a very naive question, but you detected PA swing in a repeater. If it's to do with the rotation of the object, like a pulsar, wouldn't you detect the swing every burst? No, not just in like 3 out of 1,000 sort of thing.
You said in FRB, right?
Yeah.
We only detect 3 bursts in total of thousands of bursts have PA jump.
From a repeater.
Yeah, from repeater. This is a very active repeater.
Yeah. So I guess my question is, if it was a pulsar, wouldn't you expect the PA swing to happen every single burst? Or no.
In pulsar, actually, I have this slide, but I have no time to show you. In pulsar, if the total profile has PA jump, some of the single pulse have the PA jump in this PA. Yeah, only some of the bursts, not all of the single pulse. Yeah.
Thank you. Ryan, I wanted to.
Please speak louder.
Hi, I'm Kavya Shaji from University of Sydney. Thank you for the nice talk. So there are sources which exhibits like high DM, but they are like shown to have very low RM, like nearly 0. What could be the mechanisms or responsible for this?
Actually, it depends, I think. In another very highly active burst, it has a RM near 0, but we also shows many polarization results in this source. Actually, I think perhaps it is in a clean environment, so we can answer your question after find new FRBs, more observations.
Thank you.
Thank you.
Okay, are there any questions online? Okay. Oh, here, Mouse.
Yeah, thank you for the talk. I had a question, I guess, in terms of how do we distinguish the most unique cases, like ones with you have a couple of FRBs that have PA swings or significant RM variation. How do we and they could suggest a magnetospheric origin or different things about the progenitor. How do we distinguish those from whatever the most common cases for FRBs are?
Most of the bursts, the RM variation shows no regular, but some of them shows periodicity. I think the periodicity is the evidence for the binary model but we can confirm that, I think, because the periodicity is not very convincing to answer that. I'm not sure. Compared with the observation of pulsar, in binary pulsar, the RM often not show the periodicity. So perhaps we need more observations, I think. Yeah.
Thank you.
All right, let's thank the speaker again. Okay, our next speaker is Mason Ng, colleague of mine, who will be presenting on baseband catalog 2 polarization results.
Cool, thanks, Ryan. So I'm usually tech support, but I'm Mason. I'm actually a postdoc here at McGill. I'm an extra astronomer by training, but I'm here today to talk about the first look at the polarimetric properties of FRBs from the Chime FRB baseband catalog 2 or basecat 2. So to orient ourselves, the CRA has already given a nice introduction, but just to orient ourselves, a reminder that polarization is just the orientation of the electric field in the propagation of an electromagnetic wave. And as Jerry also motivated in the previous talk, we care about polarization because we get insights into the emission mechanisms and also the local magnetoionic environments in and around FRBs. And also a high linear polarization, for example, gives us strong, highly ordered magnetic fields. And in terms of how we do this, we can construct Stokes IQ/UV parameters from the XY linear feeds, and we can systematically study the polarimetric properties through large data sets that I'll describe in a short while. But I do want to lay out some relevant definitions for now, and so that we're all on the same page. So we have the linear polarization fraction, which basically tells us how aligned the electric field vectors are. So imagine all of you in the audience, you're all waving Canadian flags because you're in Canada. And the linear polarization fraction tells us whether you're all waving the flags in the same direction or in sync or chaotically. But I won't be talking about the polarization angle today, but it basically refers to the orientation of the electric field vector itself. And then there's the Faraday rotation, which is just telling us how much the electric field vector rotates as it passes through a magnetized medium. And it's basically related to the electron density and also the magnetic component, a magnetic field component along the line of sight. And this can be negative because the magnetic field has a direction. And in likewise to what you hear from like the DM budget, there's also an RM budget with various distributions. There is the can't read my own slides, ionospheric and the IGM contributions, which is roughly 0. And then there's also the Milky Way contribution, which we can use a galactic rotation, Faraday rotation sky map to do so. Although there are some uncertainties there, and in terms of how those uncertainties can affect FRB measurements, take a look at Aisha's latest paper on the archive. But basically what you have left over is the host RM that's scaled by 1 plus Z all squared, or what I'll call the extragalactic RM from now on. So before talking about basecat 2, I want to quickly summarize results from the first baseband catalog or basecat 1 with polarization measurements from 128 non-repeating FRBs over 400 to 800 megahertz in the Chime band. And out of that 128, about 89 have significant detections, significant meaning above 6 sigma. And among some of the key results are that there's no seen dichotomy in the distributions of observed linear polarization fraction or the extragalactic RM. And there's also between the non-repeating and repeating FRBs. So just to put some of the words I just said into diagrams, I'm showing the top here the distribution of the, let me move this up. The distribution of the linear polarization fraction between unpolarized and polarized FRBs in gray and in blue. And then on the right is the cumulative distribution function for the comparison between non-repeating FRBs in blue and repeating FRBs in orange. And then below is a similar type of diagram, but this is for the absolute value of the extragalactic RM, histogram on the left, and cumulative distribution function on the right. And simple p-values from simple Kolmogorov-Smirnov or Anderson-Darling test suggest that the two groups are drawn from the same population. So here's a visualization of the basecat 1 sample with the 89 polarized FRBs in white and 29 unpolarized and 10 that are limited by the instrumental polarization. And now so far, oh, did it load? Maybe not. Oops. I wanted to run animation. Okay, well, for basecat 2, we have quite the expanded sample. So the processing of the baseband data has been led by several folks that's up there, including myself. And the caveat is that we're still processing the events and verifying more of them. And we still need to inspect the polarization fits in depth to determine the events that are limited by the instrumental polarization, but it's coming along. And to put some numbers to what I just said, the detection threshold for polarized unpolarized is the same as in the basecat 1 sample, which is 6 sigma. And for any upper limits on the linear polarization, it's 6 over the intensity signal to noise. But the sample so far here, I've listed there are 997 polarized non-repeating FRBs and 182 unpolarized. And the preliminary visual comparison that with repeating sources will make is facilitated with the published catalog by Cherry Ng et al. No relation. And in all cases here, we've calculated the structure maximizing DM. And I should also note that a very simple sanity check we did was, we did a simple KS80 test, implying that the underlying distribution sample for base cat 1 and 2 were roughly the same. So onto the distributions itself for some of the relevant quantities. I'm showing both histograms on the left and right. On the left are the comparison for the linear polarization fraction, and on the right is for the extragalactic rotation measure. And the caveat is that for values of RM below about 10, there's we're still investigating and likely limited by instrumental polarization there. So I guess be careful. Although some preliminary statistical tests suggest that we don't see any significant differences between the non-repeating and repeating populations in either of the two quantities or metrics there. But if I now just focus on the non-repeating sample itself, and let's think about the expectations for the extragalactic RM as a function of the extragalactic DM. And if you assume that the DM and RM components, the contributions come from independent sources along the line of sight, you might perhaps get something like this, maybe, because of the 1/1 plus Z factor difference between the RM and DM. But in reality, you get something like this. And focusing on the non-repeating sources in blue, with the caveat again that the low RM environments events may have polarization leakage, they're not accounted for properly yet. And but if you do a simple Spearman rank correlation test between between the extragalactic RM and DM for the non-repeating sample, you get a p-value of something like 0.00 below 0.006. And the reason why I quote that value is because in that same exercise that was being done in the previous sample with the 128 non-repeating FRPs, in base cat 1, that was the value that we got. So I will, at the risk of abusing p-values too much, I will just say that we might see something, but we still need to do more to ascertain the relation. But going back to the physical picture, if the extragalactic DM, which has both the IGM and the host galaxy contributions, if that is a proxy for distance, take my word for it for now, then we would expect the extragalactic RM to be lower at higher DMs just because of the 1 plus Z squared denominator for the RM. And so maybe the high RM values we see here may indicate significant magneto-ionic environments. But just to explore and look at that extragalactic RM a bit more, here is this probability density function of the extragalactic RM without taking absolute values. And you can see from the base cat 1 sample that's in blue and the base cat 2 sample that's in orange, the distributions look roughly similar about 0, which is kind of what we expect. But our first thoughts, or at least my first thought, is that if you have a conglomeration of random distinct regions contributing to the RM budget along the line of sight, the central limit theorem would indicate or dictate a Gaussian distribution for the extragalactic RM here. But if we were trying to fit a Gaussian, so for in this case, pink for base cat 1 and purple for base cat 2, and some of you could already probably tell, you don't get a very good fit. In particular, the wings of the distribution aren't very well modeled. But if we try something like a Lorentzian, you get a slightly better fit, at least for the distribution around plus minus like 1,000 or so in the wings. But I mean, it's not perfect either. No model is perfect, I guess. But I want to perhaps try and link this back to what we see in simulations of these galaxies, where there have been some theoretical work to try and model the extragalactic RM distributions. So, and on the left from Basu et al. 2018, they simulated 10,000 disk galaxies with a range of inclination, azimuthal angles, and effect parameters. And on the right is COVAX plus 2024, where they used the TNG 50 simulations with 16,000 plus-ish galaxies and a range of rotations and FRB positions in each galaxy, because there they're focusing on FRB host galaxies. And then the host galaxy RM contributions are just calculated for each sightline. And in both cases, they found that the host galaxy RM distributions are well modeled by the combination of a Lorentzian and 2 Gaussians. A Lorentzian for the wings of the extragalactic RM distribution, but also a Gaussian that's related to something like the product of the field strength and the electron density, and a second Gaussian to describe the peak at around 0. If you want more details, I invite you to look at the paper. And then I should also stress that these are rest frame values. The distribution I've been showing has not been corrected for either individual shifts or we have not done yet a statistical correction. And then just to put maybe a more schematic picture to it, here's me drawing the RM quantity in white arrows and multiple different sidelines. And in those studies, there is a redshift dependence, but they generally see that the azimuthal components of the magnetic field is much stronger, a few times stronger compared to the vertical and the radial components of the field. So an observer, us, would see contributions to the RM from the azimuthal component. And if we do get these high RM-ish RM values, we may be seeing these edge-on orientations, maybe. And so, motivated by that, I made the same Lorentzian plus 2 Gaussian fit to the base cat 1 and base cat 2, which is shown in the dashed lines. And the slightly more complex model fits the observed distribution slightly better, but actually not that much more. But I guess the main takeaway is that the best fit model, at least requires some Lorentzian-like component to at least describe the wings of the observed extragalactic RM distribution a bit more reasonably. And this maybe tells us that some FRB sources tend to result in these galaxies, as I was trying to motivate before, similar to what Alexa Gordon showed us yesterday and plenty of other work as well. And then some very recent work archived last week by Wovatsky et al. From last week, from the craft survey of about 35 FRBs, found a potential correlation between the extragalactic RM and also the ratio of the semi-minor to semi-major axis for the host galaxies, and maybe pointing to edge-on orientations. Now, what I'm offering here is an interpretation of what's going on, not the interpretation, or I'm not going to claim anything like that, since we don't have enriched information. But the talks yesterday, including by Alexa, was showing us that they're likely delayed channel host 2. So comparisons with other simulations of elliptical galaxies or other types of environments would be instructive in this case. Okay, now looking ahead, there's much more to do with the base cat 2 sample that we have. For example, with the baseband localizations that we have and we'll do, we'll look for host associations to the path framework. Something I didn't quite touch on because of time constraints are the polarization and variations in the polarization angle profiles, various things that CRA was just talking about in the last talk. But it's an extension of what in the base cat 1 sample, what Ayush Pandey led for a couple months ago. We don't want to do simple correlations with burst properties and many more as well. And of course, with the full chime outriggers array, it's just amazing how we have these precise host localizations now. And hopefully that means we'll get more redshifts, as we were discussing yesterday at the end of the day, so that we can more precisely constrain the magnetoionic environments around or near FRBs. So to conclude, we're now working with a sample of polarized non-repeating FRBs in base cat 2 with an expansion of at least 10 times, but again, we're still working on the sample. And we do see FRBs that are generally highly linearly polarized. I think I didn't even mention that, whoops. Anyway, but I showed the distribution of the extragalactic RM, and it seems to require some sort of Lorentzian to describe the wings of the distribution. And I argued that in comparison with these theoretical simulations, they might point towards disk-type galaxies, at least in those environments. And again, results of preliminary analysis are still ongoing, but since we are at FRB 2025, if you have any ideas about things to play with, things to look out for, papers to compare to, or whatever ideas might be going on, I'm more than happy to chat with you either here this week or by email. With that, I'll take questions. Thank you.
Right, any questions for Mason? Nice, great. Let's start down here.
A reminder to please introduce yourself.
Hey, thanks for the really interesting talk. I'm Pawan from Sunvan University. So I was just curious about the thing that you probably did not touch upon on the depolarization aspect. Do you find any significantly depolarized bursts in the chime band in your base cat 2?
Yeah, I think Ayush is actually better positioned to answer that from base cat 1 because we've not started on that yet. Because we plan on doing very simple looks, because the chime band is relatively narrow, between 400 to 800 megahertz. We'll just do a simple fraction between 400 to 600, 600, 800, but we have not done that yet, so I can't comment.
Thanks.
Thanks for the question.
Hey, Mason. Thanks for the talk. This is Marcus Lower from Swinburne University.
I was wondering if you could say a little bit more about how the BaseCat RM distribution compares with the ASCAP craft sample.
Oh, yeah, I guess from Wovalski et al. Yeah, I guess let's slide from here. So yeah, I think when the paper came on the archive last week, I was very curious about what this looked like. But I guess with 35 FRBs, I mean, the distribution I've shown here in lime green, and the fit with the Lorentzian +2 Gaussian in light green as well, and the fit isn't so good. So I think there we can't say too much more other than we'll like definitely a bigger sample of polarized FRBs from all, including Chime, but also with Craft. But again, the interesting result with the host galaxies was like what I said before. That was very well noted.
Great, thank you.
Thanks. Sunil, can you unmute yourself, please?
Oh, yes. Thanks. Hi, this is Sunil from Northwestern Chicago. I was just trying to, well, this could be a question for clarification because I might have just misunderstood it. So in your RMEG versus DMEG plot, you don't see the negative correlation, which is just the indication, as you mentioned, that the RM is likely coming from the circumburst medium and not the interstellar medium of the host. But you also showed that the RM distribution of the bursts are Lorentzian, which could be explained by basically the ISM being a disk. So how do you reconcile these two? To me, it sounded like they were contradictory, but maybe I'm misunderstanding it.
Yeah, sorry, I only caught kind of a 75% of the question in the front here. If I understood the question, I think we would need host galaxy associations to really get a better sense of what might be going on in like distinguishing between the different contributions, possibly. If I didn't quite catch your question, feel free to just message.
Yeah, I'll just put it on Slack. Thank you.
Okay, thanks, Sunil.
Okay, let's thank the speaker again.
We also just want to get rid of the subtitles.
I'll leave you to it.
Yeah. So I'm gonna try and be off. It was Google Slides, right? Yeah. Amazing. And this is yeah, I read that. You can use this if you want, or just the errors. Awesome. I'm not gonna put this on just yet, so we quickly introduce ourselves. But hi everyone, my name is Jacob Faber. I'm a third-year graduate student at Caltech, working with the DSA 110 collaboration, the Deep Synoptic Array 110.
And I'm Ayush Pandey. I'm a final year PhD student in the Time FRB collaboration at the University of Toronto.
Right. Awesome. So today I'm going to be telling you about a sort of unique joint venture between these two collaborations that we're a part of, and the special, unique, very interesting things that we can do when we use them in tandem. So, or use the instruments that both collaborations use in tandem, namely the DSA 110, located in Southern California, and Chime FRB, located up in British Columbia, Canada. So I won't belabor you with the back of these baseball cards. You've heard enough about these observatories already, but broadly speaking, Chime FRB, amazing FRB detecting machine, wide field of view operating between 400 and 800 megahertz. The DSA 110 geared towards localizing FRBs to within arc-second precision and operating at L-band between 1.3 and 1.5 gigahertz. Now, the two observatories fortuitously share a substantial degree of overlapping sky coverage, which is not on purpose, but amazing for us because that allows us to do the science that we're talking about today, and possibly, and eventually, as you'll see now, simultaneously detect individual FRBs, actual individual bursts from the same source. This offers a unique opportunity to constrain
propagation effects across a wide frequency range, 400 megahertz to all the way up to 1.5 gigahertz, which we'll be talking about today, but also their emission physics. So the sample. The sample is comprised of 16 FRBs in total, 12 of which were sufficiently bright to be stored or dumped as raw voltage data at both observatories. It comprised one repeater, which only repeated twice at the DSA 110, observed once at CHIME, and the rest non-repeaters. Now, the search itself was quite simple, performed simply by cross-matching the two detection catalogs, searching for coincidences in dispersion measure, times of arrival, obviously, as well as sky position. Now, to classify these as co-detected FRBs was a little bit more challenging, but relied specifically on precisely measuring the time of arrival such that we could say whether or not it arrived within the expected light travel time between the two instruments, which depends both on sky position and the actual baseline. Now, what I mean by this is you can see on the map here, CHIME FRB up top, DSA 110 down below, fortuitously located at very similar longitudes. The CHIME telescope, being a transit telescope, stays fixed on the sky, whereas the DSA 110 is only steerable in elevation and typically operates in drift scan mode, parked at a certain deck, which over the course of the roughly 2 years that we looked at observations for, was positioned at a deck of roughly 71 degrees. Thus, we expect roughly the same time arrival offset to occur between the two observatories for all of these bursts, where it arrives at CHIME just a little bit earlier than it arrives at the DSA 110. Now, this TOA offset, roughly speaking, is plus or minus 0.1 milliseconds or so, is 2.5 milliseconds. And you can see that if we actually plot the primary beam of the DSA 110, which given the narrow field of view is roughly where we expect those FRBs to fall, this time of arrival offset shouldn't change very much. And as you'd have it, if we look at the bursts in our sample, all of them modulo some uncertainty in based on their burst width and their DM variations that might lead to little variations in the TOA, all fall within this expected time arrival offset, thus supporting our conclusion that these are indeed co-detections. They're the same bursts detected at both observatories. Now, what can we do with these? So much. It's really staggering, but time is limited, so I'll briefly talk to you about sort of what we see as far as the propagation effect in intensity, namely scattering, which manifests as two separate observable phenomena, mainly pulse broadening and scintillation, caused by some sort of scattering screen or interstellar plasma through which the wavefront propagates. Now, scintillation, the DSA 110 is perfectly geared toward this, whereas pulse broadening, that's really where the CHIME data shine. Now, what I mean specifically when I say scintillation and pulse broadening, scintillation is an interference phenomenon. So when the wave propagates through some sort of interstellar plasma, the path lengths will differ, imposing a phase change, and those will constructively or destructively interfere, leading to these striations in intensity that you see across the burst. On the left here, typically we measure this by taking the autocorrelation function of the time-integrated frequency spectrum, looking for a characteristic scale that ought to evolve with frequency. Both of these phenomena are chromatic, and if occurring due to the same screen, are chromatic in a similar fashion, scaling by the same sort of power law index. Pulse broadening manifests as this delay in time, where we fit a pulse broadening function, typically an exponential, as opposed to the ACF, which we typically fit a Lorentzian, and we look for that characteristic smearing in time, basically due to the path length differences of the rays in the wavefront. Now, when we actually look at the scintillation, we often find in FRBs that it's imposed by the Milky Way. The same is true for 11 of the 12 bursts in the sample, all of which show scintillation bandwidths at frequency scale consistent with what we expect from the Milky Way. And because this bandwidth ought to narrow towards lower frequencies at CHIME, it becomes a little bit harder to observe, but we see that it actually scales consistently for 4 of the 12 bursts that we measure scintillation for in CHIME. Now, the last point I want to make is that what this sample is really geared towards is, or really sort of allows us to do at scale, is constrain two screen phenomena. So where you have one screen that's maybe a little bit closer to the host galaxy and one that's within the Milky Way. And these two screens are actually, we can constrain the presence of these two screens if these two, the broadening and the scintillation, don't necessarily agree or are Fourier inconsistent, meaning they don't adhere to this relation, or they do adhere to this relation, the equality doesn't hold. This enables us to place a constraint on the distances of these screens collectively. These two are degenerate phenomena, but we can place an upper limit on the two. And we basically find that the two screens, when we basically find for all the bursts in the sample that they are indeed Fourier inconsistent, highlighting the presence of these two screens, which you can see on the right panel here. I'll leave you with this. So this is basically the constraint that we get, the upper limit on this multiplication of the two, which when compared to previous two screen constraints is comparable. So all falling likely roughly within a virial radius, supporting the conclusion that scattering, the pulse broadening itself, is occurring within the host galaxy, whereas the scintillation is occurring within the Milky Way. This roughly doubles the number of events that we can constrain this for. So this is really a leg up in our ability to talk about the presence of these screens, and then ultimately moving forward later, constrain things, constrain the plasma turbulence properties, et cetera, within the local environment of that fast radio burst. And I'll hand it over to Ayush.
Great. Thank you, Jacob. So I will talk about the frequency-dependent polarization effects in the co-detected samples in the second half. So the first effect that we're looking at is how does scattering affect the polarization angle or PA profiles of these FRBs. So here's a simulation where on the left, we have a simulated FRB and its PA swing. And then on the right is what you get when you scatter that FRB. So now in the leading edge, which is still coherent, you still get a bit of a PA swing. But in the scattering tail, where now you've scrambled the pulse phases, at any given time, they average out to 0. So you get this flattening in the PA profile in the scattering tail. Here's an example of what that looks like in our data. So here on the top panel is the DSA detection at 1.4 gigahertz, where in the inset you can see an 80-degree PA swing, versus in the chime detection at the bottom, now it's much wider due to the scattering, and the PA profile has flattened. And there's also a really good example of this in Mawson's talk tomorrow, so I recommend that you watch out for that. In our co-detected FRBs, we only see this in 2 out of the 12 co-detections, and in most of the FRBs, actually, they show constant PA profiles at both L-band and at 600 megahertz, regardless of whether or not they're scattered. Comparing this to most FRBs in literature, we know that most of them have constant PA profiles, but also that some FRBs, like this 121102 burst at high frequencies, we see constant PA profiles even though we don't see any scattering. So we know the underlying population does have some FRBs that do have intrinsic constant PAs, but also our result is highlighting this bias where you have a fraction of the population that did have an intrinsic PA swing, but now has been flattened due to scattering at lower frequencies. So we don't have a large enough sample to figure out exactly how many FRBs this happens to in the population, but it's highlighting that this bias does in fact exist. Next, we looked at the linear polarization fraction, or L over I, as a function of frequency, and we fit a few different models for how that could work. Here, it's just a constant model, so it remains the same at every frequency. Here is a beam depolarization model, which Rob explained really well in his talk on Monday, but the summary is when you travel through an inhomogeneous plasma, the light will scatter, experience slightly different Faraday rotations, and so when you sum up all of the light, you get depolarization from the interference in the PA angles that are different. In this final model, we've taken that beam depolarization and we've added an effect that we see in pulsar emission. So this is a birefringence effect that happens specifically in neutron star magnetospheres, where you get these X and O modes, these orthogonal wave modes, and they propagate at slightly different paths. At higher frequencies, they propagate closer together. And so the observer might see a superposition of them, and they interfere and depolarize. While at lower frequencies, they are further apart, so you might only see one or the other. And they're independently highly linearly polarized. We fit these different models using an MCMC fitting routine. And here is an example where the best fit tells us that there's beam depolarization, so the presence of inhomogeneous plasma around the FRB. And here's an example where we see this birefringence effect, where at higher frequencies, you're starting at lower linear polarizations, increasing and then going back down due to beam depolarization. The asterisk here is that the birefringence part relies on us detecting the exact same component of the burst at both chime and DSA. And that's an asterisk because remember, we're missing data between the bottom of the DSA band and the top of the chime band, so we don't have continuous coverage to visually confirm this is in fact the same component. We just believe that it is based off of all of our tests that we've done. In terms of the best fit models, 4 out of 12 of them have constant linear polarization, 5 have beam depolarization, and 3 are best fit by this more complicated birefringence model. In terms of the literature, we see a few examples of depolarization only. And most of them are in these repeaters with extreme environments, and only a couple in non-repeaters. And we only have one real example of this repolarization behavior. What our results are telling us is that maybe these depolarizing environments are actually more common because we see them in more than half of our sample, but we only can characterize them because we have such broadband observations. And so it might be more common than we think to have these inhomogeneous plasma environments around FRBs. The second thing that we find is potential evidence for magnetospheric emission through this birefringence process in a few of our bursts, again with the caveat that it's assuming that we're detecting the exact same component between the two telescopes. So with that, we will leave up a summary slide and we can take questions.
Okay, any questions for Jacob or Marcus?
Right. Marcus Lower from Sorbonne University. Very cool work. So you looked at linear polarization with frequency. What about circular polarization?
Yeah, so that one's a little bit more challenging. So DSA does a really good job calibrating their circular polarization, but CHIME, we don't calibrate it. And so we have about a 20% uncertainty in circular polarization. So we have looked at it, but it's hard to tell any specific like frequency dependent effects in circular. Yeah.
Cool.
That's really cool work. I'm Pawan from Sorbonne University. So I was just curious about the sense that you have in terms of what fraction of population would you actually see to be depolarized, given that you have a large bandwidth, which is ideal for such detections.
Yeah, so in our co-detection sample, out of the 12 co-detections, we saw evidence for beam depolarization in 7 of them. So it's, go back up. So it's the 5 that are best fit by the beam depolarization model, and then in 2 that are best fit by the birefringence and beam depolarization, we actually see evidence for like a downturn in the yellow bar.
So do you expect if you have even more large bandwidth, what do you have a sense of just from like simulations or something?
Yeah, it's
how-
hard to extrapolate from such a small sample, but it seems like it's at least more common than only the handful that we have in literature so far out of like the hundreds of polarized FRB. So definitely more common than that. Yeah.
Thanks.
Question over here.
Hi, it's Matt Dobbs from McGill. One of the CHIME outriggers is co-located with the Allen Telescope Array, and their new upgrade is coming along pretty well. That would take us out to many gigahertz. They don't have much of a detection pipeline, but it would be easy. They have a good baseband buffer. So with that possibility in the future, how exciting would it be? And, you know, the overlap in sky, their beams are smaller, so it would only be a few events, I guess. How exciting or not exciting would it be to explore that sort of?
I think potentially very, with a strong emphasis on potentially. I mean the one of the things that we haven't actually done is characterize why we only see the number of events that we've actually seen here. So if the two are you know well suited positionally or as far as sensitivity goes to actually detect the same events, amazing. Yeah, I mean the broader the frequency coverage, the better all of these constraints can be, and the more precise that we can be in discussing radio properties literally across the band. But I think if does the Allen Telescope Array localize well?
It should be able to, and they have a baseband buffer, so it's as good as, you know, the post analysis.
Yeah, then I mean, then that's perfect, and that can, I mean, that, again, that's in addition to the DSA 110, which is already positioned just out. So, yeah.
And I think one of the more interesting things is also that, I mean, we're going up to L band here where we know there's a lot of FRBs, but going even higher than that, we don't know how many FRBs actually exist at higher frequencies, or we don't know it super well. So that would be just figuring out how many do actually exist in the co-detections compared to what you should have detected, I think would be a simple and really interesting answer.
Okay, that's all the time we have for questions. Let's thank the speakers again.
Yours is on this PowerPoint, right? Yeah. You. Oh. Second. If it's not currently up, I'll just.
Smart. It's here.
Aha. All right, I'll get you back to
Yeah.
start.
Okay, just start.
Yep.
Yeah, thank you.
Okay, next speaker is Wang.
Yeah.
Who will be telling us about depolarization.
It's the propagation.
Sorry.
I'll share? Okay.
We shared that on Zoom. Sorry about that. All right, all yours.
Okay, thanks. Okay.
Oh, okay.
Okay, maybe let's start.
Yeah. Maybe I'll just explicitly share your PowerPoint. That might work better. And yeah, make sure that stays plugged in. So it should be sharing. How does it look on Zoom? The presenter mode.
Presents.
It's annoying. It wasn't doing it before. Dude.
It like creates a new screen. So if you share first and then sorry, if you full screen this first.
Full screen it, then share.
And
Okay.
then share. Right.
Okay.
Yeah.
Then share this one.
Yeah.
What about now?
Does that look good? Right.
Okay.
Go for it.
Thank you. Good morning, everyone. I'm Wang from University of CES. So today I will share my recent work about the propagation-induced polarization properties for fast-rate burst. So I will introduce from these 4 parts. I think Jerry have given very nice review for the polarization properties for fast-rate burst. So I just share some very intriguing parts here, which is the frequency-dependent polarization properties for the fast-rate burst. So you can see that from this pictures, you can see that not only the U and Q are oscillated with a frequency or wavelengths, but circular polarization components, we can also oscillate with the frequencies. This phenomenon has also been found with some burst from some sources, and also have been seen from some magnetars and pulsars. So according to the plasma physics, so this phenomenon may be caused by some propagation effects like conversion. So based on the plasma physics, so if the magnetic field is strictly perpendicular to the line side, so there will be some Faraday conversion happens. So in that case, the basic modes, the O modes and the E modes are strictly they are 100% linearly polarized. And but these 2 modes with a different frequency, with different arriving time, different phase velocity. So the summation wave of this, so the summation wave can generate some circular polarization components at some frequencies. That is so-called Faraday conversion. So it actually converted it actually let the linear polarization components converted into circular polarization components. But in reality, the truly astrophysical magnetic fields could not be strictly perpendicular to the line of sight. So if the Faraday conversion happened, there must be Faraday rotation. The question is how to measure them, how to know that how to know the contribution from the Faraday conversion and the Faraday conversion and Faraday rotation individually. So that is the biggest question. So someone proposed some methods to solve this problem, like the generalized Faraday rotation. So if we treat the Faraday conversion like a generalized Faraday rotation, in other words, we can assume that the polarization vector is a generalized power law relationship.
And then we can introduce some rotation metrics. And then we can use this method to feed the trajectory of the Stokes parameters in Poincare sphere. And then we can get so many parameters like the alpha, which is the power index, and there's so many angles. But this method only give you some parameters. Could not you could not find the physical properties directly from these parameters. So in order to solve this problem, we propose another method which is based on the analytical solution of the transformation function. So before that, we assume in general we assume that the FRB wave can go through the magnetic plasma medium. But even we don't know where is the plasma this plasma medium, we can just assume that there is a foreground and a background rotation measure layer here. Before we solve this equation, we need to select coordinates in which we select the coordinate which is the intrinsic plasma coordinate, because the subscripts of the Stokes parameters of U can be ignored. And the FRB waves always have a strong, extremely bright temperature. So the emissivity from the medium itself can be ignored. So this equation can be mostly simplified. But another question is actually the v-axis could not be always parallel to the north axis of the Earth. So we need to change this equation, change the solution back to the observer's lab frame. So and then after these operations, we can get the solution. I think everybody dislikes the equations, so I will skip this part quickly. Back to the and now we discussed the two two cases of the plasma medium. One is the cold plasma, and the other is the hot plasma. Cold plasma means the non-relativistic, hot plasma for the ultra-relativistic. So in the cold plasma cases, we can find that if the number density is really large, the free absorption will dominate the propagation. But for the lower density, and for the lower magnetic fields, the Faraday rotation can dominate the propagation. And for the higher magnetic fields, the Faraday conversion can dominate. The cases is different, really different for the hot plasma cases, in which the Faraday rotation is decreases with the Lorentz factor increasing, but the Faraday conversion rates can get larger. So this is the most differences. Therefore we can find that for a hot plasma medium, the Faraday conversion can be much easier to occur at a higher Lorentz factor. And we consider that we're introducing scenario which is called the mixing Faraday spectrum. The mixing Faraday spectrum have a comparable Faraday rotation and Faraday conversion. So in that case, we made some simulations with different incoming wave properties, like showing in these pictures. We can also find that there are some common properties, like there is some precision in Poincare sphere with the frequencies, and we can find that both all of the Q, U, and V Stokes parameters can oscillate with the frequency or with different phases, and then we can also find that the position angle looks like an S shape. So the trajectory in the Poincare sphere in that case is very similar with the Foucault pendulum. The Foucault pendulum actually consists with the two different frequency different rotations with different frequencies and different directions. One is the Earth spin, the other is the pendulum itself. So that is similar with the mixing Faraday spectrum. One is the Faraday conversion, the other is the Faraday rotation. Actually, both the cold and hot plasma cases can generate such scenario. So the cold plasma requires a large perpendicular magnetic field components, but for the hot plasma, it does not need. But the hot plasma just need a large Lorentz factor, and the hot plasma cases will always predict a large dispersion measure here. We then develop this analytical solution method to develop the code to help observers to make some data precision. That's my students Xiaohui Liu helped me do this. We have Faraday rotation, Faraday conversion, FRB here. So all of these words have the same initial alphabet, which is F. So we call this method mixf. So the mixf code has been published in GitHub. If you like, if you want to use this method to make some data precision, you can find it. So by comparing with the generalized Faraday rotation methods and the mixf methods, we can find that both of these methods can feed the data very well. But the mixf methods can show can can give you the more physical information of the plasma medium, like the magnetic fields, column density, and also for some incoming wave parameters. And we also use this method to feed the observation data from another repeating FRBs. And back to the question: what is the plasma medium here? So some FRBs are associated with a persistent radial source. So if we assume that the FRB wave can go through the plasma medium or directly go through the persistent radial source, so I can see that by considering the synchronous radiation mechanism, the persistent radial source is a hot plasma here. Ultra-rare is hot plasma, so it can generate synchronous radiation. That is the very wonderful candidate for the persistent radial source. So we can see, but based on this equation, we can find that it is very easy to generate Faraday conversion here. But the question is the observed number density or the of the event rates of the Faraday conversion is inconsistent with what we predict. So basically, I don't think the persistent radial source may be the modeled hot plasma medium here. So in order to generate Faraday conversion and for some repeating FRB source, it might be cold plasma medium here, maybe possibly some stellar wind from the companion stars or something others. So the last part I really want to show you is the results from the recently very active repeater. So in this source, we actually have detected so many polarization samples, and among these samples, we have detected so many bursts with the Faraday conversion here. We can find that the Faraday conversion can occur within several days, which indicates that it looks like the perpendicular magnetic fields appears within several days. And we also find that the rotation measure contributed by the background field is roughly equals to 0. So which means that the plasma medium is really close to the FRB source itself. So it looks like a binary system. Just just assumption. So for the summary parts, the most important thing is we propose a new method to process data, which is called the mixed-F method. So if you do some data processing of the polarization data, if you like, you can use our methods to make some data processing. It may help you. And one notion here is if you find that the circular polarization components is frequency dependent, like showing some oscillation structures, you will not only use the Stokes parameters of U and Q to derive the rotation measure. That is wrong, because you should consider the Faraday conversion here. And the last part is we can use these methods to study the magnetic element for fast radial burst. It can help us to understand the truly physical parameters of the plasma medium. So that's what I really want to share with you. Thanks.
Hey, it's great that you were under time, so we have actually time for questions.
Yep. We'll go at the back here.
Hi, Wei-Yang. I am
Hi.
Om Gupta from UT Austin. I have a couple of questions. One is, what are the initial Stokes parameters that you have input into your model so that you can fit the GFR spectra? And my second question is,
yeah, maybe it's too small. I guess you can see the input parameters include magnetic fields, the angle between the line of sight and the magnetic fields, and the Coulomb density here, and the temperature of the medium, and also the last three parameters are based on some polarization properties from the incoming wave. So we need we need 6 or 7 parameters here.
so so you need some non-linear, like the initial wave should be completely linearly polarized, or you need some additional polarization going in to your medium?
The fitting result shows that then for some bursts, the incoming wave is not totally totally linearly polarized. So actually, the incoming wave may have some circular polarization components.
Okay. And my second question is, I did not understand. You said the PRS should be capable of generating the circular polarization because of the hot component, but it's not matching the RM, the predicted RM that you want. Is that right?
Sorry, what?
If I'm not sure whether I understood, you said that the PRS should be capable of generating the required circular polarization from Faraday conversion.
Yeah, for the highly circular polarized wave, it might be it possibly dominated by not dominated. It may cause both from the propagation effects and the intrinsic mechanism. For the propagation effects, you may find that the circular polarization component is frequency dependent. But from Jinchen Jiang's paper, we do not find we did not find such observation. So it's possibly dominated by the intrinsic mechanism. But the propagation effects like the Faraday conversion can also generate some circular polarization components here.
Okay, thank you.
Thank you for the talk. So do you see any evidence, I guess, in fitting these repeating bursts, do you see any evidence of multiple Faraday rotating media, for example, a hot and a cold plasma, or some superposition of whether you have like a local rotating medium and then a and then a ISM rotating medium, or is it largely dominated by a single Faraday rotating medium?
Actually, we don't, because I think that the question is actually we don't know where is the plasma medium here, possibly located at the host galaxy or in our Milky Way. So it depends on because there is some degenerates between the background rotation measure layer and also for the foreground rotation measure layer here. So possibly we can know, possibly one day we may know where is the plasma medium here by determining by determining the value of the rotation measure contributed by the foreground layer here, I guess.
Thank you.
That's all the time we have for questions, unfortunately. So let's thank Wei Yang again.
Yours was PowerPoint again, or?
No, it's a don't touch it. I'm free.
Oh yeah, just what was the format?
Keynote.
Ah, right. Oh, and I think I need to, yeah, I think I need to reshare the.
Good. Okay, our next speaker is Ilya Kirkin.
Thank you. And first of all, let me thank members of FRB2025 collaboration for their help with this project, and specifically Alexandra and Luis. So Alexandra gave a very interesting talk yesterday. Luis will be speaking tomorrow, I believe, and I urge you to go and check out their amazing work. And I think that I should probably start with addressing the fish in the room. Some of you might be wondering, why did I put a very surprised fish in my slide? So as astronomers, I think we all know that when you start a new project, you build a new telescope or start a survey, the right name gives you at least 50% of success. So internally in F4 collaboration, this project is known as Mahi Mahi. Hence I asked ChatGPT to generate a fish in the galactic magnetic field. Speaking of, what do we actually know, or what we think we know about the galactic magnetic field? So we know, well, we think we know that there was a primordial magnetic field in the beginning of the universe, and then in the later stages, after the structures grew, galaxies formed and evolved, the magnetic field got amplified, and probably all galaxies right now should have magnetic field. And this is a nice example from the hydrodynamical simulation that shows a snapshot on one random halo and the distribution of magnetic field of different strength in and out of this galaxy. So it's fairly easy to simulate magnetic field in simulations, but it might not be that trivial to detect them in real life with observations. And FRBs are actually very uniquely suited as probes of magnetic field, as we heard all morning today and yesterday as well. And noticeably, well, you all remember this paper by X. I think it was the first paper that actually probed the magnetic field in the foreground galaxy of the FRB. Unfortunately, it was just one galaxy, one FRB, so statistic is not really great. And you know, after all these years, it's interesting if we can do better, because maybe we have more statistical information. So I'm not gonna go into the details what RM is. You heard about it today all morning. We also heard a very nice talk on Monday about all the propagation effects, but I want to stop for a minute on what environments can actually contribute to the observed radiation measure, because I think it's important. So we know that, you know, FRB originates in the host galaxy, and the first environment that might and probably contributes to the observed radiation measure is the radiation measure associated with the host ISM or FRB progenitor itself, which is given by this term RM local host. Then the signal travels further, it goes through the halo of the host, which might also contribute to the observed radiation measure. Finally, it goes through the IGM and might intersect the halos of the foreground galaxies. And then it reaches us in the Milky Way, giving us the final contribution. So usually people ignore these two terms. And well, I guess mostly because there is no information about the foreground structures, or is there? So one of the motivations for this work is actually check if can we simply ignore these factors. Yeah, one assumption that I will use as others is that IGM contributes 0, which is warranted given that the estimates show that this radiation measure at least 2 or 3 orders of magnitude smaller than what you would expect from the galactic environments. So we have assembled a sample of 14 FRB sightlines, and besides, of course, the requirement of very nice, good localization, we also require these FRBs to have measured rotation measure. Sorry. And also, we need spectroscopic samples of the foreground galaxies. So it's just a sample summarizing the observables. Better you can see this from these plots. On the left side, you see the extragalactic rotation measure plotted as a function of redshift. So our sample is black, and then I'll show 2 other samples from previous works. And on the right side, we plot rotation measure, well, extragalactic rotation measure as a function of the direct measurement of the dispersion measure in the host of some of the galaxies for which we had Muse data. These measurements come from the very nice paper by Lucas Bernales-Cortés, to which I really want to refer you. It's a very interesting way to measure the DM of the host directly without invoking the McCart relation. It's probably the future of the field. Anyway, so this is the observables, right? This is one requirement of observed radiation measure. What about the foregrounds? So luckily, we have FLIM-FLAM, which is a survey aims at mapping the foreground structures of multiple FRB sightlines. And last year, we published the first data release and the first analysis that gave the first measurement of the distribution of cosmic baryons. And along with this measurement, we acquired lots of information about foreground structures, specifically halos of galaxies and clusters and groups. So this plot summarizes what we have in our sample for the foreground halos. Not all sightlines are covered by FLIM-FLAM data. We also used Muse data for those that lack FLIM-FLAM data. data. And basically, I mean, it might be a busy plot, but the message from this plot is that each sight line intersects at least one halo, when in reality, probably more than that. So it's interesting to check if they actually contribute to the rotation measure. And this is time to start building our model for the observed rotation measure, which is given for a single FRB by this equation. And let's go quickly each term at a time. So first we start with the Milky Way contribution. We of course have the Faraday rotation maps for our galaxy. And for given the position of the FRB on the sky, we can get nice, well, kind of Gaussian distribution for the rotation measure of the Milky Way. Next, to describe the rotation measure of each individual foreground halo, we use the modified NFW profile, which is characterized by mainly two parameters, which is mass of the halo, M halo, and F gas, which is the average fraction of cosmic baryons that reside in ionized CGM of individual halo. If you integrate this density profile, you can get the rotation measure of a given foreground halo, which depends on this B parameter, which is the average magnetic field in the foreground halos. So if you do this, one important thing is that halo mass is a very uncertain thing, and we should take this into account. And we do by randomly sampling the Gaussian distribution of the halo mass for a given halo. And so if you do this, you will actually get not one RM measurement for halo, but a distribution which would look like this. You can notice that it's only has positive side, just by construction, which corresponds to the case where the magnetic field is aligned with the sight line and directed towards the observer. In order to take into account the other case where the magnetic field is directed in the opposite direction, we simply mirror this distribution to the negative side, and then we have this full distribution of rotation measure for given foreground halo. And then we move to the halos of the hosts. We use the same modified NFW profile to model it. Again, we take into account both geometrical options for the magnetic field and distribution. Well, this is an example distribution that looks like this. And it depends on this B parameter, which is the average magnetic in the halos of the host of the FRBs. Finally, we come to the RM of the local environment. Again, luckily from FLIM-FLAM, we have direct measurement of this dispersion measure in the local environment due to the ISM or FRB progenitor. And using the conversion between DM and RM, we can directly sample this distribution, this posterior distribution from the FLIM-FLAM DR1 results, and get the RM local distribution that is shown here. Again, the geometrical factors are taken into account. So we have four parameters, free magnetic fields in different environments and F gas as well. And in order to infer them, we use MCMC. And the first step is, of course, to build the likelihood function. I'll quickly go through the steps of doing so. Well, of course, you create the parameter space, and for a given point in this parameter space, you find the corresponding distributions of rotation measures in the foreground halos, in the host halos, and in the local environment. You, of course, you find the RM distribution of the Milky Way, you sample them, combine all these measurements into one RM model, which is shown by this black histogram. And then you feed this histogram with the kernel density estimator and evaluate this KD PDF at the value of the observed rotation measure for a given FRB. So this is done for a single sight line. So you repeat the same steps for each point on your parameter grid, and then, and then you compute your joint likelihood by summing up the log likelihoods for each FRB in your sample. Then we have priors that are listed here, and one important thing is that we require that the magnetic field in the halos will be smaller than in the local environment, which I think is warranted given the results of hydrodynamical simulations. One extra prior that we have is the prior on the diffuse baryon fraction, which is similar to what we used in FLIM-FLAM DR1, although there we didn't know the FIGM. Here we have a measurement from FLIM-FLAM, and we use for the mean, which is shown here by the black curve. we use the average value from the Flim Flam of 0.6. So when we sample this likelihood with MCMC, we get these results. So the top left is the F gas fraction, and then diagonally you have three different components of the magnetic field. One note, so we have a very nice measurement, looks like, except maybe for the foreground galaxies, because the posterior is still, well, it's not attached from zero, you cannot really distinguish the zero case. That's why we put the upper limit instead of a measurement. Anyway, we can compare it with previous results. So I devised so the plot shows different measurements of the magnetic field in the CGM and the ISM of the galaxies. So on the left side, most of these measurements come from the magnesium-2 absorbers in the quasar spectra, except Axis work and Kovac et al. They use lensing. On the right side, we have two works on the analyzing FRB samples. But I stress that both of these works assume that all rotation measures coming from the ISM of the host galaxies. So technically, in this right panel right now, there is no host halo contribution. We put our results on this plot, so you can see that. So our CGM measurements are consistent with others, and I think the takeaway message from the left panel is that halos are important. The degree of their importance is still to be determined, but I think that we should really have knowledge about the foreground structures if we want to correctly describe the, well, either rotation or dispersion measures. And on the right side, you see that we're in a good agreement actually with the average values for the ISM measurements, but the scatter is probably, well, scatter is given by the individual measurements, and plus some of this can be attributed to the halo contribution, which was omitted in previous works. So my conclusions here, we used the sample of 14 FRBs to measure magnetic fields in different galactic environments. For the first time, we split and measured the magnetic fields in host halos and ISM. We also put a limit on the magnetic field in foreground halos. And we estimated the fraction of cosmic barriers. So I think this shows the importance of the foreground surveys, and the future generation of telescopes will give us information, maybe if it exists, about the redshift evolution of the magnetic fields as well. Thank you.
For a couple questions.
Over to Stella.
Nice talk. Sorry if I missed this, but we saw a couple of examples yesterday of FRBs that had extreme RMs and then evidence of, magnetic fields local to the source that, are 10 to 100 times larger than, the maximum value in your prior. So are all of your sources relatively low RM? Are you explicitly excluding cases where there might be an extreme local contribution?
Yeah, so our sample doesn't have these extreme RMs. That's true. I think that they will significantly bias our results in the sense that probably that extreme RMs as well, as we heard yesterday or today, they are associated with some local screens, right, that give us these huge values. I don't think that our analysis is, well, at least not yet sensitive to this particular screen. So maybe in the future we will include them.
Thank you. I think it's fascinating what you're doing, but I think I might be missing something basic, and maybe you could just explain it in very simple terms. But what observational information, apart from model assumptions with NFW profiles, what is that? What observational information are you using to split to separate the B field components from one halo versus another halo? I'm not understanding that.
So first of all, we need to identify if there are any foreground galaxies between us and the FRB, right? So For that, we do the spectroscopy of the fields around the FRB position. So we determine the redshifts of the galaxies. If they're between us, okay, that's step one. Step two, we determine the impact factors of this that these foreground galaxies have with respect to the sightline. Because when we construct the model of the halo, we need to determine if it's actually intersects the sightline, right? So we need to know how far away it is. And also we use then photometric surveys to get magnitudes, which we can then convert to the stellar masses to the halo masses, in order to get the profile of the density of these halos. So these are the main observables that we use. So redshifts, photometry, and impact parameters.
Okay. So I don't understand where the field comes from. So the density, I totally understand. It's the field I'm not sure about, but perhaps we should talk at coffee
Sure.
because this could be longer.
And I believe the next speaker is online. So if you're there, will you share your screen? Right. Oh, it's a video. Okay. Oh, apologies. Yeah, I'll start that. And we should be able to hear it, but just give a thumbs up on Zoom if you can hear this once it starts.
Okay, good morning, everyone. My presentation focuses on fast polarimetric observations of this hyperactive FRB 2024-0114A. These are my collaborators. Our data processing covers births from January 20th to August 30th in 2024. We analyze over 5,000 births with SNR exceeding 20. And the complete catalog is in Junshou's talk. He will give a detailed introduction later. This plot shows the overall analyzed results, including the temporal evolution of RM and the linear or circular polarization degrees. The mean RM of this value is around 363. And from the plot, we can see there is a very significant RM variations. So we think maybe there is a periodicity. So after removing a second order polynomial trend, we do the Lobscago period search on the daily average RM values. And the result revealed around 60-day periodicity with 4.5 sigma confidence. Fast observation of this source is still ongoing, and we will check these results using new data later. Additionally, over 1,700 birds exhibit circular polarization degrees exceeding 10%. And the circular polarization fraction and the absolute RM values of this source generally follow the empirical relationship proposed by Zhang Yunkun, matching a power law trend. And with the large circularly polarized sample, we identified multiple births showing Faraday conversion phenomena. Faraday conversion is on the electromagnetic field, electromagnetic waves transfer between linear and circular polarization states. If it occurs on Poincare sphere, is manifest as polarization vector deviating from the v-axis. And spectrally, we can see the oscillations in Stokes V parameter versus the square of the wavelengths. And totally, we detected over 200 bursts with these interesting effects. And so to further analyze these special bursts, we applied Wang Liang's model to perform a parameter fitting. He has given a detailed introduction of this model just now. Maybe. And we think compared with the GFC geometry methods, this model can improve more scientific values for analyze. So we choose this model. And this is the result. The contour of the parameter distributions. With these results, we obtain the constraints of the magnetic field and the electron density of the Faraday conversion medium. Well, Faraday conversion is the probe of magnetic ionic environment of FRB. We can learn about the knowledge of the magnetic field configuration through through Faraday conversion. So it's very important to study the long-term change of this UCC effect. But the most intriguing finding is that most Faraday conversion events clustered dramatically within a few days, especially for March 12th, with over 170 events. It's appearing just like flares. We use the term Faraday conversion flare. And we think this may indicate a rapid magnetic field reconfiguration within the Faraday conversion media. And the further analysis is still ongoing. We are trying to find if there is still potential Faraday conversion events that we ignored before. And finally, this is a summary of my presentation. Okay, thank you.
We're going over time, so we're going to go straight into our next last speaker.
Yeah, which is also pre-recorded.
Oh. But if folks have any questions, I encourage them to post some questions on the slide.
Here with Sam.
Hello everyone, I'm Wanjing Lu from NOC, and sorry to pre-record this flash talk to prevent any network issues. I'm going to share our progress on constraining the physical scale of FRB local environments. And this work is supervised by Professor Dongzi Li, who joined the Tsinghua University, China, very recently. As we all know, repeating FRBs could show significant evolution according to many long-term monitoring campaigns. For example, the variation and even the reversal of Faraday rotation measure of some repeaters imply that they are surrounded by evolving magnetoactive medium. And because of that, current environmental models collapse into two scenarios: young supernova remnants and binaries. One of the key differences between these two models is their physical scale. So in both systems, FRB emitted by the celestial object may propagate through the foreground plasma screen in the closing environment, for example, the outer shell in supernova remnant or stellar wind in binary, and be received by the observers. The propagation path of FRBs could be different if the FRB source has a transverse velocity. perpendicular to the sideline, and the slide shows. Assuming that the propagation effects, including depolarization, scattering, and the ion variation, are dominated by the foreground plasma screen, we derive this formula to constrain the physical scale of FRB environments. Here is the main plot I want to show you. The variation timescales were obtained from the autocorrelation of the FRB RM variation curve for artificial inspection. For two FRBs that show significant arm reversal, the arm variation was split into different time spans to figure out the changing rate. The depolarization and the scattering scales are measured roughly at the same time with the arm variation. And furthermore, the error bars are not the measure uncertainties of the physical scale, but the range of velocity from 10 to 1,000 kilometers per second. The gray dashed lines refer to the spatial distance of this transverse motion. For comparison, we plotted the ratio between the spatial moving distance and the physical scale in the lower panel, altogether with the varying velocities. So we draw the possible parameter spaces of SNR and binary based on the galactic observations. And the plot is shown the physical scales of FRB 2020 1124A and 2019 0520B favor the binary model, and others lean to SNR, which is also distinguishable in the lower subplot. The ratio basically means the ellipticity of the binary orbit, or if there will be one, and the propagation motion of the central compact object is negligible with respect to the expanding outer shell, especially for the newborn supernova. And I will introduce some of the repeating FRBs to show the detail. And FRB 2019 0520B was reported to show an arm reversal in 2 years, observed by several telescopes. And so does FRB 2020 1124A. As for FRBs that show either circular arm variation or fluctuation, as indicated in the purple circles, they are more likely to be deeply modulated by the local SNR-like environment. Here, we investigated multiple FRB sources, including the R3. To conclude, this work is an independent constraint on the physical scales of FRB local environments without any prior. For example, the arm reversal is expected during the periostrum passage in binary systems. But we didn't use that knowledge, we just combined multiple propagation effects, including the dipole, the scattering, and the arm variation. So the result indicates that there are potentially different populations despite of the environmental model prior. I will end here, and any questions are welcome in the Slack, during the Slack and the email. Thank you all.
Right, that concludes this session. We'll now break for coffee. Let's thank the speakers again.
I want to try to do Okay, it's not quickly. I don't know who I told. It's Jason.
Yeah.
Okay.
Fix sharing later.
Okay. It's Phoenician. Phoenician.
Ah.
Yeah. It's like to introduce a ton of slides and then make people we've got the signs.
Sorry, I was just I didn't have the I just came back, so I didn't have that schedule.
It's Manisha Caleb.
Re-recording process.
All right, I'll just introduce the session. You'll hit go on the doc, yeah. All right, welcome back, everyone. This session is starting a little bit late, but we'll try and not eat too much into the lunch break. So this is a session on ultra-long period transients, where ultra-long means, more than seconds in our case. And the first speaker is going to be Manisha Caleb, who's going to be giving an overview of ultra-long period transients. This will be a recorded talk. She's sleeping right now, so she's unavailable to take questions directly. But if you have any questions for her, please place them in the appropriate Slack channel.
Good morning, everyone. I'd like to thank the organizers for inviting me to give this talk today. Now, in my talk, we're going to explore long period radio transients, what we've learned so far, how they might connect to FRBs, and why they're challenging our ideas about where and how coherent radio emission can occur. But before we go into the talk, the term LPT or some variation of it started popping up about 2022. While the terminology isn't exactly standardized, most versions seen here seem to be used interchangeably in both the literature as well as colloquially. But as astronomers, we do tend to have a soft spot for three-letter acronyms that roll off the tongue. So for now, it does look like the LPT is the one that's sticking. Now, in order to understand long period radio transients or LPTs, we first need to understand the PP dot parameter space. And this is something that's commonly used to classify neutron stars and understand their evolutionary paths. So here we have in the figure, we have spin period on the x-axis and period derivative on the y-axis. So this is the rate at which the object is slowing down. Diagonal lines represent constant magnetic field strength. So these go from the top left to the bottom right, and it's calculated from basic dipole radiation physics. The pulsars, as you can see, sit down here in the bottom left corner with fairly well understood properties coming from about 60 years of observations. And then up here we have magnetars with much stronger magnetic fields, so they're like the slightly less understood cousins of pulsars. The lines going from the top right to the bottom left, so these are called the death lines. And they're a theoretical boundary beyond which radio emission is expected to stop, because the spin and the magnetic field aren't strong enough to sustain coherent radio emission. Now, there are a few versions of the death line depending on the assumptions you make, like whether the emission is from pair production or curvature radiation or multipolar magnetic fields. But it's important to note that this isn't a hard boundary, but it's more of a gray zone. So as the pulsar ages, its period increases towards the right, it moves to the right of the plot, it crosses the death line, and it stops emitting in the radio. And this was indeed true until a recent plethora of coherent radio sources with long periods have been identified, and they all seem to lie in this death valley or graveyard region beyond the various death lines. And these discoveries have opened up a whole new parameter space to be explored. Now, I think this figure here, it quite nicely captures why the sources I'm talking about today are really special. So this is the transient phase space, and it showcases a menagerie of radio transients, both coherent as well as incoherent. So in the figure here, we have time scale or the burst duration on the x-axis and brightness temperature or luminosity on the y-axis. So we've seen a few versions of this plot over the course of the conference. The 10 to the 12 brightness temperature line separates the incoherent emitters in the top region from the coherent, or the incoherent emitters in the bottom right region from the coherent emitters in the top here. What I'd like to do now is draw your attention to pulsars here at millisecond timescales. So these are neutron stars in our own galaxy. And if you go up about 8 orders of magnitude, we have the elusive fast radio bursts at much higher brightnesses and at extragalactic and cosmological distances. However, it's quite obvious, though, that a significant portion of this phase space remains unexplored. But with the discovery of these new long period sources, we're starting to fill out some of this previous empty territories of phase space. And it turns out that the space was not actually physically empty, but just previously uncharted. Now, these transients, they're sort of appearing to blur the lines, and it raises a very fascinating question. Are all these different types of coherent radio signals, that is pulsars, LPTs, and FRBs, are they all actually coming from the same source? Are they just behaving differently depending on the environment, their age, and the activity levels? So what exactly is a long period transient or an LPT? Now, first of all, these are just a phenomenological term. LPTs are highly polarized, coherent radio bursts of unknown galactic origin. They're unusual because their rotation periods are from minutes to hours, so these are fairly longer than typical pulsars, and their burst durations last seconds to minutes. Again, they're far longer than the typical millisecond durations of pulsars. Some repeat very regularly like pulsars, some others are more irregular like intermittent pulsars, and then you have some others which are truly transient in the sense that they've only been active for short periods of time of the order of a few months or even weeks. They're highly polarized, so the emission can be both linear and circular, and they are typically steep spectrum. Some of these objects are in confirmed binaries, while others appear to be isolated. But despite deep, extensive multi-wavelength follow-up observations, their origin and their nature still remain uncertain. Now, just quickly rewinding to 2005 for a little bit of historical context, even though the term LPT appeared only in 2022, the source GCRT 1745 was very likely the first LPT to be identified. Now, Scott Hyman and his team, they found 5 bright 10-minute long bursts reoccurring every 77 minutes in the direction of the galactic center. Now, much like the Lorimer burst in the context of FRBs, this particular source stood out as a clear outlier. Now, this GCRT source at that point in time, it hinted at a new population, but without other examples, it just remained a curiosity like the Lorimer burst. So this particular source actually pioneered the field of long-period radio transients more than a decade before other such sources actually began to emerge. Now, altogether, we've discovered, I think, less than 20 long-period transients. Not all of them have been published, but this number is slowly but steadily growing, and we're still very much in the early days. We can loosely group the LPTs into a few different categories. So you've got GCRTs, M-dwarf, white dwarf binaries, long-period neutron stars, and a handful of them that remain unclassified. Now, we know about compact objects, right? We've known about white dwarfs and pulsars for decades. So why is it only now that we're finding these long-period radio transients? Well, it mostly comes down to how we search for radio transients. Traditionally, we use the time series analysis where you slide a boxcar function across the data to match the shape of the pulse. And this method works really well for detecting short duration signals from pulsars and FRBs. It's efficient, it's computationally cheap, and it's great for real-time commensal searches. But the catch here is that it's inherently limited by the width of the boxcar that we choose and you can computationally process. So this makes it much harder to pick up long duration signals like those from LPTs. Additionally, in time series analysis, there's also the issue of non-stationary noise and baseline variations on much longer timescales. So to overcome the limitations of these traditional time series searches, we can turn to the image plane. Now, this approach, which we often refer to as fast imaging, basically looks for transients in a series of short, regularly spaced snapshots rather than relying on a single long integration. For example, if you have a 1 hour long observation with 8-second time resolution, you get 450 individual images to search for transient sources. And what you're seeing here is exactly that. So you've got a stack of 8-second snapshots from Meerkat observations of the Vela X1 field. So this is where we discovered a source with a period of 76 seconds. And this source had a burst width of only 300 milliseconds. The source very clearly showed up in these fast images, as you can see in that little stack there. So fast imaging, though it's brilliant for detections, you do need beamform time series data as well to really characterize the pulses, because this gives you a wealth of information about pulse morphology as well as structure. And as you can see in the dynamic spectra at the top here, this object produces some of the most diverse and complex pulses we've ever seen from a coherent radio emitter. Now, these two types of searches are better visualized in the figure here. So traditionally, pulsar surveys have focused on millisecond duration bursts and short periods, whereas image plane surveys have targeted much slower variables like supernovae and variable stars, and these are over timescales of hours to days. But you can see that this leaves a gap, and LPTs fall right in the middle. Their pulse durations are basically too broad to be picked up efficiently by conventional time series methods, and they're too narrow to stand out in the image stacks, which you then integrate over long periods of time. So it's not really a surprise that they've been missed for so long. They simply just fall between the cracks of our standard search techniques. So it wasn't until short time scale imaging came along that this gap was actually bridged, and we're starting to fill out this region of space now. Now, if you look at the various categories, these are the published sources in each category at the moment. And if you scan the QR code there, it'll take you to an online database or a catalog of LPTs. Now, there are a few more sources which have been categorized as galactic center radio transients simply because they occur in the galactic center, but they don't have a measured period, which is why I haven't put them under the LPT banner here. Now, it is still small number statistics, but this is how they're distributed at the moment in our galaxy. And I think it's too soon to draw any conclusions or look for any trends, even though it does appear to seem that the white dwarf binaries are at higher galactic latitudes and maybe older sources. Right, so we've already very briefly looked at the GCRT and a long period neutron star. Now, M12 white dwarf binaries can also produce these long duration coherent radio bursts. Now, these systems are composed of a white dwarf and a late type main sequence star that are detectable in the UV and optical and other wavelengths. But unlike canonical neutron star pulsars, it's believed that the source of coherent radio emission, in this case, is intrinsically tied to the binarity, and it's due to the magnetic interaction between the two stars. But for these systems, since we don't typically have spin down measurements, what I've shown here are their periods as vertical lines. Now, of the four systems that are known, AR, SCO, and J1912 are classified as intermediate polar. So this is where the white dwarf spin is asynchronous. So it's shorter than the orbital period. Now, in contrast, you've got the ILT source and the GleamX J0704. So in this case, the spin appears to be synchronously locked to the orbital period. It's typically of the order of a few hours. So this makes them more similar to the polar class of cataclysmic variables that are seen in the optical. What's intriguing is that these sources give us a possible analogy for periodically active FRBs, which could originate from highly magnetized neutron stars interacting with a massive stellar companion, but with just scaled up energetics compared to the white dwarf system. So maybe there is something to be learned here in terms of emission processes for FRBs. Now, Iris will be presenting the details of the ILT source later on in the session and also more on white dwarf binaries broadly. For the rest of the talk, what I'm going to do is I will focus on how long period transients can be linked to FRBs and the broader neutron star population. And I'm going to be doing this by considering these three unclassified sources that I've highlighted in bold here. So one of those Andy will again touch on later on in this session. So the first one we're going to be looking at is GPM 1839. So this was discovered in 2023 in the MWA Galactic Plane Survey during short timescale imaging searches for transients. And this particular source was seen to repeat with a period of 22 minutes. Now, Meerkat beamformed observations of this source showed that the pulses, they were about 5 minutes wide, and they exhibited this beautiful quasi-periodic substructure and flat position angles, as you can see from the figure on the left there. So Natasha and her team, they looked through archival radio data, and they found that the source had actually been active since 1988. So almost 3 decades or possibly even more. So this basically indicates that there may be more of these long-lived, long-period transients in archival radio data. Something to note is that the source is also seen to exhibit short-duration substructures with drifting behavior. Now, in this figure here, C1 is the wideband emission component, and C3 and C2 in panel C are the 2 narrowband emission components. And we see that C3 appears to drift. Now, this sort of frequency drifting behavior has been observed in FRBs as well as in solar bursts. But the drifting behavior observed in solar bursts typically involves longer timescales, longer than the tens of milliseconds that are seen here. And they also exhibit a slower drifting rate compared to the substructure that is seen here. What's interesting is that the substructure of this GPM source right here is quite reminiscent of the drifting rates that are witnessed in repeating FRBs. And here I've got an example from CHIME. So this suggests a possible shared emission mechanism or maybe even propagation effects between this particular source and repeating FRBs. Another source I'd like to highlight is ASCAP J1935. Now, this particular source was discovered while simultaneously monitoring a GRB and searching for pulses from an FRB at the same time. Emil Lenz from CSIRO, he basically spotted bright pulses lasting 10 to 50 seconds in the observation. So the observation itself spanned 6 hours. Now, by eye, just looking at this light curve here, you can see that the pulses seem to appear every 54 minutes. In the deep image, we see that the long period source sits at the edge of the supernova remnant that hosts the famous galactic magnetar SGR 1935. Now, if you look at the table, the properties of the ASCAP pulses show that they have typical widths of about 10 to 50 seconds. It's 90% linearly polarized with negligible circular polarization. And the in-band spectral index over 288 megahertz is seen to be fairly flat. Now, follow-up observations of the field with ASCAP showed more pulses, but not every observation or integer period. And what I mean by this is, if you look at the plot on the right, the different colors represent the different days, and each row in this case represents one period of 54 minutes. And it's quite obvious that we don't really detect a pulse every period. And this shows that the source is quite intermittent. We then followed up the source with the more sensitive Meerkat telescope in both imaging and beamformed observations. And we found 2 weak pulses, one of which is shown in the figure here. So the black is the total intensity, and the pink and the blue are the circular and linear polarizations. And you also see that the burst has a little cute little, it's got a precursor and a postcursor. And the Meerkat beamformed observations gave us a DM estimate. What was very odd, though, is that the properties of the Meerkat pulses were absolutely nothing like that of the ASCAP pulses. The Meerkat pulses were 370 milliseconds wide, they were highly circularly polarized and steep spectrum. The only thing in common between the Meerkat and the ASCAP pulses were the RM and the coordinates. And this was what gave us confidence that it was indeed the same object that was producing these different bursts. Also from the plot on the right, you can see that the times of arrival of the puny little Meerkat pulses here quite nicely lined up with that of the ASCAP pulses. And this suggests that the emission is likely coming from the same region of the object. So overall, we see that this particular source emits 3 different emission states. So it's got the bright pulse mode, which was seen by ASCAP. It's got the weak pulse mode, which was seen by Meerkat. And then it's got this quiescent or nulling mode, which is seen by both telescopes. And these different modes are quite similar to what has been already been seen in pulsars. And I'm not quite sure how a binary system would be able to account for all these different modes. Another LPT I'd like to highlight is J1839. So this has a remarkably long period of 6.45 hours. And when I say period, I actually mean rotation period. Now we know this is the rotation period because, like some orthogonally rotating pulsars, we detect emission from both magnetic poles. And that's what you see in the animation here. So if you look at the light curve, we see a bright pulse at the period and a weak pulse at roughly half the period. Now, what's notable is that there is no high energy counterpart seen for this particular object so far. And building on that, we have the same pulse here. So the figure on the left, the same pulse observed simultaneously at both the U band and the S band frequencies at Meerkat. Now notice that the pulse at U band is almost twice as wide as the pulse at S band. And this behavior is a classic example of radius to frequency mapping that is seen in pulsars. So this is where the emission region is located higher up in the magnetosphere at low frequencies, and this causes broader pulses. And then as you move closer to the neutron star surface, you get narrower pulses at higher frequencies. And again, like I said, this effect is quite commonly seen in regular pulsars. Ongoing monitoring since its discovery also reveals a decline in flux density over time. And this gradual fading is quite reminiscent of the radioluminosity evolution that is seen in a handful of known radio-loud magnetars. And this suggests that this particular source, ASCAP 1839, might share a similar evolutionary path or maybe physical nature to these magnetars. Finally, it's worth noting that 1839's period is actually not too different from that of the well-known X-ray magnetar 1E1613. Now, this particular magnetar is associated with a supernova remnant RCW103, I think. But this source is active only in the X-rays and is radio quiet. The takeaway here is that many of the properties of 1839 is quite similar or closely resembles those of known magnetars. So what are these LPTs? We know they're compact objects, so it can either be a neutron star or a magnetic white dwarf. Now, an isolated neutron star can explain the polarization properties and the emission state switching phenomena quite naturally because it's been seen in other pulsars. But we haven't seen a high energy emission for most of these objects. Now, Andy, later on in this session, will talk about high energy emission for one of the LPTs, but for most of them, we haven't detected any high energy emission. And the radioluminosity is much higher than the spin down luminosity if you assume a magnetic dipole emission. So it can't be spin down powered. In this case, it really needs to be powered through magnetic or decaying magnetic fields. In the other scenario, you could have magnetic white dwarfs. In this case, you have a higher moment of inertia, which means that it increases the spin down luminosity. But the absence of other nearby highly magnetic white dwarfs in the radio and the fact that almost all known magnetic white dwarfs have magnetic fields less than about 10 to the 9 Gauss makes this scenario quite unlikely. Could these unclassified objects be in a binary system similar to the other ones we've already seen? So maybe they're in a binary system with an unseen cool normal star. Maybe, but we still don't have any multivalent evidence for binarity in most cases, or at least for all cases in the unclassified objects. So what are these LPTs? Are they neutron stars? Are they white dwarfs? Or are they some other transient altogether? I think the jury is still out there, but it does seem to be some combination of 1 and 2. What is intriguing though is that the pulse morphology between these various coherent emitters, so pulsars, neutron stars, and FRBs and LPTs, they seem to be incredibly similar, although on slightly different timescales. So the difference in timescales here, you can see some of them are in seconds, some of them are in milliseconds. And this could just represent diverse sizes of emission regions as well as plasma densities. So what we see overall here is that they all exhibit a combination of amorphous structure and sharp peaks, which drops down to the noise level in between them. And then you also have these occasional quasi-periodic micropulses in some cases. So this suggests that the plasma responsible for all these types of coherent bursts might share some physical traits which are then imprinted on the dynamic spectrum, even if the physical mechanism behind their creation might be completely different. So we know FRBs are these millisecond duration bursts. They are extragalactic cosmological. Some of them repeat, though we don't really have a real period. LPTs, on the other hand, they have durations of hundreds of milliseconds, seconds, or even minutes. They're all galactic and they have periods. What ties these two seemingly different phenomena together is that they're both coherent emitters involving compact objects, and they may share similar emission mechanisms. Maybe they are evolutionarily connected. Perhaps FRBs and LPTs share a common progenitor. Maybe these progenitors represent different stages or manifestations of the same underlying population. For example, if FRBs are produced by magnetars and if some LPTs are also produced by magnetars, then it's quite possible that they share a common progenitor or some manifestation of it. So far, all the confirmed LPTs are completely galactic. So if we ever detect an extragalactic LPT-like object that also emits short FRB-like pulses, it would be a smoking gun for a link. So in summary, FRBs and LPTs may seem like separate phenomena, but their shared characteristics suggest that they could be connected, either perhaps even part of an evolutionary sequence involving magnetars or other compact objects. By studying them together, we can begin to trace coherent radio emission, how it evolves over time and in different environments. Now, this will not only help us narrow down possible progenitor models, but it also pushes us towards a more unified understanding of how nature can produce such coherent radio signals across a wide range of timescales. Thank you.
All right. If you have questions for Manisha, please put them in Slack. Our next speaker is going to be speaking online. That's Jun Chan. And I'm assuming our AV expert can take care of that. So Jun is going to be talking about long period galactic radio transients, specifically from the Mirror Trap project. And I assume you can hear us, Jun?
Yes, I can hear. Yeah.
All right, that's a good sign.
In which case, just share your screen and go ahead.
Yeah, I will share my screen. Yeah.
And Jun, I'll let you know when you have minutes.
Okay, can you see my screen?
Yes, indeed.
Okay, cool. Hello everyone. My name is Jun Tian, and I'm a postdoc from University of Manchester. Today, I'm going to talk about some galactic radio transients discovered by Mirror Trap. Okay, so first, can we move the? Okay. So here is the mirror trap system as already introduced by Kostu. Mirror trap is a real-time transient detection system that use meerkats to search for galactic and extragalactic radio transients. We use 3 observing bands from 500 megahertz to 2.2 almost 3 gigahertz, and we can achieve a time resolution of 300 microseconds. We use 2 observing modes to search for radio transients. One is incoherent mode, and the other one is coherent mode. While incoherent mode, it can have a much wider field of view. The sensitivity of incoherent mode is worse than the coherent mode. So this real-time detection pipeline, when it detects a radio transient, we have a transient buffer system. We will save the voltage data of these transient candidates so that we can image and localize the source to arc-second precision. So far, the mirror trap, we have already discovered 109 galactic transient sources. Here is a distribution of the DM value of these sources. The orange color, it represents the mirror trap sources. As you can see, the DM value of our sources, it span from around a few DM units to a few hundreds DM units. Here is a plot to show the distribution of the period of the mirror trap transient sources. So as indicated by the orange color, so the mirror trap sources, the period, it range from most of them, they have the period larger than 1 second. So this is basically a gap between the pulsar population and the long period transients. Here is some discovery pulses that we have found for the mirror trap sources. Most of these galactic transient sources, they have a very simple single pulse profile, but a few of them do show some subcomponents. Okay. So as I already mentioned, when we detected a transient source, we can save the voltage data and use them to make image of the source. Here I just showed a few examples of the images we created for a few galactic sources. In each figure, the left panel shows the image before we detected the source, and the right panel shows the image for when we detected the source. So we can clearly see the transient source in the image. That's how we localize them to arc-second precision. Apart from imaging localization, we can also use the arrival times of single pulses to obtain a timing model for some of the sources. This only applies to very active galactic sources because we need lots of GOAs to make to fit the timing model. Here, I show 5 sources that we can get the timing solution. The left panel shows the timing residue. For these sources, the timing residue after fitting a timing model is consistent with 0, but for the first source MTP14 and the third source MTP20, we can say the timing residue shows a bandit feature. This is because the pulses of these 2 sources, they have some subcomponents. Apart from the timing residue, we for some of the mirror trap sources, we observe a microstructure. This microstructure is very common in radio pulsars. The left plot shows the microstructure for a 1.8 second source. So we observe a 2.5 millisecond microstructure. The right plot shows a 4.8 second source, and we can see 8.4 minutes seconds microstructure. These two sources, the observed microstructure is agrees well with the empirical relation between period and the microstructure timescale. So after because the mirror trap, we only use the real-time detection pipeline, so we cannot have continuous observation of the source. So after the detection by mirror trap, we also scheduled a follow-up observation with Effelsberg. We used the Effelsberg ultra wideband receiver to observe a few of these mirror trap sources, and we found persistent emission in 6 of these sources. Especially for the second source, we confirm that this source has a period of 17.5 seconds. So this means it's a long period pulsar, and it can potentially bridge the pulsar population and the long period transient. Okay. Here it's a plot to show the duty cycle of these 6 sources compared with the pulsar population and the long period transients. Here the 6 red stars, it represents the 6 mirror trap sources we have detected in Effelsberg follow-up. And the gray dots, it represents the pulsar population. As we can see, the duty cycle of the 6 sources we found is consistent with the general trends as can be seen in the pulsar population. But it's clearly different from the long period transient. Okay. Among the mirror trap sources, a few of them show very interesting features. So this is this source MTP27 is a very intermittent source. It's only detected once over 3 years. Here, the left plot shows the pulse profile that we detected from this source. The top panel shows the folded profile, and the bottom 6 panels shows the single pulses. The right panel shows the images of this source that we use to localize the source. Another source is an MTP96. It's an X-ray isolated neutron star in a coronal nebula. So this source is found by a mirror trap by accident, and we detected a single bright pulse from this source, and then we localized this source, and its position is coincident with an X-ray neutron star that's discovered by XMM Newton, and it's already published by Costu. So here is a summary of my talk. Mirror trap is already discovered 100 underlying galactic transient sources, most of which are likely to be RRADs. And we localize some of these sources in the image domain to arcsecond precision. Some of these sources are found to be long period pulsars with sparse bright pulses. So we are still finding new galactic transients over the sky, and some of them are showing interesting features. That's my talk.
Thanks, June, and thanks for keeping the time. It looks like we have a talk or a question up here from Adam.
Thank you. That was a really good talk. Adam Dong from NRAO. My question is, it seems like are you timing your sources with single pulses from the rats? And if so, how are you getting your TOAs?
You mean here? So
yeah, they're single pulses?
Yes. So for the single pulses, we use the brightest pulse to first measure the DM value of the source. Then we apply the DM value to every pulse to measure the arrival time.
Yeah, okay.
Yeah, but we here we use the signal to noise maximizing DM.
We have time for one more question if there is one. As the next speaker trots down. No? Oh, we have one up here. Yeah. Don't forget to introduce yourself.
Okay, this is Monkey from McGill University. I have a question. Yeah, just a follow-up question. So, when you get a TOA, what I saw some of the TOA because there are two peaks in the post profile. So why there's a TOA that goes to like one of the posts? Is that does the post profile changes over time so that one of the peak appears time of the observation, or it just
yes.
something
So I
else?
think for these two sources, because like there are two components in the pulse profile, so the brightness of these two components is changed with time. So for some of the pulses, I measure the TOA of the first component, but for other pulses, I measure the TOA of the second component. That's why it shows the banded residues.
Ah, okay, sounds good. Thank you.
All right, great. Thank you very much again. Let's thank June again. And just in case you were wondering if any of the speakers are going to be live, we have Adam Dong now, who is going to be talking about his work with Chime.
Oops. Hello. Is this working? Hello? Hello? All yours? Okay. Okay, hello everyone. It's wonderful being here. My name's Adam. I'm from the Green Bank Observatory, so I work at NRAO and I'm a Jansky Fellow there. So for this talk, I'm going to be talking about some of the work we're doing with Chime with these LPTs. Okay, so what have we been doing up until now? Well, like Meertrap, we've been finding galactic pulsars. This is actually the point of our survey, to find galactic pulsars via the single pulsars. And we're just accidentally finding LPTs. What a wonderful accident to have. So for a dedicated survey on LPTs or things that are similar, I'd like to refer you to Jeff's talk later on. So just a plug, because this is actually, what I work on most of my time, is that we're finding a lot of new pulsars. There's actually about 111 of them. Okay, so what types of LPTs are we biased towards? For now, before Jeff's survey real-time flow comes online fully, is that they sort of unnecessarily spiky and they have this quasi-periodic pattern. And that's because we're a survey that's specialized to detect FRBs. And so it has to look like an FRB at some point of its burst. So, our detection pipelines are biased towards these, and also they have to be dispersed. So they can't be these long things where it's hard to tell the dispersion measure, because we have phased array beams. We're not imaging. What that means is that it's really difficult to tell the difference between something that's long and RFI. But what we can do is we can monitor these things every day, because the sky passes overhead of Chime every day. And so even if they're very sporadic, we can get daily cadence on the monitoring. And hooray, you've heard this many times today, in the future, or in the very near future, we're going to be able to do
outrigger localization. So we'll hopefully be able to report them to milli-arc-second localization in the future, okay? And so this is sort of the idea of the types of bursts that we are detecting. Okay, so let me just start with the first source. I'm going to talk about two of them. 1634 plus 44. So some of you might have seen this drop on archive earlier this week. It's got about a 14-minute period, but it's also got a secondary period of 5 times the 14 minutes at 4,206 seconds. So we think this might be in some way due to binary activity. And to do these to make these detections, we have had observations with the VLA, and so shout out to Casey Law, who coordinated with us near Christmas, actually, with the real fast instrument. We have detections of the GBT. We have observations with Swift to try to constrain the high energy counterpart, but unfortunately, there's no detection there. And also, I just want to highlight that there's another paper, Blut et al., who independently discovered the source with LOFAR as well. Okay, so this is what the bursts from the source looks like. So you can see there's like quite clear, spiky magnetar, maybe like structure, and there's some quasi-period involved as well. Okay, so let's talk about this period weirdness. I said there's a secondary period at 4,000 seconds. So what is it? So most of the time the bursts arrive, you get one burst every 5 rotations, but sometimes you get 2 bursts every 5 rotations. So, and they're always separated by 0.4 of a phase. Statistically, this is very unlikely. So why would you say that this is a 841 second and not 4,000 second transient? It's because if you try to do timing, it just doesn't work. So Caitlin made this really, really nice imagery to sort of explain it. And so you see every star is a detection, and these stars, I should point with this. These stars here are all separated by 2 days. And 2 days is a beat period between 4,000 seconds and Chime's daily observation cadence. That's why they're separated by 2 days. This is what you would expect if the period was 4,000 seconds. But then what you see is that suddenly you detect them every day for a little while, okay? And so that, you get one exception to your theory and that sort of rules out your theory, right? Okay, and then so if you want to do this statistically and you say, okay, given an 800-second period, how likely is this to happen? It turns out very unlikely. Okay, I got to speed up. It's okay. So with the 800-second period, we can do pulsar timing. It turns out it prefers a negative period derivative. And that's, as a pulsar astronomer, this makes me very uncomfortable. I don't like it very much at all, but we've got to try to explain it. I just want to note that the LOFAR group sees this as well. So why would it be spinning up? So Iris is going to tell us later on that their source has a locked radio period to its orbit. So its orbit and its radio period is locked, which means that the pulses they're detecting are completely aligned with their orbit. So they're detecting the orbital period, basically. And what this means is that if we have a negative period derivative, if this source is in a similar case, then the orbit is actually shortening, is actually getting closer together. And so if the orbit is coming closer together, then that means it must need to release that energy somehow. And one way would be through gravitational wave radiation. And if that's the case, then it'll be in the LISA band, which would be pretty cool. But this is purely a speculation, and I'm not claiming that this is the case. So here, what I'm showing is the phase coherent timing residuals. And if you aren't familiar with looking at plots like this, what we're doing is we're saying, okay, the period's 800 seconds. We've got a period derivative. Let's subtract that from the model. How wrong are we predicting when the next pulse should arrive? You can see the next pulse, we can predict it to about 1%. Okay, the other funny thing is that the polarization is 100% circularly polarized. As we heard earlier today, there's not much that's 100% circularly polarized. And this has only been observed in FRBs and pulsars at these luminosities. So it's really bright as well. It's about 9 Janskys, about 3-ish to 4-ish kiloparsecs away. And this is work led by Casey. So this was one of the nicest photos I could find, Casey. It was nice. And so you can see in the VLA circularly polarized feeds, it's clearly in one image, but not in the other image. So it's very clear indication of that. Okay, so conclusions. Oh, sorry, there was one more other point. I should have mentioned this earlier, is that in the localization region, we find one potential white dwarf counterpart, optical counterpart, but we think the association is quite weak, so we're not really focusing on that. It's 100% circularly polarized, and from the luminosity, we think it might be a neutron star, although obviously if we find any optical in that way, it's probably more likely a white dwarf. But maybe it's a neutron star with a binary companion because of that secondary period I was talking about. From timing, it's spinning up, which means it could be accreting mass or emitting gravitational waves or something of that sort. Oops. And so that's all about this source. Okay, so I have 3 minutes or so to tell you about the second one. The second one I actually put in archive in 2024, but it was never published, and I just wanted to let you guys know there was nothing wrong with the paper. I had this little thing called a PhD thesis to write. So that was the reason that, now we've resubmitted it finally after the review. So this is what the pulses look like. But the good thing about waiting for so long, or about writing a PhD thesis, apart from getting a doctorate, is that we have new data now. And now we have baseband localization. And with that, we get polarization analysis as well. And so before, we had to fit the RA index. So we had to fit the positions in our timing. Now we don't because of Caitlin. So we no longer have to fit that, which gives us a lot more confidence in our timing solution. It's relatively close by, and we know that from the dispersion measure. It's about 100 parsecs, plus 310 minus 100 at 95%. This might be biased a bit low, I have to admit. And these are the people who led the new analysis that's going into our new paper that's going to be that's submitted. Okay, so this is what the timing solution looks like. And what I'm showing you first is the timing solution. And actually, our timing solution prefers a glitch in the model. Okay, so for those who don't know pulsar timing very well, a glitch is a rapid spin up of the rotation period. And when you do that, you assume this is a neutron star. It might not be, but if you do that assumption, you infer a magnetic field of about 10 to the 15 Gauss. Thank you, which is a magnetar-like field. Okay, so these are the residuals. You can see on the right, your right? Yes, your right. It's the no glitch residuals, and on the left is the glitch residuals. The no glitch residuals has all the structure in it, because you don't want that for pulsar timing. And there's other reasons as well, but I'm running out of time, so I won't talk about it. But the glitch timing solution just works a lot better. Okay, so for the polarization analysis, it's really juicy. Along this line of sight, we have a really high detection of rotation measure. And there's no clear indication of structure along this line of sight. So we think this is a very dense magneto-ionic material in the vicinity of the neutron star. And we can place a lower limit of 20 microgauss along this line of sight. And so if you plot this against all the other neutron stars with DM on the bottom axis, so you're comparing the DM and the RM, all the neutron stars lie there, and our source just is clearly on top of all of that. And that's all enabled because of one baseband detection. So that's really incredible. Okay, so conclusions for this source: baseband localizes it to 1 arc minute. Timing analysis prefers a glitch, and with that you get a high inferred magnetic field. And so because of that glitch, we assume it's got a neutron star origin. No glitch gives spin up. I told you how that makes me feel uncomfortable already. And the polarization analysis shows that the RM implies that there's a dense local magneto-ionic conditions. Oops, that's my thing. So in conclusion, CHIME FRB is poised to find these things. and they're very quite interesting. So I think over the next few years, we're going to be finding quite a few more of these, and I'm very excited for that to happen. Thank you.
Great talk. Yeah. Oh, right there.
Yeah, and online. So my question, Lauren Rhodes from McGill. I had a question about your first source. So you said you had Swift observations?
Yeah.
Yeah. So can the X-ray upper limits you get, can you use those to actually rule out the presence of accretion in the system?
Let me think. Can we use it to rule out accretion? We can use it to rule out some X-ray binaries.
Okay.
So
Do
in that way, yes.
distance?
From DM, it's about 3 to 4 kiloparsecs away. So it's
Okay.
it's pretty distant.
It's pretty close.
Yeah.
Yeah.
Oh, it's pretty close. I was gonna say it's pretty far.
No, it's pretty close. If it was an X-ray,
Different
then it's
perspective.
Cool, thanks. And then so there's a couple of online questions. The first one someone's written in the chat. This is from Pranav from MPIFR in Bonn. Do you have plans to follow up the sources with telescopes like GBT or the Broadband receiver on Effelsberg? Do you see any anomalous single pulses in the sample?
So let me answer the last question first. Every pulse is anomalous. They all look different. So and yeah, we are following it up. So I think we're putting in a GMRT proposal. We haven't decided on whether we're doing a GPT proposal, but every day we get chime follow-up for timing and extended, and also outrigger triggers as well. So yeah.
We have someone who wants to ask a question on that. Sorry? Yeah, okay, we will go to Marcus then.
Hi, Marcus Lower from Swinburne University. Very cool results. With your timing, have you been able to rule out that you're not completely dominated by single pulse jitter causing the spin up and your apparent glitch?
Yeah, so I have some slides for this. So jitter, right? Not our yeah, okay. So okay. So yes, admittedly it could be single pulse jitter for the glitch, right? Like pulse jitter can form structures like we're seeing here. But if you just assume that it's there's no glitch, you get spin up and significant spin up as well. And you might think that's okay. In the other source, I actually really tried really hard to get rid of that spin up and I couldn't. So maybe it's okay to have spin up, but I think there's no indication it's a binary. So why would it be spinning up is the question. I feel like that's more implausible than a glitch.
Right, I think we'll have to leave it at that.
We can talk about it.
Yeah. All right, let's thank Adam again. And then we will move to an online talk by Iris de Ruiter. Can you hear us, Iris?
Yes, I can hear you. Hopefully you can hear me too, and you can.
Yeah, we can hear you, and we can
see this.
And I'll let you know when you have 2 minutes.
Perfect. All right, just getting some Zoom screens out of the way. Yeah, so I want to start out by thanking the organizers for organizing such an excellent hybrid conference that has been really enjoyable to attend online. So my name is Iris de Ruiter. I'm an OSGraph postdoctoral researcher at the University of Sydney, but luckily I'm joining from a more favorable European time zone at the moment. And today I want to talk about yet another LPT that we found with LOFAR, which we show is a white dwarf binary system. So, yeah. I want to spend one slide on how we actually found this source, which is basically the majority of my PhD work. So I worked on image domain transient searches with LOFAR. LOFAR is the low frequency array consisting of dipoles placed all over the Netherlands and all over Europe that work together as a radio interferometer. And piggybacking off the LOFAR survey, we're able to do high time resolution imaging. So basically making these 8-second snapshots that allow us to search for these types of transients as shown in this GIF here. So if you have any questions about how we actually do this, about any details, I'm happy to talk about it. But for the purposes of this talk, I'll just skip straight to one of the results, which is actually this source you see in the GIF here. So that source is ILT-J1101, which we describe in detail in this paper here, which has a lot of amazing multi-wavelength collaborators. Here on the left, I show the light curves of the radio pulses that we found. In blue, you see the actual detections. In gray, we have non-detections. And here, the bursts have been folded with a 125-minute period. So some more details on these radio pulses. For that, I'll zoom in on this brightest pulse highlighted in the navy, in the slightly darker blue. So going to slightly higher time resolution, which we can only do for this burst since it's really, really bright, we get this 1-second light curve, and we can also make a dynamic spectrum. Some of the measurements we can do are a moderate RM and DM, consistent with galactic contributions in the directions of ILT-J1101. We can see already straight from the dynamic spectrum that this source has a very steep spectral index. So it's much, much brighter at lower frequencies. And also we find that this burst has a moderate linear polarization of around 50%. And we find no evidence for circular polarization. All right, so that's great. We found an LPT and the first one with LOFAR actually. But the next step is actually trying to figure out what this is. So to do that, we look into multi-wavelength archives. And actually what's really quite helpful for this source is that it's quite far off the galactic plane. So a lot of these LPTs have been found towards the galactic plane, as Manisha also showed, which really complicates follow-up at other wavelengths. So in our case, the LOFAR source, ILT-J1101, is indicated with this green cross here. And it really overlaps very well with this faint red optical source, which turns out to be an M dwarf at a Gaia distance of roughly 500 parsec. Now we know of M dwarfs that flare in the radio. Most radio stars are M dwarfs. However, the properties I just described in terms of polarization and also mainly luminosity really don't fit with a stellar flare scenario. So we try to dig a bit deeper. And we do some spectroscopic measurements of this M dwarf. So what I show here is the radial velocity of the M dwarf as a function of time. And this is measured with 2 different instruments. I show the measurements in black and gray here. And you can see that clearly this M dwarf is moving back and forth, indicating some binary motion. And we can fit this behavior really well with the simple sinusoid. And what's really cool about this result is that the orbital period, so the period of this sinusoid, is again very, very close to the period that we found for the radio pulses. So this shows that really this radio flaring period is related to the orbital period of the binary. So now we know that this M dwarf is in a binary with something. Well, sort of gave away what the other constituent of the binary is in the title of my talk, but how did we figure that out? So what we did is we looked at archival photometry. So here I show the SDSS and 2MAS data points, and we tried to fit that with an M dwarf model, which doesn't work too well, as you can see in the residuals here. But if we allow for a secondary component, and we allow that component to be a white dwarf, we get really a perfect fit. And even despite allowing for more degrees of freedom, this is a statistically significantly better fit. So where does that leave us for ILT-J1101? Well, we've now confirmed that it's an M dwarf white dwarf binary, producing bright coherent radio pulses at the orbital period. And especially this last part, it was quite a key finding at the time, because a lot of people mainly focused on this LPT period coming from the rotation period of a single object, or a spin period. But it turns out that these long periods can also be linked to orbital periods. And more broadly, we now know that a subset of long period radio transients are white dwarf binaries, because next to this LOFAR source I just described in detail, we now know of a source that was found with the MWA, GLEAMX J0704, which shows really similar properties to the LOFAR source. It shows radio flares as a 2.9-hour period, and the binary constituents are also really very similar to what was found for ILT J1101. So last week, this part of my talk would sort of been where I stopped, but given the very rapid developments in this field, and also given Adam's talk just now, I've included yet another slide about maybe the binary scenario in LPTs more broadly. Because the source that Adam just described in the first half of his talk, that was co-discovered with LOFAR, also shows clear indications for binarity with these very interesting potentially orbital resonances in the timing solution. And just, I think, yesterday or 2 days ago at the National Australian Astronomy meeting, there was a very interesting talk showing that the best studied LPT, GPM J1839, can also be modeled really well with the binary scenario. So that's really awesome, very recent developments. All right. Oh yeah, I want to zoom out one step further, because how do these white dwarf LPTs fit into maybe a broader population of so-called white dwarf pulsars, or magnetic CVs in general? So to sort of describe this, I took this picture from this paper by Schreiber et al., which tries to model why we see many more magnetic white dwarfs in binaries compared to single or isolated magnetic white dwarfs. Because this suggests that the magnetic field of the white dwarf comes from the fact that it's in a binary. So without going into too much detail, here in stage 4 is when the white dwarf has actually become magnetic. And in the Schreiber paper, this is actually already called the ARSCO stage. So just as a reminder, ARSCO and J1912 are two other systems where we see variability, but across the spectrum from radio to X-rays. And we see radio flares for these two systems with periods of 4 or 5 minutes. And that period is thought to be linked to the spin period of the white dwarf. So in this stage 4, the white dwarf is still relatively rapidly spinning. However, the magnetic field starts to connect to the magnetic field of the companion. And over this stage 5, this interaction implies that the white dwarf spin starts to synchronize with the orbital period of the system. And finally, you arrive in stage 6, which is called the polar stage, where the white dwarf spin and orbital period have synchronized. And this stage really fits perfectly with these ILT J11 and GLEAMX LPTs that I just described. So I just wanted to put these sources on one of these evolutionary pathways, because I think it's helpful in how we interpret them. And also, I want to highlight that it's really cool that we're starting to find these sources from different wavelengths, basically. So these two sources down here have really been identified in the radio. However, these two sources up here were identified because they were highly variable in the optical. And then in follow-up, we determined that they showed radio flares as well.
Keep this about 2 minutes, please.
Yes, perfect. Because most of what I was planning to say, I think Manisha already mentioned. So I wanted to zoom out and also show this transient phase space a bit again to really highlight the connection between LPTs and FRBs. But Manisha did that in a lot of detail. So I'll just show the zoomed in version, which is, I guess, a bit more updated, but already out of date again. So In the black box, again, are the LPTs. And I think just this figure already sort of captures why probably there are multiple source populations within this LPT class, because you can really see that these sources range all the way from the pulsars to the magnetic white dwarf binaries. So yeah, I just wanted to show that and highlight yet another reason why probably there are multiple LPT source classes. And another thing I wanted to say, and I took exactly the same example that Manisha showed, but I just wanted to mention that we're now starting to get into the phase where we can do really detailed studies of these LPTs. So the past few years we've been really finding a lot of them, but now I think we're moving towards a domain where we can really do detailed spectropolarimetry as well to really look for detailed physical interpretations of emission mechanisms and also really start to draw these connections to pulsars and FRBs. So just to conclude, magnetic white dwarf binaries can produce bright coherent radio emission, with some very similar properties of more pulsar-like LPTs. Some LPT properties are very similar to fast radio burst. I haven't been able to show that in detail, but in terms of polarization properties and spectral properties. And I think LPTs might, for the FRB community, offer an opportunity to study some of these potentially joint emission mechanisms a bit closer to home and also study the local environments in more detail. And yeah, the main question that remains, which I guess is similar to one of the main questions for FRBs, is how do these systems, both in a binary or in an isolated system, how do LPTs produce this bright coherent radio emission? All right, I'll leave it there. Thank you.
Great. We have time for certainly one, maybe two questions. You can see you have your laptop in front of you, so.
Thanks. Yeah, this is a great talk. This is Miles Sherman from Caltech. I was wondering if you have I guess a preference for whether or not other LPTs that don't show optical counterparts, are they at different stages of this evolutionary cycle of, say, a white dwarf binary, or do you think it's more likely that it's a completely different source, like a neutron star binary?
Right. Well, for some sources, I guess for most of them, we don't really have the timeline yet to do this more intricate to fit more intricate timing models. But for some sources, there's definitely indication for, I mean, for example, for the source that Adam just presented, if there is really accretion happening, which could be happening in the polar stage here, you could get a decreased orbital period. There's also other systems where we see intermittency. So we see the pulses very regularly at a certain period, then they disappear for a while, and then we start seeing them again. That might also be an orbital resonance effect. Yeah.
Thanks, Iris. That's all we have time for. So let's thank Iris again.
Yep, thank you.
Our next speaker is Yiteng Wang, and is it pre-recorded or is it?
I'll give online.
Okay, great.
Yeah, let me just share my screen.
We can hear you okay. I assume that you can hear us okay.
Yeah. Can you see my screen? All right.
Great. And I'll let you know when you have 2 minutes.
All right, cool. So good morning, afternoon, and evening, everyone. My name is Andy. And today I'm going to talk about this bright long period radio transient SCAPG 1832, which is the first source, also shows X-ray position. So it's a bit cold in Perth now, so bear me if I made any mistake. So first, I would like to thank my co-authors for their contributions and support in making this discovery possible. So at the very beginning, I would just briefly introduce how the source was discovered. This source was discovered by actually 2 ASCAP surveys. The first survey is called the Variable and Slow Transit Survey, or what we call VAT survey. You can see the logo on the right. And VAS observes the galactic plane every 2 weeks for 12 minutes. And there are different ways finding interesting objects. You can construct light curves, you can search for circular polarization, and you can do fast imaging. And this G1832 was initially discovered with the circular polarization search because it is straightforward. And it was pretty bright when it was discovered. So even with a not so high circular polarization fraction, you can still see it in Stokes V images. And after the discovery, we also made the full Stokes dynamic spectra. And it is only about 2 minutes wide, and partially of it is circularly polarized, and most of the pulse is highly linearly polarized. So there should be a highly ordered magnetic field in the system. And the second survey is Craft, and you all should know it. And the subpulse structure was actually detected with Crackle. And by using the Crackle data, we find a DM of about 480 parsec per centimeters cube, which is at a distance around 5 kiloparsec. And the brightness, the bright pulse, and also the narrow structure imply a pretty high brightness temperature, about 10 to the power of 20 Kelvin, suggesting a coherent emission process in the play. But you cannot do too much things with just one pulse. So therefore, we perform like heaps of observations with telescope all around the world. And we detected multiple pulses, and we measured a period of 44 minutes. So that confirming it belongs to the LPT family. And if you zoom in those pulses, you can find they are pretty similar to previously discovered LPTs, steep radio spectrums, and also highly linearly polarized emission. And also, if you see the SD, it is so perfect to be true. And it also has very morphology, both the whole envelope and also the stop pulse structure. We have no idea about it. If you have any comments on it, please let me know. And also the polarization angle is relatively flat at both high time resolution and low time resolution. And we also did periodic search within the pulse, but we found nothing. So this suggests likely there is no fast spinning object in the system, but there is still possibility that under some fine tuning geometry or something like that, there's still something rotating pretty fast. We also did like this subarray observation with Meerkat and GMRT, which means you can observe over a pretty wide frequency range. And contrast to some known LPTs and some repeating FRBs, the emission from 1832 is pretty wideband. It is from like low as like 300 megahertz to about like 1.5 gigahertz at one time. We also tried to time the source with pulses, but we got a lot of uncertainties on the TOAs due to the wide pulse morphology. So we saw some hints on the spin down, but we need more pulses to confirm or reject it. But it is obviously hard to understand the nature of the source solely based on the radio data or of the source itself. So you may want to zoom out to check the field or check the data at other frequency. So if you like stare at this beautiful image, you will notice some like extended emission like in red near the source. That is from a known supernova remnant, G22.7 minus 0.2, and 1832 is spatially coincident with that. However, it is a bit hard to confirm the association because the distance to the source is with a huge uncertainty. So we actually used two methods. The first one, you can always get a rough estimation based on the DM. However, the error can be as huge as 30%, and also different models will tell you different distances. And also, we have the H1 measurement, but that will only give you a logarithm, and also none of them are actually robust. So it is close to has the same distance, but the uncertainty is huge. We can also do VLBI, and we performed several VLBA observations last year, and we measure a relatively small value of the proper motion, and combining with the relatively large offset from the center makes this association unlikely. But at the end, if the source still radio bright and with enough data points, we can get the distance and also the proper motion, but it will take some time. And you can also see there are lots of other supernova remnant nearby, so which means like the chance coincidence is pretty high, which is about like 70%-ish. So combine all of that, I would say there is no strong evidence on the supernova remnant association. But if we have more clues, we may be say yes in the future. So now we need to go to some other frequencies. If you search V0, you will find that there is a Fermi source nearby, and its 95% eclipse right covers the source. So however, it has been already associated with a gamma ray binary nearby. So currently we don't consider its association with this source. So next part is infrared, similar to other LPTs. So because we know some LPTs can be explained by the white dwarf and M dwarf system. So if you can detect something in optical or infrared, it might tell you something. And thanks to the precise localization with VLBA, this helps us to avoid the crowded sources in the plane. We can confidently see that there is no clear counterpart in infrared. And the deep in the plane means severe extinction. So therefore, we can only exclude any main sequence star earlier than M0. So finally, we can go to X-ray. Despite extensive searches on previously discovered LPTs, nothing has been discovered in X-rays. So at the very beginnings, we didn't expect to see anything. And indeed, for most of the time, you can see on the top left figure, the source is X-ray quiet. The only detection comes from a private Chandra data, and it is not for the source. It was just scheduled at the right time. So you can see its X-ray luminosity seems to be correlated with a radio one, but again, we need more data to confirm this claim. The X-ray observation happens when the source was extremely bright in radio, about 20 Jansky at 900 megahertz. And we have 100 photons, so we can do timing. And we find that X-ray is also periodic, consistent with the radio period. And within the uncertain, we can see the radio emission and X-ray emission comes at the same phase. So likely they are produced at the same region. One another thing to notice is the phase between 0.5 and 0.75. There is no photon within that range. It could be just faint, or it could be totally nothing. And we did a rough calculation and find that eclipsing is a bit hard to explain it. However, 100 photons is not enough for a spectrum, especially when absorption is severe at a soft end. So we could potentially fit a particle or black body, but neither is informative. However, if you have 600 photons, it would be much easier to fit the spectrum, but we need to be very lucky for it being X-ray bright again. So X-ray detection actually gives us some hope, but not too much. We need more monitoring in both radio and X-rays, and we also need deep optical or infrared observations. So now let's just trying to interpret the observational data, but maybe sometimes a bit over-interpretation. So if you put this one with other neutron stars or specifically magnetars, you will see its low quiescent X-ray luminosity and low spin down luminosity will imply it is something old. So potentially an old magnetar can explain it. For this case, you need to find a way to explain its bright radio pulses. So as all other radio out magnetars are relatively young. And if you try to compare it with like other known transients, you will find it doesn't quite fit any known types of transients. And in this radio X report, even LPTs does not cluster together. Compared to those LPTs known to harbor a white dwarf, the radio luminosity of 1832 is way brighter than them. And
Andy,
also the port. Yep.
Andy, about 2 minutes, please.
Yeah. Okay. Cool. Also, the polarization properties are different. So, though I would admit that this may be wrong because we only have very few samples, but it could tell us something. But also, there could be more parameter space for us to explore, for example, spectral index, fractional polarization, and so on. But still, there are some questions. For example, like how long is long? Like is seconds, minutes, or hours? And what is a radio period? Is it orbital period, spin period, or precession period? And what can we know from this period? For example, if the period is too short, maybe it can stop the radio emission because of the accretion. And of course, like, are all the LPTs the same? Maybe probably not. And also, like, what is the relation between all these sources? Because like Manisha has already mentioned that in this plot, like there is lots of things on export, but if we can try to fill in the gaps, maybe it can tell us something. So to fully understand the nature of it, we need to try to find more, or we want to know more about the known sources. So like there are lots of different ways of finding more of them, but there are always pros and cons. So we will just keep working on that, especially like Andrew and I are working on some folding algorithm on the visibility, which perhaps will help us to find something more. And also with the lesson we learned from this object, we know that prompt multi-wavelength follow-up is very essential for LPTs, and we are just trying to observe as much more information as we can from the bright object, because maybe it will just turn off in the future. So that is end of my talk. And if you want to know more details, you can just read the paper. We will have another paper in preparation, just creating the folder. And if you have any questions or comments after the meeting, you can contact me via email or just DM me on the Slack.
Great, thanks, Andy. Very interesting. We have time for one or two questions. I'm sure there is one somewhere. Anyone? Oh, yeah, Kelvin. You don't have a laptop? Okay.
Hey, Andy, this is Calvin Leong from UC Berkeley. Great talk. I was wondering if you see, maybe zooming out a bit, any correlations between the binarity or the X-ray emission and the radio emission luminosities or properties of these long period radio transients?
We try to do that, but it's a bit hard because the sampling of the observation are pretty sporadic. So like we are trying to find out if there is a longer periodicity of what you said, like potential binary systems, but currently we didn't find any evidence on that.
Okay, thank you.
All right, so I think we're gonna have to move on. So the final speaker of our session will also be speaking online. Great, you can hear us, I assume?
Yes.
Great,
Is my
so our
sound
final,
loud and clear?
yeah, we can hear you clearly.
Okay.
Bit of feedback, but that's gone now. Okay, and our last speaker is Ali Jinsali. Please take it away. I'll let you know when you have 2 minutes.
Okay, thank you. My name is Ali Arda Gençeli. I'm a postdoctoral research fellow at Sabancı University working with Ünal Ertan and Ali Alpar. Today I'm gonna give a talk about the long-term evolutions of long-period radio transients with fallback disks. So previous talks are summarize the properties of LPTs very well. That's why I'm not gonna give another introduction to them. Also, most of the sources are shown in the period and period derivative diagram today. That's why I'm also gonna skip that part. What I would like to mention is that we have already studied these three sources using the fallback disk model and successfully reproduced the rotational properties of these sources consistent with the upper limits on their X-ray luminosities or period derivatives. Today, mostly I would like to focus on the newly discovered source, which exhibit an active state in both X-ray and radio bands. But first, let me give some introduction to the fallback disk model, which is first proposed by Terce to explain the observed period clusterings and X-ray luminosities of anomalous X-ray pulsars. Then Ali Alpar states that if you include the disk properties as an initial condition, the model also could explain the observed properties of other young neutron star populations. In the model, we solved the disk diffusion equation using the alpha prescription to determine the mass accretion rate in the disk. In this way, we can calculate the inner disk radius and the torques. The model also includes the X-ray irradiation of the disk, contribution of the cooling luminosity into the irradiation, and inactivation of the disk at low temperature, which extends the lifetime of the disk. For the inner disk radius and torque calculations, we used the analytical torque model developed by Ertan in 2021. We use this very complex formula to determine the inner disk radius. What is important here is it depends on the spin period of the source as well, compared to the conventional inner disk radius calculations, for instance, Alphen radius. And for the rotational phases, if this inner disk radius is greater than 1.26 arc rotation, where the inner disk, where the field lines can accelerate the matter at the inner disk to speeds greater than the escape velocity. In this case, the matter can be expelled out of the system. There is no mass accretion onto the star in this phase. And pulsed radio emission is allowed if the source has enough rotational power. The source of the X-rays will be the cooling luminosity. We use the Page cooling luminosities. And the most dominant torque will be the disk torques arising from the disk field interaction. If the inner disk is less than 1.26 arc rotation, the matter cannot reach the escape velocity, then will fall back to the disk again, which will cause a pileup in the disk, which will push the inner disk further in until it becomes equal to the arc rotation, which will initiate the mass accretion to the star. In this case, ordinary radio pulses are expected to be quenched due to the mass accretion. Total luminosity will be accretion luminosity plus the cooling. There will be a spin-up contribution coming from the mass accretion. Total torque and all the torques will be active in this state, but the most dominant torque will be disk torque again. Those are some early results for anomalous X-ray pulsars and soft gamma ray repeaters, which is published before the discovery of LPTs. What we are seeing here is the evolution of the X-ray luminosity period, spin period, and spin period derivatives. And sources evolving with fallback disk with conventional fields, which I mean fields around 10 to the 13 and 12 Gauss at the pole, can achieve the rotational properties and X-ray luminosities simultaneously at ages around 10 to the 3, 10 to the 4 years. Then sources continues to evolve towards the periods observed from the LPTs. After this first discovery of the LPT, which is the first source with the spin period of 1091 seconds, we applied the same model with the disk parameters similar to those applied earlier and which are not very important actually. What is important here is the magnetic field strength, also the initial spin period and the mass of the disk does not significantly affect the evolution of the source. Here again, we are seeing the evolution of the X-ray luminosity, spin period, and period derivative with respect to time. And source properties can be achieved in both phases, either the weak propeller phase or the strong propeller phase, depending on the magnetic field strength. And our results are consistent with the upper limit on the X-ray luminosity and the period derivative. Then the second source put a constraint with the observed measured spin period derivative. The source property is only achieved in the strong propeller phase for this source, with similar disk parameters and initial conditions again. Then more recent work, we show that for different initial conditions, we are not just achieving the rotational properties of LPTs, but we are also can show the rotational evolution of all the isolated neutron star populations in a single picture and the evolutionary links between these populations. So as you can see, most of LPTs starting their evolution as a high magnetic field radio pulsars. Then during the big propeller phase, we can see them as AXPXers. Then they become LPTs. And I would like to give the solutions for the most recent discovered source. The spin period and period derivatives gives a rotational power much less than the observed radioluminosity. Also, archival data put some upper limits to the both X-ray and the radioluminosity. And observations, the absence of an optical counterpart supports the possibility of a compact neutron star rather than a white dwarf system for this source. So we can apply the fallback disk model to this source as well. These properties should be sustained as we saw in the previous applications. And the source properties can be sustained again for this source, in both weak propeller and the strong propeller phases, consistently with the upper limits, with magnetic fields around 4 to 8, 10 to the 12 Gauss. But again, with this model, rotational properties can be easily achieved. What is important is, I think, the short-term X-rays and radio enhancement. What could be the reason for that within the same model? So this is the recent activation of the source. Archival data indicate that source is activated only recently and shows high variability in both X-ray and radio luminosities during this active state. If these sources are evolving with disk, some instabilities in the disk could occasionally increase the mass accretion rate in the disk, which will increase the accretion rate, which can explain the increase in the X-ray luminosity. Also, increasing m dot in will decrease the inner disk radius, which will open more field lines, which will increase the flux of the open field lines at the pole, which can enhance the radioluminosity and can explain the observed radioluminosity. So if you want to quantify these values, you can use the Puff-Ray model to do that. And the rotational power can be enhanced with this ratio.
3 minutes, please.
Okay. And the magnetic field strength found in the model is placed to the rotational power formula, which gives a very low value. If the inner disk radius is at the arc rotation, you can enhance the values to these values, and inner disk can penetrate further in, which will enhances more the rotational power. Actually, I was not gonna show this plot, but because of the Adams talk, I wanted to add it. Because when the accretion rate increases, inner disk will enters from the arc rotation and takes the system to spin up. So we can expect some of the sources can show spin-ups during these states. And these inner disk radiuses are calculated for steady accretion. And I would like to compare the rotational powers with the observed radioluminosities as well. But the given values are mostly assumed with the isotropic emission. But for better comparison, we need to consider the opening angle, so the solid angles, so beaming effects and the duty cycles should be considered as well, which can lower the observed luminosity. And now we can compare the rotational power and the radioluminosities, which are greater than the observed luminosities, as you can see from this slide. And the enhancement in the radioluminosity can be sustained by the enhancement in the mass accretion rate due to some instabilities in the disk. So as conclusion, we can explain the long-term evolution and the short-term observed phenomenon within the same model, and similar mechanisms could be operating in ARATs and other LPTs as well for lower m.dot in values. So if the m.dot values are low, which means we are not gonna see the X-ray emissions from each source. So thank you for listening. So you can ask any question if you want.
Hey, thank you very much. It's nice to see this kind of modeling, and we have time for one question.
Hi, Vicky Caspi from McGill. So at the time that fallback disk models were proposed for anomalous X-ray pulsars, the models predicted correlations between the torque as measured by period variations and the X-ray luminosity, and also made predictions for infrared emission, which were later shown to be not valid by the very, very high pulse fractions in the infrared for some AXPs, for example, 4U01 42+61. And so I'm wondering, I guess here for LPTs, we might not see torque variations that you could test, but do you have predictions for the infrared fluxes and potential pulse fractions?
I don't have any predictions at the moment for the infrared part, but the inner disk radiuses is very at the very outer disk. So as you can see, the light cylinder radius is around 10 to the 13 centimeter for this source, and arc rotation is around 10 to the 10 centimeter. So the disk is very cold at these radiuses. So I'm not sure we can detect them or not.
Okay, thank you.
You're welcome.
Great. So this concludes the session. Let's thank Ali and all of the speakers of this session again. So importantly, everyone should come down to the front so that we can take a group picture. And as you are, I think, so Matt, there's also a chord collaboration meeting at TSI during lunch, right? In TSI. Yeah, okay. Oh, sorry.
That's probably the very thing.
Zoom though. Yeah, I don't know how to increase the
The grid. Some of us are in it twice.
I don't know what. I go for a second.
Or online, assuming you can still hear me, can you please turn on your cameras? Then you can be in the picture. So Caitlin and Marta and Swali. Oh, Caitlin, how can you be in two places at once? How is this possible? Okay, great. Yeah, so we can see everyone online now.
So we were 2 times. That's right. There. Special consequence. At the same time. It'd be worse if we were on the bottom than we'd be in it. Yeah, and then in friend
See, many of you smiling when the other half is not, that's all pretend. 10 seconds that you're enjoying yourself.
Not bad. Can the Zoom people hear also?
And they what?
They can hear.
We have a communicator. We have a communicator.
Take a few. Ready? 1, 2, 3. One, two, three. Right there, giving it. Because for Instagram, you Three. Okay, I think we got some. Oh.
Yeah, and George, we just put the audio on here, so anytime you're ready, you can go right ahead.
Okay, great. Can you hear me?
Yes, we hear you clearly.
All right, wonderful. Okay, I cannot see my. Can you see my cursor on the screen?
No, we don't see your cursor. We do see your slides.
That's okay. That's fine. All right. Okay, yeah, thanks everyone. Thanks for the invite to give this talk on the magnetars and the FRB connection. So we're starting a new session. And this session will be kind of devoted to really digging deep into the magnetar class and their FRB connections. So my talk is going to be a little bit of an overview. Yeah, again, thanks. I'm learning a lot from this great conference, and I'm very envious of all of you radio astronomers for all of the great discoveries you're making. We're only trying to catch up. So I'm a high energy astronomer. I am based at NASA Goddard, so this is going to be biased towards X-rays and a little bit of gamma rays. Okay, so you've seen some variations of this. Of course, when we talk about pulsars and magnetars, this is the first thing that we show. This is the famous BP dot diagram. And very immediately, it kind of comes to you that there are separate classes in this population of neutron stars. So what we are interested in today is the population that is on the top right. These are what we call magnetars. So they have, classically speaking, periods between like 1 and 10 to a little bit over 10 seconds. They have large spin down rates, and if we assume magnetic dipole breaking, this translates to dipole fields that are 10 to the 14 Gauss on average, and young spin down ages of the order of a few kilo years to a few tens of kilo years, again on average, with quite a bit of spread. Their spin down luminosity is also on the lowish side. But the more interesting element is that, as I will show in a second, this E dot cannot really explain their bright X-ray luminosities. So far, we've discovered about 25 to 30. This is a little bit maybe outdated, the 25 number. So we have about 30 discovered magnetars. They all reside close to the plane, so that gives you an idea of their or a confirmation of their young ages. Also, some of them are within centrally located within X-ray bright supernova remnants. Again, a confirmation of their bright ages. So we haven't found a very convincing case for a magnetar in a binary. This is in contrast to, for instance, some of the models that are proposed for long period transients. But that's an interesting question. And as I said, they're bright X-ray emitters, typically stronger X-ray emitters than regular pulsars. They have hot surfaces with a temperature of about 0.5 keV, which is quite a bit larger than normal pulsars at similar ages. So this is kind of a distinction between the two. And of course, some of the magnetars are radio pulsars, radio loud pulsars, about 25% or so, 6 so far, if I'm not mistaken. And perhaps the most striking element of magnetars and something that separates them and what was used in the first place to basically establish the magnetar population is their variability. And they are varying over 10 decades in time scales and energy scales. So it's a staggering time domain type sources. All right, so here what I'm showing is basically the X-ray luminosity as a function of the spin down. The yellow line is a one-to-one relation, and the red dots and bars are basically for magnetars, and this is simply to establish that most of the magnetars, either in outburst or in quiescence, which is what the dot shows, they have X-ray luminosity larger than E dot. So you're going to have to go and find another energy source, and the most natural, obviously, is their B field. So you take from that magnetic energy flux and you kind of transform it or convert it into radiation. And that could be done through decay of fields, and that work has been done for a couple of decades now. That's of course different than the regular pulsars are shown in gray dots here. Of course, if you ask, for instance, how much energy does a magnetar pack, it could be quite a bit, varying between 10 to the 46, 10 to the 50, and that's not to say, at the early stages of their birth. So because of that, they have been kind of thrown into the mix of many different time domain transients, for instance, gamma ray bursts, superluminous supernova, ultraluminous X-ray sources, and of course, fast radio bursts. So they're very appealing to explain extreme phenomena because of that energy that they can pack. And of course, we're still kind of looking for the smoking gun evidence for many of these classes, but we know that in the case of fast radio bursts, as I will discuss later on, that has been, in a way established. Okay, so magnetar transient phenomenology. This is really kind of an overview again for the things that are of interest to this talk, and of course, basically what makes magnetars magnetars. So let's go through this. One of the, I would say, perhaps telltale signature of the case of a magnetar when in any type of source is if you detect what we call short bursts from that source. So these are typically on the order of 100 milliseconds to 200 milliseconds. They're SED peaks in the hard X-rays around 10 or 20 keV. Their spectrum is thermal, so it's kind of a fireball plasma emitting some energies. And they're bright. They can reach energies of about 10 to the 40 or 10 to the 41 if we're speaking in energy scale. And of course, that's quite bright for large field of view hard X-ray monitors to detect like Swift-Bat Fermi GBM. And this is how we in fact discover most of the magnetars. And these bursts could come in storms. So you could have, for instance, in this case, about 20 minutes or so, a little bit less, 200 bursts from the famous galactic magnetar 1935 plus 2154. So that was in towards the end or maybe April 2020. And this has been detected about 7 times so far since the, let's say, the mid 1980s or something, or maybe even earlier than that. So they're a little bit on the rare side to see the storms. At the time of these bursting activity, including the storms, what you see is that the X-ray emission from a magnetar increases, sometimes by as many as several orders of 2 to 3 orders of magnitude. And that's what we call outbursts. So basically you have the bursting activity and then you have the outbursts. The outburst evolves in a typical manner. It decays back to its quiescent state most of the time over the course of months to also a couple of years or so. And during that time, you have a lot of activity going on. On top of that, at the start of typically, for the ones that are continuously monitored, at the start of an outburst, you observe some sort of a timing anomaly. Typically, it's a glitch. And that kind of tells you that there's something connected between the internal and the external of the star that is kind of driving all of these interesting behavior. And of course, for several of the magnetars, as I mentioned before, some radio emission has been discovered. Typically, that's kind of concurrent to the X-ray activity, not simultaneous in a way. So on the lower left side, I'm showing the flux density from XEJ 1810, I believe. And you can see that it started quite a bright radio pulsar and then decayed towards quiescence several years after. So, and of course, this is not the only transient activity. I'm skipping over giant flares and a few other elements. So this is not the end of the story, but just to kind of give you a flavor of what's going on. Okay, so since the discovery of FRBs, of course, magnetar has been they were at the forefront of the kind of let's say the progenitor of FRBs, and you can kind of understand why. You can pack lots of energy in very small volumes, and you need that because FRBs were quite bright, and also their short time scales indicate that probably where the emission region is quite small, and so magnetars obviously are a natural explanation for FRBs. And of course, that kind of, let's say, was one of the perhaps, I don't know what people think about it, but since the discovery of FRB is one of the most important discoveries, in my opinion, was, of course, the FRB from the galactic magnetar SGR 1935 plus 2154. So this on the left, you are all familiar with what I'm showing. This is the chime double burst from the source that happened in April 2020. And of course, that kind of can, okay, you have the answer. Indeed, magnetars can produce FRB like emission. Maybe at the time it wasn't, it was at the tail end of the brightness, but you could see it to extragalactic distances. So if this was from whatever few megaparsecs, you would have seen it and you would call it an FRB. So you got your answer. But of course, that now allows you to perform more rigorous tests of a whole lot of other questions. So for instance, now you could, now knowing what the progenitor is, you can perhaps look deeper into the question of what is their triggering mechanism? What is the plasma properties at the time of the FRB emission? Is there any relation with the X-ray activity? What about the other magnetars? Are we just simply missing them because we're not observing them, or was there something special about this case? And of course, now that we know that they are correlated, you could basically go into asking the question of how they are related to extragalactic FRBs, both repeaters and non-repeaters. You could look at that question from a qualitative type of analysis. Well, maybe I shouldn't say qualitative, but basically what I mean is, are the polarization properties of FRBs, similar in a way to the polarization properties of some of these bursts that we've discovered from 1935 and other magnetars as well, of course. So you could look at it that way, and of course there's the population analysis, asking ourselves what we know about the magnetar population, what we know from that one single data point. Also, it's still a single data point, but it's something. What does that translate in terms of explaining the extragalactic FRB population? So many talks have already covered some of this, and also please stick around for the rest of the session. There's going to be, in fact, what I would argue the more interesting talks that I am simply kind of introducing the landscape for. So, all right. So some of the questions that I laid out were immediately answered. Some, an hour or two later. It was quite remarkable that in my opinion, that the radio burst occurred simultaneous to an X-ray burst. So this is, you hit two birds at the same time. So you, not only FRBs are connected, or FRB-like emission connected to magnetars, but they're also connected intimately to the X-ray activity. The X-ray activity has occurred since 1979, and so we've had time to study it a little bit. So that gives us, more constraint into what's happening in the magnetar environment, in order to kind of trigger FRBs and where they come from. So that was excellent. And of course, another element that we should always keep in mind is the fact that the FRB occurred perhaps, I believe, 13 hours after the massive and the largest burst storm that SGR 1935 has shown. So SGR 1935 was active for about 13 hours. You cannot see my cursor, but the middle panel over there, the very left, a tiny black bar, a zoom in of that is the bottom panel, and that's basically the burst storm. And then it calmed down quite a bit. So the burst storm, we've detected hundreds of bursts with NICER and with Fermi GBM and SwiftBat. None of them had shown any FRB, and then had, the FRB occurred just hours later, but the source had died down quite a bit. So what does that mean? Is it just simply coincidence? I don't know the answer to that, but that's something to keep in mind. So we had a lot of answers to that. And then, of course, once you had that beautiful bright X-ray burst, you could perform spectral analysis on the burst. And also, I'm not mentioning the temporal analysis, but you could perform spectral analysis on the burst and compare it to the rest of the bursting activity that occurred that day. And what we found, and others, of course, has found the same thing, is that spectrally, the FRB associated X-ray burst was a little bit harder. So let's say the SED extended to a larger range of energies, as you can see on the top panel over there. So the dashed line is a simulation of the FRB associated X-ray burst, and the other is an example, a very, let's say, normal, like basically most of the burst other than the FRB associated one showed that type of spectral behavior. So you see the difference hitting you in the eye. So what does that mean again, right? I'm not going to go into the details, but many people have thought about this heavily, and you've got plenty of references there to kind of refer to. And I'm sorry, I'm missing a lot, I know. Since that burst, of course, many radio bursts were detected from, well, define many, I guess. But several radio bursts were detected from SGR 1935 and its activation. It goes in and out of activation since 2014, since its discovery. But on the top, you will have basically the radio burst episodes that I have been able to collage or put together. And the green ones are the ones that have X-ray associated bursting activity as well. So not only the FRB happening in 2020 April, but also there are other ones that we had seen some X-ray activity from. And so it seemed, and of course, these radio bursts were several orders of magnitude weaker than the FRB. And so if the X-ray to radioluminosity kind of scales proportionally, then in that case, it's perhaps not very surprising that we did not detect all of them in X-rays. And of course, we don't have full sky coverage in X-rays as well. So the fact that we've discovered many of them, in my opinion, tells me that likely all radio FRB-like bursts are coincident with X-ray bursts. And the overwhelming majority of X-ray bursts are not coincident with radio bursts. And people can speak to that. There has been many deep observations in 1935 and long coverage with radio to only discover one or even null. So of course, kind of if somebody could collage all of that information, not only looking at the population of radio bursts from 1935, but also bring in all of the X-ray bursts, which is probably not an easy task because you'll have to contact multiple teams. These X-ray bursts have been detected by CONUS Wind, the Russian Space Telescope Integral from the Italian Space Agency, HXMT from the Chinese Academy of Sciences, and from EGBM from NASA in the US. And so you have to contact all of these people and kind of bring them all together. But I think it would be very useful because you would be able to kind of answer some questions about whether indeed the radio to X-ray luminosity ratio, is it constant? What is the scatter there? Is it very tightly, for instance, correlated, or there's a lot of scatter? All of that is extremely important. For the same X-ray luminosity also, do you see the same curvature in the FRB associated burst compared to the others, or is it really different for the same luminosity we're talking, okay? So all of that will give you very excellent ideas for what's going on. But indeed, you need to kind of contact. So you got to be social and perhaps coming from a neutral country, so maybe Canada or Luxembourg or whatever. But some people can do this. Okay, so I'll mention one more thing about 1935. So this happened in October 2022. So we had the second brightest radio burst. So that would be the dashed line in red, basically at 0, detected by China as well. So 1935 was in an active state again. And so the top panel in what you're seeing here is basically the burst per minute. So we're talking about a burst every minute on average for about 2+ days before the FRB was detected. This is a zoom in on a longer monitoring in X-rays, by the way. That was like a 20-day something monitoring in X-rays. And the bottom is basically the X-ray count rate, or a proxy for luminosity, how bright the source was. And immediately you can see that there was a flare in X-rays just before the FRB occurred, but the FRB occurred towards kind of like the tail end of the flare. But what was fascinating to us is what was happening in the timing, which basically provides you an idea with the internal but also the external dynamics of the source. So we believe that changes in nu dot is related to kind of how much wind is escaping the star, and that relates to how much open field lines you have. So that would be the third panel that you're looking at there. And during about 10-hour period surrounding the FRB, you had a massive nu dot, the largest ever discovered by an order or 2 orders of magnitude compared to any pulsar. And during that period, smack in the middle of it, there was the FRB. And we would expect many open field lines during that period in order to get to that nu dot. That's all speculation. It's for the theorists, but that all of that is various clues that brings you closer to understanding the FRB phenomenon from the magnetar progenitor perspective. And there's a lot of physics going on here. I'm not going to go into that. Perhaps not necessarily related to FRBs. And the last thing that I want to mention is basically the population. And so that's when you start basically asking the question of, and people have looked into this plenty before we started looking into this, but the question of how connected is the extragalactic FRB population to the magnetar population in the galaxy, and that starts with understanding the magnetar population in our galaxy first and foremost. And so this has been done slightly before, but never really involved starting to constrain the population from an observational perspective. And we set out to do that. A team of scientists, that would be a PhD student, my postdoc, and some collaborators, Daniela here on the call as well, who helped quite a bit in this. But so basically we incorporated the observational constraints. We predominantly discover magnetars through their bursting activity, so we incorporated that into the modeling. We treated XMM as a survey. We see 0 magnetars discovered through the XMM survey. Sorry, yes.
Hey, George, just to let you know, 2 minutes.
Thank you. Yeah, almost done. And through that, we've been able to, and of course, we have to match the observational properties of the population, like pp dot, log n, log s, and that's what you're looking at here. And we've been able to kind of get observational constraints on some of the parameters. The one that matters perhaps the most for the FRB case is basically the birth rate. And so we've been able to get a birth rate in the fraction of neutron stars, roughly speaking, about 10%. But I will say that this is a strict lower limit, and the case for that is because in our modeling, with quite a bit of assumptions, and you can go look at the paper for those or ask me, but we basically, for this first work, we said that we would detect every single outburst with the current large field of view high energy monitors, which is not the case, and we know it's not the case. And so, and of course, our results show that the magnetar population that we simulate that matches the observed one actually does not match the heliocentric distribution. It's actually galactocentric, and that tells you that we're missing something. So we're working on a more complete model, incorporating the sensitivity of SwiftBAT and other missions to kind of get a better idea of that fraction of magnetars born at neutron stars. So it will be somewhat larger than the 10% typical number. By how much, I cannot really tell. 20 to 30%, I don't know, but we shall see. And then from there, you can basically, and the model also incorporates a more detailed prescription of the bursting activity. And then from there, you can go and ask yourself, okay, what does that mean for the FRB population? So that's a long work in progress that we're trying to kind of perform more rigorously. So let's see where we get. Okay, I'll leave you the summary. I'm gonna tell you that X-rays are expensive. They don't easily come. We mainly provide you with upper limits, which I apologize for. But there are things that one could do. Heavy continuous radio monitoring of magnetars and outbursts. That's extremely important if possible. Also in quiescence, because we don't know what they're doing. We only observe them typically in outbursts. And we miss a lot also. So if it's possible in quiescence, that'd be great. And then the rest, if we can do stuff from the X-ray world, that would be great. There are some interesting mission proposed, but we shall see. The landscape is changing under our feet as we speak. So hopefully we're lucky in the meantime. So thank you.
Okay, questions for George? We'll do Sujay first.
Hi, Sujay Mate from RRI, Raman Research Institute, Bangalore. I have a question about the X-ray detectability. So you're saying, are we limited by FOV or are we limited by the sensitivity? Like if you have all sky coverage right now, given the X-ray to radio ratio, will we be able to detect all of them, or we do really need more sensitive detectors?
Thank you. I think we are limited by both. So we certainly know that we are limited by sensitivity because we do see an extension. If you look at the log n log s distribution of the bursts with Fermi or SwiftBAT, and then if you look at the ones with XMM or nicer, you do see an extension of that log n log s.
Sorry, George, can you repeat? I think you were there was an issue with the internet.
Oh, I apologize for that. Can you hear me better now?
Yes.
Okay. So what I was saying is, I think it's a combination. It's the two together, but mainly sensitivity. So, but that comes also with, if you want to become more sensitive, it's difficult to have a larger field of view. But I'll tell you that if you look at the log n log s distribution with Fermi GBM or SwiftBAT, which are large field of view monitors, and you look at the ones from NICER, you will see that the log n log s actually extends down to below the sensitivity of Fermi and Swift, which tells you you're missing quite a lot because it's a steep log n log s. So you want to gain in sensitivity, but that unfortunately kind of lowers your field of view unless you build this humongous telescope. Yeah, it's not easy. But what I will say, perhaps just to finish up, is that radio bursts most of the time have happened from 1935, close to quite active periods. And that's when we observe them mostly with X-rays. So if you have a monitor that can just look at 1935 and afford looking at it during activity, and not only 1935, other magnetars, that would be the best strategy. So you have an outburst and then just stare at it. And that's what HXMT did to catch the beautiful X-ray burst associated with the FRB. So there are ways around it, and it's not easy. Yeah.
There's time for another question, but maybe the next speaker could start to right behind you. Oh.
Hi, this is Sachin from McGill. So there was a recent coherent burst from Carina Nebula that we all heard about during this conference. Was there any X-ray activity associated with the burst from Carina Nebula?
Thank you. Shout out to Kaustubh who performed all of that analysis. We looked for X-ray activity from the source with Fermi because of its large field of view, and with Swift as well, and we could not find any. In fact, I believe actually now I know for sure the source. I remember. The source was in the field of view of Fermi GBM, and we did not detect any bursts in Fermi GBM. The LX over LR is not very constraining because the radio burst was a bit on the weaker side. So if we're lucky and we detect more bursts from that source that are a bit brighter, maybe these upper limits start becoming tighter and tighter, and then a comparison with 1935 becomes more meaningful. But yes, down to the limits of Fermi and Swift, we do not see anything.
Okay, I think we have to move on to the next speaker. Thank you very much, George. Okay, next speaker, Marcus Lower from Swinburne on the title you can see in front of you.
Thank you. So yes, I'm Marcus Lower. I'm an ARC DECRA fellow. Oops, I'm not sharing. Oh, just classic. Yeah.
There's all, sorry for that.
No more subtitles. All right. Yes, I'm Marcus Lower, ARC DECRA fellow at Swinburne University. And today I'm going to be telling you about some interesting emission that we saw from an extraordinary radio loud magnetar, partly on behalf of the Parkes P885 magnetar monitoring team. The magnetar I'm talking about today is, of course, 1E1547 minus 5408, not SGO 1935. Now, this magnetar was actually found way back in the 1980s by an ancient telescope called the Einstein Observatory, not Einstein Probe, where it was discovered, catalogued as an X-ray point source, and kind of forgotten about for a few years, until Gelfand and Gainsler noticed that its X-ray flux was quite variable, and they suggested that it was possibly a magnetar candidate embedded in this radio shell, which you can see on your left. That's a much more recent ASCAP image of the supernova remnant. It was then observed using Muriang by Fernando Camillo and friends, and they found that that this source was actually a radio pulsar spinning once every about two and a bit seconds, and that its high spin down rate confirmed that yes, it was in fact a magnetar. And in fact, it's the second radio loud magnetar to be discovered after 1810. What makes this magnetar a bit unique amongst the other radio loud magnetars is that we've been conducting an almost continuous 18-year monitoring campaign using both Muriang 64-meter Parkes radio telescope and the Swift XRT. So on your left, what I'm showing there on the top is the X-ray flux over a very long time span going from 2007 all the way to about 2025. And you can see, it's undergone several X-ray outbursts during that time. The bottom panel is showing the spin down rate as a function of time. But what I want to draw your attention to is the sort of gray band along the bottom there. That's kind of giving you a sense of the fraction of time that the magnetar is seen to be active in the radio. And it has been more or less active all the time. Every time we point parts at it, we see it in the radio. So this is the only persistent radiolab magnetar that we know of to date. And with 18 years of observations, you find that it can kind of do anything. If you can think of any kind of pulsar phenomenology, any kind of pulsar thing, this magnetar does it. It has pulse profile shape variations, glitches, spin down rate variations during outbursts, and then pretty much every single kind of emission state switching that you can think of. It's got nulling, state switching, so yes, so there's and a lot of this data is currently unpublished, and we're going to be looking at it at some point. But the data I'm talking about today was all collected shortly after the 2009 outburst. So this began back in January 2009, where the X-ray flux shot up by about a factor of 2 to 3 orders of magnitude, and it was followed up extensively by pretty much every high-energy telescope that was out there at the time. During this period, its radio emission switched off very briefly, then came back, then switched off and did all sorts of crazy stuff. One in particular cool thing was that there was similar to SGI 1935, there was a coincident detection of a 3 sigma coincident detection of an X-ray and a radio outburst that was seen in a joint observation taken by X-Newton and Marie. And that's reported in this work by Israel et al. From 2021. A few days after the outburst began, so about a month after it began, we also saw this unusual little transient component pop up. Now, as far as magnetar outbursts go, that's pretty normal. Their profiles change all the time. We see new components appear and disappear. That's not that unusual. This was only seen in our X-band observations taken using the Mars receiver on Parkes. Unfortunately, the data we have is only fold mode, so we're averaging over between 9 to 12 rotations of the magnetar for each subintegration. I guess I can point out this transient component's highlighted in that little pink square on the left. So that's on the left is showing pulse phase versus time. You can see you've got kind of regular magnetar emission and then this sort of intermittent component. If you look at sort of a waterfall diagram of what the sort of spectrum of this transient component and the more regular emission looks like on the right, again, you can see broadband emission for the magnetar, pretty normal, but the transient component, if you squint, has kind of some interesting looking features. And if we look at the individual subintegrations containing the emission from this component, from this transient component, what we notice is that almost all of the bursts, if you could call them that, are very narrow band. Some of them are only like a few pixels in these pictures that I'm showing. Now, these are real. These aren't radio frequency interference. They only show up within a very narrow phase window. And they also all show the same kind of diffractive scintillation that we see in the broadband emission. Whereas the interference, you'd expect to see it across all pulse phases. It shouldn't be in phase with the rotation of the magnetar. We also have a few subintegrations where we see what could have been multiple component bursts, but because, again, we're averaging over several rotations of the magnetar, it's unclear whether these are single events that have multiple components or these are just individual bursts that we've just averaged, that have been averaged together, which is unfortunate. So in this work, we are sort of still treating these possible multi-component things as individual independent events. In terms of their properties, we've extracted the spectra and we've run things like the running power law model that was used in the Time FRB catalog 1 to look at the spectral running. Unfortunately, doing a bit of an apples to apples comparison between the results of that, running that on this magnetar and the other sort of narrowband emitters like the Crab pulsar and SGI 1935, it's a bit hard to do one-to-one comparison because, as you can kind of see, the scale on the x-axis and y-axis of these plots are very, very different. And this just comes down to this really comes down to the observing frequencies that these bursts were detected at. In terms of maybe a bit more informative, looking at widths versus spectral extent, the kind of distribution of widths and spectral extents kind of follow that, what was seen for the repeating FRBs in the Chime FRB catalog. And I saw there was an update yesterday for the catalog too, which looks this looks a little bit more like what's seen in the Chime FRB2 catalog 2, which is kind of nice to see. In terms of polarization, the bursts are in general mostly highly polarized. There is a bit of diversity in terms of the fraction of linear versus circular polarization. Some of them look a little bit over-polarized, and that's partly because of some artifacts in the data, as well as some questions about our calibration. So in general, that appears a bit different to what's seen in the sort of polarization fraction distributions for several repeating FRBs. So there is a bit of a difference there. But of course, repeating FRBs, as we're now starting to find, are also quite diverse in their polarization properties as well. Sticking with polarization, this here I'm showing is a series of average pulse profiles. This is many, many rotations averaged together, both seen on different days. And you can see its polarization was changing quite a bit over this sort of 10 to 20 day period. This is also seen at some observations at different frequencies. So drawing your attention to the position angle swing in the top panels of each of these plots, you can see the position angle swing was quite variable. The very first observation, it's even going the opposite direction to all of our subsequent observations. And then the sort of lines that are overplotted, those are the rotating vector model fits. So, we can kind of see that the rotating vector model does somewhat match the position angle swing as it evolves over time. However, if we then look at this middle panel here, the implied angles between the spin and magnetic axes is incredibly variable, much more than you'd expect for, a very simple dipole that could be kind of quite stable with time. So this implies that we're either seeing some sort of variable changes in the magnetic and viewing geometry of the star, in which case the mechanism behind that's a bit unclear. It could be something like free precession or twisting of the magnetic field. Or it's also possible that the rotating vector model is just not a good match to this data. In which case we'd need something more complicated to try and explain what's going on. I just want to end on this other little kind of, what's maybe a minor point of interest. So we've now got 4 minutes. We've now got 4 known narrowband emitters of radio bursts, kind of in and around our galaxy. You've got the Crab pulsar, SGR 1935, the Crab's LMC twin, BO5 4169. These are all, young, energetic pulsars associated with supernova remnants, and that is kind of interesting. I don't really know what to make of that in terms of, does this imply that repeaters are related to these objects? Maybe. But if that is the case, then we are starting to kind of build up a small, at the moment, population of galactic-ish BO540 is not in our galaxy, it's in the LMC, population of repeating FRB analogs, which might tell us a bit more about, the mechanism responsible for the repeating FRB emission. So just to end, I think I've hopefully convinced you that 1547 is a truly extraordinary magnetar. It does everything, as I said. For a very brief period of time, we saw this transient component appear where it was emitting quite band-limited radio bursts. The bandwidths are comparable. Bandwidths and polarization properties are comparable to other narrowband emitters, and there are some similarities to repeating FRBs. This coincided with some dramatic changes in the magnetic field topology that we don't fully understand at the moment. And this raises, of course, this interesting question of, is this magnetar yet another galactic FRB analog? The emission properties kind of imply that maybe there's a similar emission mechanism. However, of course, this still doesn't account for the whole issue of these bursts being 10 orders of magnitude less luminous than genuine FRBs. And I also want to point out that the P85 project on Parkes is very well poised to capture the next outburst from this object and any other magnetar that goes bang and over the next few years. So thanks for your time, and I'm happy to take questions.
We've got a question online. Oh, you need this?
It's in the chat. Yeah, so there's a question in the chat. Hi, Pranav here from MPIFR in Bonn. Do you have any statistically significant hold on only the highly linearly polarized FRB-like components of this magnetar? And do they show distinct polarization and spectral properties?
That is a very good question. I can say for the position angle swings for the highly linearly polarized bursts, they don't follow the same rotating vector model tracks that we've plotted against the broadband emission. They're kind of just scattered all over the place. Yeah, otherwise, let me go back a few slides. I mean, again, these things are kind of a bit scattered all over the place. There's no kind of real, they don't like cluster as well as like the repeating FRBs in terms of polarization fraction space.
Okay, question from Yuri.
Thank you for a very interesting talk. I agree with you. There's so many exciting things going on in this pulsar. You could talk in this magnetar. You could talk about it for an hour. But may I ask something about this the narrow band features that seem to appear at a certain pulse phase? Now you have a coherent timing solution, I imagine, for over 18 years, or coherent enough. It's connected. It seems connected anyway. It's fine. But if you just looked at these, could you find the periodicity from these?
Oh, that is a good question. I'm not sure. Unfortunately, again, this is fold mode data. So I guess for this observation, we see quite a few bursts. I can imagine you might be able to get a periodicity, but like an RAT. But yeah, that would be if we saw it again do this, that would be a good thing to test.
Hey, time for one more question. Lose your laptop.
Thank you. Thank you. I'm Matteo from INAF in Italy. Another question regarding the narrowband burst. I mean, I couldn't appreciate the scale because it's
a bit hard to tell.
There's a millisecond.
Yes, these are all a
time.
few milliseconds wide.
Okay. Do you have like high resolution data to see if there are, substructure like Saturn moons?
Unfortunately, no. Even there was one observation we had simultaneous fold mode from the analog filter bank. But aside from the fact it was an analog filter bank and the data is not very good, the time resolution was even worse. It was like 2 millisecond integrations instead of, well, time samples instead of 1 millisecond. Yeah.
Okay, let's thank our speaker again.
The next two talk are the first one will be by Zhenshu Zhang on restriction constraints of magnetar magnetic energy as an FRB.
Great. So yeah, anytime you're ready.
Okay, can you hear me? And can you show my screen?
Yes, you can hear it.
Okay. Okay, now I'm going to start. Hello everyone, my name is Zhenshu Zhang, a PhD student at NAOC, surprised by Dili and Pei Wang. It's my honor to present our recent work on FRB 2024 on behalf of the Fast Key Science Project, providing the most stringent constraint on magnetic energy of magnetars as an energy of fast FRBs to date. Okay. Now, since Chenhui Niu has already given a nice overview of FAST, I won't go into the details again. I'll just mention the sensitivity of the FAST help us to capture the more bursts of the FRBs. And the FRB T-Sense project is one of the major large programs at FAST. So far, it has detected over 26,000 bursts. And here's some active repeater, and the work I'm presenting here is based on about half of them. And here's a brief timeline of the basic information of FRB 2024-01-14A. The source was first discovered by Cham, and thanks to the VOE network and ATEL, the discovery was rapidly circulated. We decided to follow up quickly as the source appeared to be both bright and hyperactive, and later on we detected a few bursts, and which we reported on the ATEL. About a week later, Meerkat team localized the source precisely and identified its host galaxy. So we calibrated the fastest pointing position since then. And on March 5th, we captured the burst storms and reported it on the ATEL. Follow-up observations with the GTC telescope, including work of Shang Lichen from our FRB K-Sense project collaboration, measured the photometric redshift for this source. And here we present the fast observations of this most active repeater up to now. We carried observations between January and August in 2024 and maintained a nearly weekly observation cadence over a span of 214 days and 34 hours of on-source time in total. And during this period, the average burst rate was about 220 bursts per hour. And at the peak, the burst rate reached an astonishing level of over 700 bursts per hour. This is the highest rate ever recorded. And all the bursts were identified using a SNR threshold of F12. This corresponds to a sensitivity of roughly 26 millijansky milliseconds. We identified two major active phases during this period. The first started from the March to April, and the second happened to between July and August. During our observation period, we found that this FRB remained active for the entire 8 months. In total, we detected 11,553 bursts, which means we have collected the largest data set of repeating bursts to date. We calibrated the flux density and energy for each burst, and as shown in the time energy counter plot, 2 major burst storms are clearly visible. In addition, we did not see any significant trend in the daily median energy all over the observation. As Jerry New has just mentioned, observations have shown that magnetars are a source of FRBs, and so far the magnetar channel is the only known mechanism that can produce FRBs. The strong energy release from this source allows us to place constraints on the magnetar as a central engine behind these bursts. We estimated the total equivalent energy and emitted during our observation period by scaling it according to the duty cycle of our observations. Assuming a typical radio efficiency of about 10 to the -4, and taking a global beaming factor of 0.1 in consideration, we found that the total emitted energy is about 1.47 times 10 to the 47 erg. Compared with other active repeaters reported so far, the energy is more than 30 times higher. It is also around 86% of the total dipole magnetic energy stored in a typical magnetar. If the current rate of the activity continues, the magnetar may run out of valuable magnetic energy in just about 1 more month. As a magnetic moment of a magnetar can be estimated through the equation shown here, we provide a lower limit on the magnetic moment of the central magnetar. The value we derive is about 9.4 times 10 to the 32 Gauss cubic centimeter, as shown on the right-hand axis of this figure. Our result places a strong constraint on models that assumes a low radio efficiency, such as non-magnetosphere models. It also challenges models that rely on large B-mean factor within typical magnetar parameter. To match the observational data, the central engine must either emitted within tightly constrained parameters, or it must be a more powerful compact object than a typical magnetar. We also examine burst rate distribution of the energy, and we identified a characteristic energy around 10 to 37 arc. As shown in the plot, the burst rate tends to decrease when the energy falls below the EC and clearly deviates from power law behavior. We perform a power law thesis with increasing the energy thresholds from the EC and found that the power law phase indices didn't converge to a consistent value. This indicates that a single power law model does not describe the overall distribution very well. We also examine the log normal fit and the bimodal log normal fit on this distribution. We noticed that the residuals and the normalized Pearson coefficient shows deviations in simple log normal fit. In addition, statistical tests indicates that the single log normal fit performs worse than the bimodal one. These results suggest a bimodal structure in the distribution. This, in turn, may imply that there are multiple burst populations or distinct emission mechanisms in repeating FRBs. We also plotted the corner plot between observational parameters, parameter pairs, but no correlation were found except flux density, bandwidth, and pulse width, all of which show positive correlation with the burst energy. This is expected as energy is derived from these parameters, so they are naturally coupled. The first KSP collaboration has also conducted a comprehensive analysis on this repeater, including polarization, periodicity, and morphology. Results on arm variation, Faraday conversion, and so on were just reported in Tianzong Wang's talk. And Deng and Zhou search for the periodicity on both short and long timescales using multiple methods. As a result, we identified 3 sub-second period candidates and a potential 68-day activity cycle, and several QPO candidates. The QPO candidates exhibit a strong correlation between the central frequencies and widths, suggesting a potential universal quality factor. This may be related to magnetar cluster oscillations or Arvan wave instabilities. Furthermore, multiple QPOs appears to evolve dynamically over time. These findings help to clarify the observational basis in previous studies, where QPO detections were sometimes attributed to the spin period of compact objects. Longxuan Zhang analyzed the statistical properties of burst morphology. The burst
just to let you know, sorry to interrupt, 2 minutes.
Oh, okay. Based on the bursts are classified based on the morphological features and the frequency drift rates. The significant statistical differences are observed between the upward and downward drifting clusters. Okay, here's a summary of my report. Our 4 works on energy budget, polarization analysis, periodicity searching, and the burst morphology will be available soon as a preprint on the archive. And thank you for your attention, and I will be happy to take any questions. Okay, I will stop here.
Hey, thank you very much for the very interesting talk. We have questions. We'll start with one from online.
Thanks. This is from Pranav in Bonn. The question is, did you also investigate whether the bimodal distribution observed in burst energies is correlated with the classification of bursts into clustered and Poissonian types based on their wait time distributions?
I will come back to the. So that's a great question. Bimodal, we do analyze waiting time distributions, but haven't analyzed bimodal energy distribution with a waiting time distributions yet. And we will try it later. Thank you.
Great question.
Thank you. Hi, I'm Marilyn Cruces from UC Chile. I was wondering regarding the 68 potential activity cycle that you mentioned, and for what I read in the slides was inferred from Lomscargo and from folding. Do you have those results?
Yeah, this work is mainly developed by Deng Zhou, and as far as I know, he used epoch folding and Lomscargo to verify this 68 per day activity cycle, but there are we only observed this source using 200 days, so there are only two or three phases for this result. It is not so solid. If you want to know more details about this, I will talk to Dunker and for your questions. Thank you.
Yeah. So Zora, what are you seeing? University of Maryland, NASA Goddard. The QPOs you find, do they have harmonic ratios of the frequencies like you'd expect from crustal oscillations, or are they sort of randomly placed in frequency space, the QPOs?
Okay. I have no idea with these questions, and so I will look transfer the questions to Dunker later, and I will talk. I will talk with you in the Slack.
Yeah, well, he was just asking if the if they're harmonically related. The QPOs, are they if you took the ratios, are they integers of the frequencies? Or you could talk later. That's okay. Okay, sorry. Okay, let's thank the speaker again.
Thank you. Okay, let's stop it.
The next speaker will be Chair.
Can I share my screen now?
Yes, we hear you.
Yeah. So can I share my screen now?
Yeah, go ahead and share.
Okay, on ultra strong magnetar.
Can you see my screen?
Yes.
Yes, we can.
Okay, so can I start?
Yes, please do.
Okay. Hi, everyone. This is Minhazur Rahman. I'm a postdoctoral fellow at the Open University of Israel. And today, I'll be talking about the implications for magnetar progenitors from persistent radio sources of fast radio burst. So for the purpose of this talk, I'll be focusing on the most studied case, well-studied case of PRS, which is the PRS associated with FRB 2025. Now to start with, we can have a basic summary of the observational facts regarding this. So from radio imaging, you have an upper limit on the size, which is 0.7 parsec. From radio scintillation studies, you have a lower limit on the size, which is 0.03 parsec. And given the shape of the spectrum and the redshift of the source, and employing an equipartition analysis, assuming a synchrotron origin for the persistent radio emission, we have an equipartition radius of 0.1 parsec, which sits comfortably in between the lower size limit and the upper size constant that we have. So if you combine all this together, you get a very important and crucial ingredient in identifying and selecting a particular kind of magnetar progenitor. So basically, what you have is a very compact PRS. Now, if you are trying to understand the PRS in a magnetar kind of a framework, what is the picture that you have in mind? So the picture is something like this, that if you follow my cursor, here we have a magnetar central engine, which is giving rise to the streams of charged particles, which is in fact confined by an expanding supernova remnant. So post confinement, it is a population of trapped, highly energetic, hot, electrically charged particles, which is forming what is referred to as the magnetar wind nebula. And it is synchrotron radiation from this magnetar wind nebula, which is the candidate for the persistent radio emission. Okay, so this is the region number 2 in this particular schematic, labeled as magnetar wind nebula, which is the candidate for the persistent radio emission. The other thing that you can immediately see from this schematic is that if you consider the outer radius of the magnetar wind nebula, that is in fact equal to the inner radius of the supernova remnant. That means if you have a constraint on the size of the magnetar wind nebula, you have indirectly a constraint on the size of the supernova remnant itself. In fact, we can actually flip this around and say if you have a size constraint of the supernova remnant in any kind of a progenitor model, you also have a constraint on the size of the magnetar wind nebula, which in fact is the size corresponding to the PRS that you just saw in the observations. Okay, so then for a magnetar progenitor model, we can ask this question: what has been the most popular magnetar progenitor model in the literature? And the answer, it turns out, is a millisecond magnetar. So the references that you see on the screen are not supposed to be exhaustive, but rather it is meant to be illustrative in showing you that this has been a popular candidate for around a decade. Now, given the compact size of the source that we just saw from observations, we can actually put this millisecond magnetar progenitor model to the test. And what is the test that you can put this to? We can ask a very simple question. We can ask the question, say, suppose in this particular framework, what is the time that is required for the supernova remnant to expand to a size of around 0.1 parsec, correct? And that time would correspond to the age of the source. For a millisecond magnetar, the time it takes for the supernova remnant to actually expand to a size of 0.1 parsec is close to 2.5 years. It's less than 3 years. And it is not surprising why this is so. Because you see, if you have a magnetar progenitor kind of a system, that suffers from a rapid spin down and almost 10 to the power 52 ergs of energy is deposited to the supernova remnant. And irrespective of what was the initial explosion energy associated with the remnant, this deposition of 10 to the power 52 ergs of energy, it will actually boost up the expansion velocity of the remnant, and it would very quickly reach this size of 0.1 parsec and beyond. And now I want to point to this important fact that since the observation of the first burst of the FRB 121102, which by its very name was in the year 2012, we have 13 years that have elapsed till now. That means if you are considering a PRS associated with an FRB 121102 powered by a common magnetar progenitor model, it at least has to be 13 years old or longer. But clearly, if you see this number for the millisecond magnetar progenitor model, this time scale of 2.5 is much less than the 13 years time that you would actually require on the very least. So then you can ask this question, okay, fine. So the magnetar model with a millisecond magnetar progenitor does not seem to work if you take the compactness of the PRS into account. But now, if you look at the second line of the solution, it is suggesting a different kind of origin. So what is the origin that is being suggested here? So here it is referring to a sub-energetic scenario. So what does it mean? So you saw for the millisecond magnetar, you actually had a very rapid expansion of the remnant. And that's the reason that you have very less time given the compact source size to actually reach that size. But now, if you consider a scenario where the expansion velocity of the remnant is very low, and that would correspond to a supernova explosion energy of around 10 to the 50 Earth and a mass in the range of 10 solar masses, which will give you a very slow expansion velocity. And it is not surprising, given the slow expansion velocity for the same size, you are actually reaching an age which is up to a few decades. So given that this particular scenario actually allows for longer and a wider parameter of ages that is possible for the system, this is the scenario that you advocate for in our work. So we already saw about the compactness of the PRS, but we still have to explain what actually powers the PRS. So to do so, what we have to know is actually what is the energy content in the nebula itself. Because to remind you, it is the charged particles in the nebula which is powering the PRS. So to go back to our equipartition analysis, we actually have an equipartition energy of 10 to the power 49 erg. So just to remind the audience, the equipartition energy is the minimum energy that is required for explaining a given set of synchrotron observables like the spectrum and the luminosity. So in principle, you need energy equal to 10 to the 49 or larger. Now, what you can look for is that how the nebular energy content changes as a function of time for the rotation loss channel, which is shown as a purple line here on the figure. So here you see, if you trace the purple line, it first rises and then peaks. So it peaks at the characteristic spin down time scale, unsurprisingly for the rotational loss channel. And then the energy content due to the rotation channel actually comes down. And this can be understood in the frame of adiabatic losses, because the magnetar wind nebula that you have is not a static thing. It is actually expanding and pushing on the supernova remnant. So with time, the energy content of the nebula is going to go down because of this PDV work done on the supernova remnant. So you see, if you now put a horizontal line corresponding to this energy of 10 to the power 49 ergs, you can quickly see that for the rotational channel, you can satisfy energy content in the nebula of 10 to the power 49 ergs or higher only for about a decade. That means if your system is actually older than a decade, your rotational channel is actually saturated, it's quenched. And you need an alternative reservoir of energy to actually sustain the luminosity. And that alternative reservoir of energy turns out to be the internal magnetic field decay of the magnetar. Okay. Now, in fact, if you're when you're talking about this internal magnetic field decay, one is the energy reservoir itself. What is the strength of the internal magnetic field that you have to ask? And the second question that you have to ask is what is the decay timescale associated with it? So just by the illustration that you see here, if you have to sustain your PRS beyond a decade, you need a time scale for the decay of the internal magnetic field, which is much larger. In fact, in such a scenario, we have a characteristic switching time in which the energetics in the nebula switches from being rotation dominated to internal magnetic decay dominated. And this switching time is almost independent of the initial spin period of the magnetar. Now you can ask this very fundamental question. Okay, given that we advocate for a sub-energetic scenario, which would actually give you longer ages for these PRS systems, what is the strongest internal magnetic field and what is the largest decay time scale that is consistent with the PRS observables for PRS associated with FRB 1211-028? And the solution space, if you look here, corresponds to this blue strip, where you can see that in this solution space, the ages that are possible for this particular system is up to 100 years. Okay. And in this particular solution space, what is more interesting is that you have clear definitive predictions for the synchrotron spectrum, which is that if you look at this dashed blue line, this would correspond to the cooling break. So which you can see from the figure itself. In this blue strip, the cooling break is supposed to be around 100 gigahertz. And if you look at the self-absorption frequency, this is supposed to be in the range of around 200 megahertz. So we have definitive predictions for this model.
Hey, just a little over a minute and a half left.
Thank you. So this has to be actually contrasted with the traditional magnetic powered models that has been proposed in the literature, where the decay time scale is actually taken to be around a few months. So in this kind of models, there is no way to actually differentiate between a rotational power channel and a magnetic power channel, simply because of the fact that both the spin down time scale and the decay time scale is of the same order. So almost all the energy is being released in over a decade, and there is no energy left for older systems. And this, again, this set of references is just illustrative and not exhaustive, just to say that the small time scale thing has been referenced here. And the largest time scale that we come to around 500 years is closer to the decay time scale of internal magnetic field that we do see for a galactic magnetar. So this is in kind of a not only a consistency check, but also a new kind of a paradigm that has been proposed here. So to summarize, this millisecond magnetar seems to be unlikely candidates for the PRS FRBs. The rotation power channel for the PRS is quickly quenched within a decade, and it is only the internal magnetic field channel that can be sustaining this PRS for up to a century. And for a PRS which is born in a kind of sub-energetic kind of a scenario, we have clear predictions for the spectrum, namely a cooling break at around 100 to 150 gigahertz at a flux value of roughly 35 to 40 microjansky, and a self-absorption frequency at the very low frequency at 200 megahertz at a flux value of around 180 to 200 microjansky. So with that, I'd like to end on this quote that all models are wrong, some are useful. So with these predictions, let us make the magnetar model useful. Thank you very much.
Hey, thank you very, very much for that talk. Time for some questions. Okay, we'll go to Casey. Can I throw this?
Hi, this is Casey Law from Caltech. I was interested in if you had any predictions for the potential for long-term radio monitoring to constrain this model, or if there's any variability expected on decade timescales that we can measure.
Yeah, so that's a very good question. So essentially, so if you have a slow injection of the internal magnetic field, your flux values are supposed to remain steady for almost few decades. So in fact, you can do a long-term radio monitoring of the base level flux. So I'll just maybe minimize this and show this. One minute. Okay. Sorry. Sorry. So there's some problem. Just trying to get rid of. Okay, so if you go to the long-term flux monitoring, you could actually do a chi-squared kind of fit, which I'm just trying to get here. 1 minute.
Okay, thank you.
Okay.
Sorry. Yeah. So yeah, so just 1 minute to do so. So you can do a long-term flux monitoring. So this is a plot from our paper, which shows that if you have long-term flux monitoring, you can actually constrain this temporal index alpha f, which would actually give you a constraint on the birth of this kind of systems. So for our sub-energetic scenario, we would actually have ages. If you fit this kind of model, it will come to birth ages of around 100 years.
Okay.
Okay, thank you. This is Duncan Lorimer from WVU. Nice talk. My question is perhaps to all the audience, but to you right now is how does this compare, these PRS models compare with the 300 odd supernova remnants that we know in the Milky Way? Like how unusual would they be? Would this model be in the context of those remnants? Do you see what I'm saying?
Yeah. So can you see my screen?
Yes.
Yeah. So the basic idea is that, that you have synchrotron radiation from this wind nebula. And now for the supernova remnant in our, if it was indeed the case that you had so much energy in the supernova remnant, you are born with very luminous, very high luminosity. So these PRS have bolometric luminosity in the radio band around 10 to the power 38 ergs per second. So that radioluminosity is directly proportional to the energy content. So if you indeed had such kind of systems in our own galactic supernova remnants, you would actually see very luminous sources.
Thank you.
Okay.
The last talk of the session will be by Andrea Giannardi on the searching for transient radio emission from galactic magnetars.
Hi, everyone. I am Andrea Giminardi, a second-year PhD student at USP Pavia in Italy. And in this flash talk, I will briefly describe Northern Cross observations on 7 galactic magnetars for a total exposure of 560 hours. The Northern Cross is a transit radio telescope located near Bologna in Italy. It samples the sky with a time resolution of 138 microseconds over a bandwidth of 14.8 megahertz, centered at 408 megahertz. The current configuration of the telescope corresponds to an RMS sensitivity of roughly 1 Jansky, and as you can see in the dark region of the plot, this is enough not only to detect FRB-like events from the targets, but also giant pulses-like emission and the most energetic pulses from pulsars and rotating radio transients. In our campaign, we didn't detect any radio bars directly associated to magnetars, but we exploited our observations to set upper limits on both on the burst rate and their energy distribution. Here in the plot, you can see as a color map the rate of detectable events predicted by our power law energy distribution model, and that is function of two free parameters that are the slope of the distribution on the x-axis and the normalization of the power law on the y-axis that corresponds to the rate of events with energy greater than the FRB-like event emitted in 2020 by SGRJ 1935. And the take-home message of this graph is that as we increase the slope of the power law, our limit becomes stringent and stringent on the burst rate. And if we compare our results with other observations on magnetars, for example, the ones performed by CHIME in 2020, we can see that our work is consistent with there only if we assume that the power law slope is lower than 1.4. And if we take into account also Northern Cross observations on nearby galaxies, we can find an even more stringent limit. And if I can leave you here my conclusions, and let me just emphasize that we constrained the power law and to be less than 1.4, and also this result is somewhat in tension with the models that tries to explain the whole sky rate of FRBs only using radio bars from magnetars. And if you are curious about the details of the work, you can scan the QR code and check the paper, and thank you for the attention.
Okay, thank you very much. So time for a question. Yes.
Hi, Marilyn Cruces from UC Chile. So sorry, I'm not quite familiarized with the observing setup. Can you go back a few slides? So what's the bandwidth observing frequency? Okay, so it's low frequency.
Yeah, it's low frequency, centered around 408 megahertz. And actually, we, as you can see also in the graph, we look for a maximum duration of around 75 milliseconds. So burst with a maximum duration of, yeah, we are sensitive to not only FRB-like events, as I said.
Yeah. Thank you.
Thank you. Miles Sherman from Caltech. I was wondering if you tried to, this is kind of a follow-up question, but I was wondering if you tried to reconcile your results with high frequency observations or monitoring of magnetars and nearby galaxies as well.
With respect to to high energy observations, unfortunately, our 7 magnetars were not active at higher energies during our campaign. This campaign was performed from January 2024 to January 2025, and yeah, we can also compare our campaign with these other similar campaign performed at the same frequency actually, that are these ones. I don't know if.
Thank you.
Okay, thank you.
Okay, and I guess it's time for coffee right now. So, and we return at 3:40. Was it 3:40?
3:45.
Oh, sorry, 3:45.
Just that on the bottom. Yeah. All right, please take a seat. Please take your laptop. Welcome everyone to this discussion session, which will be about galactic analogs of FRBs. Both myself and Miles will be coordinating this, and hopefully you will be doing most of the talking. So I'm Jason Hessels at McGill University, also affiliated with the University of Amsterdam and Astron.
And I'm Miles Sherman. I'm a grad student at Caltech, mainly working with the DSA 110.
You can barely hear us.
That's my fault. Yeah, I'm Miles Sherman. I'm at Caltech. I'm a grad student, mainly working on the DSA 110. Forgot it doesn't.
No worries. Okay. So what Miles and I have done is we've come up with 4 themes. The first theme is about pulsars and compact objects in the Milky Way. The second is about magnetars. Surprise, surprise. The third is about pulsar wind nebulae, supernova remnants, and their potential relation to PRSs. And then the fourth is about the LPTs. And these are topics that we've been hearing about all day. So what we would like to do is maybe spend 10 or 15 minutes on each of these topics. And what we are going to do for each of them is we're just going to spend 2 minutes motivating the topic a little bit. And then we want you guys then to raise points. And hopefully someone will raise 1 point. And then we will take some reactions to that point before we move on to another topic, so that we don't just bounce around between random remarks, that we try and steer the conversation a little bit. So the first question that we have out of the 4 is to what degree can pulsars and compact objects in our own Milky Way, how far can we stretch this analogy towards FRBs? So we know that galactic neutron stars have actually different types of radio pulses they make. The pulsars that were discovered already back in the 1960s have this kind of canonical polar cap radio emission, and as the star rotates, we see these pulsations. But we know giant pulses as well, and there's reason to believe that that comes from somewhere different in the magnetosphere or further out. We have magnetar radio pulses as well, and magnetar bursts, as we've seen. So are these, can we just ramp up the luminosity and we get FRBs? This is a question. And to remind you, we've seen some versions of this parameter space many times throughout the conference. A lot of the morphology that we see between pulsars, magnetars, and FRBs is similar, but don't forget that the luminosities are off by a factor of a trillion. So is that a problem or not? Might be. Next point is some galactic neutron stars are in interacting binary systems. So when we talk about dispersion measure variations and rotation measure variations, we need to remember this, right? So we have neutron stars that experience Roche lobe overflow, accretion through Roche lobe overflow. We have wind accretion in more massive systems. We also have neutron stars that have very low or high mass binary companions. We'll come to supernova remnants and all of that stuff later. But in terms of interpreting DM and RM variations, we should keep this in mind. And lastly, yeah, like I was saying, does similarity in phenomenology necessarily mean that the source type is similar? So we'd like to open up the floor to some points and reactions to this. Again, under the topic of how far can we push this analogy of pulsars and compact objects as we know them in the Milky Way for understanding FRBs. So who would like to open the floor? Yeah.
Hey, this is Pawan from Swinburne University. Yeah, so just to open up the conversation, I think the first thing in terms of galactic analogs, the first source that comes to my mind is 1259 minus 63, which can explain the.
Yeah, do you want to explain what that source is for people
Yeah,
in the audience who might not know?
It's a pulsar B star system, and every time it goes past B star, a decretion disk, you would see that there is a flip in RM sign, which is kind of used as an analogy for 190520B flip in the sign of RM. And we have been seeing more increasing sources of FRB's repeaters, especially, which have been showing this flip in sign of RM and finding galactic analogs. I just want to know what others would think in terms of finding such really weird sources in our own galaxy, and then try to see if at least canonically some of their properties match with what we see with repeating FRB sources, which is fairly straightforward compared to non-repeaters. Absolutely. So yeah.
Yeah, so there are a number of young pulsars in the galaxy that have a massive stellar companion, and they have large variations in DM and RM. That's a great source. I think it disappears when it gets close to periastron, right? Yeah. And importantly, most massive stars form in binary systems as well. So as long as they're not disrupted, it shouldn't be a surprise that you have a binary companion. Would anyone like to react to that point? Is this a plausible model for some of the FRBs? And think of, like, for instance, the third repeater in its 16-day periodicity. Yeah, Vicky?
Well, so 1259 minus 63 is an interesting case because it's a several year orbit and, way wider. The eccentricity is, I think, 0.86. So the periastron distance, it's we could work that out. But in a 16-day orbit, that's probably a much smaller orbit. And so, but in 1259 minus 63, the phenomenology is you have, first of all, huge scattering variations, huge RM changes, huge DM changes as a function of orbital phase, particularly near periastron. And if you look at a recent paper by Ketan Sand et al. From CHIME data at the 16-day repeater, you don't see any variation of scattering and DM with phase. Now, I know there are models that could, in principle, avoid that, but I just feel like, at least naturally, you might expect some sort of hint. So perhaps it's not a showstopper, but I think that's a relevant clue.
Maybe we'll go to, sorry, this is just closer, and then we'll come to you. Yeah, first go to Rob. Yeah.
Great. Yeah, I was just gonna say, I know 1259 minus 63 often gets talked about. A lot of Black Widow and Redback pulsars show very similar things. It takes very little plasma to cause what we perceive as crazy RMs. If you have a companion, it's going to have a much larger magnetic field than you see in the ISM. So I'm not suggesting that FRBs have to be in spider systems, but for instance, in Terzan 5A, it's less than 1 DM unit change across the orbit. Most of the orbit is nice and quiescent, and then less than 1 DM unit, no change in scattering, basically no change in DM. And you get absolutely wild changes of first hundreds of RM units, and then enough that you get parity conversion. So just the point, the lack of DM variation does not mean that there's not plasma that can cause, for instance, the RM variations at the order that we see.
For sure. And as Miles ferries it up there, I'll just mention that, like, those spider systems have mini eclipses that are sporadic and which kind of indicate that the plasma is magnetically threaded as well, right? Yeah.
So I think there are some things that we can learn about potentially non-repeaters by studying these galactic neutron stars. When we think of magnetars, we automatically associate them with neutron stars with 10 to the 15 Gauss magnetic fields, but that need not be the case.
Oh, sorry, could you please introduce yourself as well?
Naveen Sridhar from Stanford. So when we talk about magnetars, we automatically associate them with 10 to the 15 Gauss neutron stars, but that need not always be the case. There are some neutron stars, particularly PSR 1846 minus something in the supernova remnant KES 75, which was long thought to be a typical rotation-powered pulsar, but then it showed magnetar-like bursts. only for a very short period of time. That is, the outburst required more energy than the rotation power. So it's possible that seemingly normal neutron stars could occasionally become magnetars and then become regular neutron stars, or just show magnetar-like behavior. So this could be something that's perhaps happening in many apparent non-repeaters, something that we can learn from. So just throwing out there, that's it.
Okay, thanks. And thanks, Naveen. And I think Barak had a comment. You can just risk it. Oh.
Hey, Barak Zakai.
Can you project a bit?
Yes.
Yeah.
So to me, the biggest question. What? I'm Barak Zakai. To me, the biggest question in saying, oh, an FRB is my galactic friend X, is that if I have 100 examples of galactic friend X, why are they not FRBs? And I think that this is an important clue in the discussion. Why don't we have like many of them in the galaxy? There's something that needs to be very rare, and we are not putting the emphasis on
So on that topic, does someone know off the top of their head? Imagine most FRBs are in spiral galaxies, which is, we know is not completely true, but imagine most of them are. So how many galaxies do you need to have on average before you find one that has an FRB in it? What's the number?
Per galaxy per century?
And who are you?
Daniele Micheli from Marseille, France. I think papers in the literature reported 2 per galaxy per century, something like that.
Seems high. Okay, Mawson?
Well, depends on the luminosity, of course.
Yeah. Oh.
Yeah, I'm Molson Simons from here at McGill. I think I track with Daniele's point in that, like, if the all-sky rate for like above like 1e to the 39 bursts, I think in the Chime first catalog was like 500 per sky per day. If you're sensitive out to like a redshift of 0.5 to bursts like that, that's a lot of galaxies and not a lot of FRBs. And so, like, I don't know the fact that we haven't found any in the galaxy is necessarily, like, I don't know if we need to explain that tension.
Can we go to Adam?
And actually, before we go to Adam, I just wanted to mention on that, there's also seems to be a, dependence on the type of galaxy, of course. Like, there have been these long, very long observations of nearby galaxies as well that haven't really detected anything. The Northern Cross, survey was just one that we heard about, as well as some from like the DSN telescope, where you're looking at regions that should have a lot of FRBs and maybe don't.
Hi, this is Adam Dong from NRAO. I want to, I agree with Barak in that, like, they should be really rare. And I think one thing is that, there's these hyperactive repeaters, and with for example, a rat. A rat, you'll find, a rotating radio transient, you'll find a period. Like, you get 3 pulses and you get a period out, right? But with these hyperactive repeaters, we just saw 11,000 bursts, and they said they may have a period, right? Like, it really doesn't seem like anything in pulsar land, except for the SGR 1935 bursts that aren't coming on phase, right? So that's just my comment.
Okay, thanks. Is there a final comment on this before we move to the next topic? Please introduce yourself.
I'm Dotan from Weizmann. I think in the same sense of something that should be typical, or maybe so typical and low energy that we don't see it in FRBs, but extremely rare in the galaxy. Do we know to characterize like how the rate of bursts gets when you go to very low and to
Yeah.
barely detection, and how does the those galactic analogs, really the tail of the highest energies, highest energy burst that they can emit, like.
Yeah, so there are some galactic pulsars that the energy distribution starts to flatten as you go to the brightest pulses. So you could say, well, maybe it extends really far out. Some of the hyperactive sources that FAST has looked at, they're claiming to see a turnover in the energy distribution, but they see like a characteristic lowest energy already, so that it wouldn't extrapolate all the way down to pulsars. Yeah, it's a really important point. I think the answer is that is a point of study still. Figure that out. Yeah. Okay, then thanks for your comments, and we will move to the next topic, which will be led by Miles.
We'll switch. All right. Yeah, so this is kind of following on, the things we've been discussing with pulsars as we've sort of naturally started moving towards magnetars. So I'll just kind of motivate that a little more. So again, there's roughly 30 magnetars, depending on how you count in the galaxy. A small subset of these are radio emitters. Most of them emitting in X-rays, hard X-rays, and then shorter X-rays for their outbursts. And as you can see from this plot that we've seen a couple of times in the luminosity versus pulse width, magnetars kind of generally cluster around 1 Jansky kiloparsec squared. But then you have SGR 1935 that kind of spans the gap between magnetars and FRBs. And it's curious why we don't detect a lot more in that range. If the magnetar FRB model, has any weight, then it might suggest there's multiple formation channels for FRBs, like there might be for magnetars. And there are a number of magnetospheric models that are associated with magnetars, as you heard about earlier in the week. So some of the questions, of course, are surrounding, the main link that we have, of course, is SGR 1935. We saw this earlier during a talk. And a couple of the questions that we were thinking about are, in general, how likely or universal is the FRB magnetar model? Is it something that applies in all cases or only to like the hyperactive repeaters? Is there some distinction that we should make or somewhere that we can draw the line? How robust is our identification and understanding of magnetars? I mean, we only have 30 of them. So is that, what are observational biases there? Are we only detecting certain types of magnetars? And what is our distinction between pulsars and magnetars? As was just mentioned, pulsars can enter these magnetar-like phases as well. How do we interpret the luminosity difference that I just showed between magnetars and FRBs? And how do we search for high energy counterparts, since most magnetars are emitting in high energies? And then finally, how can we unify, the earlier evidence of magnetar or early time evidence of magnetars, so like millisecond magnetars, with the later stages of magnetars that we observe these periodic emission from. That was kind of touched on in one of the later talks, that it's very difficult to get a scenario where you can have a millisecond magnetar say emit an FRB or be responsible for FRBs. So how do we start to unify like millisecond magnetars with the later time scale magnetars? Yeah, any thoughts on any of these? Right here. Sorry. And please introduce yourself.
Hey, this is Pavan again from Swinburne. So I just wanted to probably kick off by alluding to the fact that there is still a lot of observational bias when we try to look at magnetars, because in terms of catching a burst, which is FRB-like, all-sky monitor kind of a thing, which always stares at those magnetars as something essential in order to sort of bridge that gap. And I think smaller dishes, some work by Hyperflash, which if you have smaller dishes, then picking a magnetar and then making sure that we accumulate enough observing time in order to see if there is any sudden burst, that is probably the way to go in terms of like bridging that gap. Just this is purely from observational perspective, but of course there might be different thoughts on that.
Yeah, it's a great point. And somebody had recently messaged us in the Slack channel that, it's really important to get time on radio quiet magnetars as well, in order to get time on radio quiet magnetars. We're definitely biased towards the more radio loud ones where we see an outburst and, we'll detect that and start to follow it up with X-rays. But what about the ones that we're not always getting a huge outburst from, or do they have lower luminosity emission?
Hi, so Molson Simons again. And so I guess like just seeing the statement before about there being kind of only 30-ish magnetars in the galaxy, I guess like we then have to reconcile with the idea that we're never going to have enough time to like probe into the part of the energy distribution that would emit FRBs at a substantial rate, in that if we're only seeing FRBs at, you know, so many hundreds per sky per day over this number of galaxies that we really probe out to, that trials factor from the number of galaxies you get is like adding to your exposure in a way where the same amount of time then divided up amongst like 30 magnetars in the galaxy is going to be so long that like you'll never probe that like regime statistically. And so I guess we need a different way to think about whether or not these magnetars could be generating those high energy pulses on a longer timescale.
Yeah, that's a great point as well. And it might come down to, you know, boosting our population, or whether that's boosting our galactic population, but boosting nearby nearby observations in nearby galaxies. That is, anybody have a follow-up on that?
Andrea Possenti from INAF. I just got anticipated by what said. No. It's reinforcing what I was about to say about the fact that indeed, if you look at the phenomenology of the single pulses in the radio magnetars, it's really striking the similarity with the very vast phenomenology of the repeaters, especially. And but there is this big issue of counting how many of them, which might be related to the different level of intensity of the emission. There might be a gradual distribution, or maybe not so gradual, between those which doesn't emit almost anything in terms of radio magnetar, and those which emits like radio magnetars when there are the X-ray outbursts, and those which are maybe in specific stage of magnetar life that every now and then emit very strong bursts and can be seen very far away.
Yeah, and I think you know, characterizing that distribution has been tricky also with our classification of magnetars, like, and how we actually distinguish between magnetars versus pulsars versus, like, you know, an X-ray transient that is unidentified. Like, how do we fill in the distribution when it's not always clear what falls into what category? That makes sense. Oh. Yeah, Casey.
Casey Law from Caltech. Yeah, this moving down the luminosity distribution point is really good, I think. And there is one other way to work around it, which is that, of course, all the radio emission is beamed. So if we can provide different perspectives on a source, then you would actually have independent samples of the beamed emission, right? So like, I think effectively what you want to do is like some sort of radio calorimetry of a source, right? Identify a source and then figure out how you would bound the radio energy output. But I don't know how that works, because you'd have to see it from different perspectives or have something else see it from different perspectives and then measure the energy output that way. But that would be a way to get down in the luminosity distribution, right? Yeah.
Yeah, so good.
Just one point related to this. If you go back to the previous graph, I'm not sure if everyone completely appreciates this, but, you know, Chime and Stare saw this very bright burst from SGR 1935 that was maybe like 30 times less luminous than, you know, your typical extragalactic FRB. FAST saw some radio pulses at the period of the magnetar that are kind of around where the red dots are for rats. But Vesterbork also saw two bursts that are kind of in between the two. And that one single source emitted radio bursts over a factor of 100 million in luminosity. So, you know, you could imagine maybe that means that neutron stars can emit over trillions of factors in luminosity. Yeah.
I think Yuri and then.
Thank you. So if you want to play around with this, then I say download FRB Poppy, You can build your own FRB population. You can put in the luminosity distribution, and you can see that that you can connect it to the magnetar density that we have. So I think it's doable.
A couple comments. One is, well, I think the difference in luminosity of the bright FRB or the bright FRB-like event from 1935 is, I mean, I thought I heard factor of 30, but I think it's more like a factor of 10 to the 6 to 10 to the 9.
Factor of 30 to like the weakest extragalactic.
Oh, to the weakest. Okay, yeah, yeah. Then on your next slide, you're asking, is there biases in the galactic magnetar population? And most of them were found by bright X-ray bursts. So and those identifications are really unbiased because they're found by gamma ray burst monitors that were designed to see everywhere, and they always tend to find them right in the SGR or magnetar types right in the plane. But they're biased against those that produce X-ray bursts. That was one point. And then I had a question for the, I think, was it Marcus, who presented on 1E 1547? Yeah. Oh, you're right. Isn't that funny? So my question was, you said, oh, it shows all this phenomenology, everything, and you said drifting, and you said it very quickly. But does it actually show the sad trombone kind of stuff that we see from repeaters? Because you didn't show an example of that.
Okay, this is Marcus from Swinburne. So the drifting that I think I mentioned was more due to subpulse drifting from one rotation to the next. And then the one plot I had, which had what might look like some sort of sad trombone effect, we can't tell if those individual components are from one rotation or several rotations averaged together because it was fold mode data.
The answer is no.
No.
Okay, you have a million bursts from it, and you've never seen downward drifting sad trombone things, right? Just
Yes.
right, I understand.
Yeah.
But nobody's seen that from a magnetar, is all I'm saying.
Yeah, no, that is a really interesting point because, I mean, what distinguishes the phenomenology, the phenomenology that we see in radio magnetars versus FRBs? I mean, right off the bat, like radio magnetars are periodic. So like that's already one thing that we can, in general, are periodic. So like what else, distinguishes them? We have one here, we can maybe pass it. So we'll take,
I'm gonna do it to Brian.
We'll do maybe 2 more comments and then move on to the next topic.
Brian Gainsler, University of California, Santa Cruz. So we've had 3 magnetar giant flares since 1979, one in 79, one in the 90s, and one in 2004, that were all much, much brighter in energies than 1935. Is it right that we really don't know what those were doing in the radio at those times? And that, could there have been even a burst storm lasting, a week and we wouldn't have known?
Yeah, so
do you want to respond to that, Vicky?
We'll do this last response. And then
Yeah,
move on
at
to
the
next.
time of the 1806 -20 giant flare, the Parkes telescope was observing, not pointed at it, but the source was in the side lobe. And there's a paper, Tendulkar et al., Sri Harsh led it with Chitrang and myself, and got those data. And if there had been an FRB type event, depending on exactly what you know about the side lobes of Parkes, but he did some really great calculations, you would have seen it.
So we're going to go ahead and, for sake of time, move on to the next topic. But yeah, thank you. This is some great discussion.
Great. Okay, so our next topic was supernova remnants, pulsar wind nebulae, and persistent radio sources in the case of FRBs. So I guess maybe one of the first things to say, maybe I'll even jump to the second point first. I mean, it would not be very fun being a radio astronomer if you were in a galaxy with a PRS, because these are many, many orders of magnitude brighter than the crab. And if you work with a telescope like LOFAR, for instance, like you see the crab in the side lobes of the antennas. So imagine having something that's 100,000 times brighter than the crab. It gets pretty spicy. It'd be like trying to be an optical astronomer observing during the day. It wouldn't not be very, very, very rewarding. Sorry? And it's variable as well. Yeah. Well, I'm talking about the persistent radio source. Well, there's due to refraction. Yeah. not on like super short timescales, but yeah. So so these are pretty spectacular things, and I think that's probably an argument that, well, we certainly don't have a PRS FRB in the Milky Way. I think we would definitely know that if there was something of that luminosity in our, you know, regardless of beaming, right? We would just know that there was something like this in the Milky Way. So we have lots of galactic supernovae and pulsar wind nebulae. Hopefully Brian will chime in at some point. These are different things, but they're related things. You know, one is created by the pulsar wind, the other is from the initial explosion. It seems like magnetars are less associated with nebulae, and yeah, well, at least with nebulae, perhaps not with supernova remnants. Sorry? One X-ray nebula was the comment, yeah. Okay, and we'll come to you in a second, Shami. So we don't have particularly extreme pulsar wind nebulae in our own galaxy. Like, you know, the Crab is kind of the most extreme example, I think, and there are a few others that are kind of comparable. But there has been some very interesting work done recently, for instance, by Dylan Dong and Greg Hallinan, starting to find what look like plausible extragalactic pulsar wind nebula candidates. So that might be, you know, at least the nearby universe, if we move a little bit beyond galactic analogs to just, you know, tens of megaparsecs or so, there's maybe something to be learned there. So to start this discussion, I guess, Shami, if you have your hand up, do you want to go first?
Yeah, sure. Can you guys hear me okay?
We can hear you great.
So I was beginning to wonder, like, have we gone long enough that we should be able to see time evolution in the examples of the PRSs we have, and not seeing them fade, or what limits we have on them fading, and what that's starting to say about what the sources can be?
Yeah, well, Gavia, would you like to comment on that?
Hi, this is Kavya Shaji from University of Sydney. So yeah, the long-term data we have on a PRS is of R1. So we have like, now it's been like 10 years of, nearly 10 years of observation data we have on PRS flex density. But we can see like a flex density variation in short time scales. But in long terms, like we are not seeing any evidence of long-term variation in the flux density. So yeah, it's kind of stable, and the short-term variation we are seeing is consistent with predictions from refractive scintillation. So yeah, the flux density is stable for PRS of R1.
Oh, okay. Other comments? Yeah, Matthias?
Hi, this is Matthias from University of Toronto. I guess one interesting aspect is that we're still at the era of like the Crab you use as an example is kind of our staple example of bright PRS in our own galaxy, except that there's there's this lack of very young pulsar winds that, and you mentioned Dylan Dong's paper as a candidate that's probably a couple decades. But we're reaching a point now that we've had kind of these all sky optical surveys that have been looking at least have been establishing a sample of core collapse supernovae in the local universe that are now exhibiting kind of this radio rebrightening at late times, like 5 to 10 years post-explosion, which is kind of in line with the timescales that you'd expect your ejecta to become optically thin and you get a pulsar wind that is emerging. So I think that we're early on, there were searches, especially towards the superluminous supernovae, but I think a promising avenue could be going towards these, like doing targeted searches at these late time radio rebrightenings, because at this point, if they're optically thin, then you can kind of test this young pulsar or young magnetar model more.
Yeah. Great, thanks, Matthias. Any reactions to that or other directions? Yeah, Lauren, please. Yeah.
Yeah, I want to like second what Matthias says.
Oh, I'm Lauren. Yeah. I never have to introduce myself when I hold this. Yeah, I'm Lauren Rhodes. I'm at McGill. Yeah, I just want to second what Matthias says, but also that unfortunately we won't be able to use this surveys like the VLA Sky survey to do these sorts of tests because these things are just too faint. Like if you look at the PRS associated with R1, Alex's new one as well, they do really need their own dedicated campaigns. So please write to your lovely tax and ask for time.
I would imagine that maybe DSA 2000, well, DSA 2000 will get deep enough to pick this out, right?
But if we want to monitor these things or find them in the first place, maybe we need to look a little sooner. But yeah, like the current surveys won't be able to find them, I think, in most cases. Yeah.
Okay. Yeah, watch your language. Okay, we'll go to Naveen first. Actually, I'm interested also to know, Naveen, if you think that the stability of the PRS is difficult in terms of your model of a hyper-Eddington accreting source.
It's not really. The prediction from 4 or 5 years ago was that the luminosity would barely increase, an extremely small increase over the next few years, and that's very much dependent on the choice of parameters.
It depends on kind of the evolution timescale of the binary, right? Because it's dependent on the mass transfer.
Exactly. So you cannot predict what it's going to be like 10 years from now, assuming an initial state which is going to change every year. So it has to be iteratively done. So it's a small change in the parameters could easily satisfy the observations.
Are you frustrated that I only put up a picture of a pulsar wind nebulae? Should I have put up a picture of SS433 as well? Or?
I would have loved to see an SS433 because we have seen many such persistent radio sources surrounding accreting engines. So there's something that we could learn about PRS from accreting engines, hyper-Eddington accreting engines. Many extragalactic ULXs, for example, that beautifully show these PRSs around them.
Yeah, an FRB from a ULX would be that would be a smoking gun. I guess.
Yeah.
Okay, then we'll go to Matthias, and then we'll go to Zorwar.
This is Matthias, sorry. This is just kind of going back to what Lauren was saying before. While I do agree that there's a lot of these events and not necessarily, you would have to do dedicated follow-up. You can kind of be strategic in terms of what targets you want to go after. Like you wouldn't necessarily go after a type 2 core collapse that's happened in the last 10 years because you would expect the ejecta to still be relatively optically thick. But you would then maybe say, I'm going to go for type 1Bs or type 1Cs or the broadline events that are going to be more rapidly expanding, and that sample is significantly smaller. It's still a substantial amount, and the VLAS, the rebrightening that you would expect also does hit can hit above multiple millijanskys, which is detectable in VLAS. And there's, I think, a paper from 2021, Stro, I can't remember the first name, but they detected late time using VLAS and kind of argued in favor of various models. Yeah.
Thanks.
Yeah, this is Arwadi Singh, University of Maryland, Nasa Goddard. I was just going to say, I don't know if the ULX would be a smoking gun, right? Because there's pulsating ULXs and they're most likely magnetars in a ULX. Pulsating ULXs, yeah. Yeah, but they could have a burst, right? A magnetar burst.
Oh yeah, you should use the microphone.
Yeah, so if you have these pulsating ULXs powered by magnetars, they're still accretion powered. And if you posit that the radio burst would be arising from the heart of these systems, they would just absolutely not escape the accretion disk bends. So you will not see them at all. So if you see a radio burst from an ULX, it's coming from far away distances.
Okay, great. Theory consensus instead of theory battle. Okay.
But yes, ULX.
Okay, we have time for a few more remarks on this. Any other directions?
Yeah, it's Molson again. So I have like basically complete naivete about PRSs and the continuous aspect of FRBs. But in the cases where if we were fortunate enough to have observations of a PRS that were at the same time as some kind of burst storm, do we expect there to be changes in the brightness of the associated PRS, not because of the emission from this burst storm being like included in that observation, but because physically something is happening at the source? Okay. Okay.
Yeah, so the question from Mawson was whether you would expect the luminosity or the observables from PRS to change if there was an burst storm happening in the engine, not due to observational effects, but physically. It depends on the model. If you were to invoke a magnetar wind nebula model where the PRS is inflated due to the flares from the magnetar, then yes, you would expect such a change. But in a hypernebula scenario where the flares launched from the pointing dominated jet, say, are producing the FRBs, then the PRS overall properties would barely be affected. But overall, the luminosity of the PRS would scale with sort of the luminosity distribution of the intrinsic bursts that are launched from the system.
Okay, then we'll go to Kavya, and then we'll see if there's any final remarks on this. Yeah, go ahead.
I think I just agree with Naveen. And also, I was also like thinking, why didn't we mention about the AGN scenario? Because the flat spectrum and also the long-term stability is also consistent. I mean, like the AGN, radio loud AGN can also explain such properties as I read from literature. So maybe.
You have to wait for the microphone.
I think accretion powered, I mean like AGN, which is having accretion, it can also like, if the PRS is something coming from that, then the observed stability over this like decade and also this flat spectrum observed in L band could be explained by such a system.
Yeah, it hasn't been mentioned a lot at the conference, but there are dwarf galaxies with persistent radio sources in them that are thought to be massive black holes. I think, Tarne, you've worked on this with Amy Rines quite a bit. It's not obvious that whether that's like a different population of persistent radio sources and dwarf galaxies, or whether those are just the ones where we don't see the FRBs, but it's all the same thing. Yeah. For people online, Tarne is just politely nodding. So, okay. Vicky, you had a comment?
Yeah, just a comment. So well, I guess we haven't heard that much, unless I missed it, about the synchrotron maser model so far. And that was, part of that model was to explain PRSs in 121102. And so we heard, I guess, a talk today about how, the magnetar wind nebula would be inside a supernova. And I guess I'm sort of associating the magnetar wind nebula with, that there would be a shock there that could be where the synchrotron maser would operate if that model were applicable. And but that, that whole thing evolves with time. And so I guess what I'm thinking is you might expect different types of bursts from, that would somehow be correlated with the properties of the pulsar, of the PRS, if those indeed are one and the same type of object. So if you see a really bright one, wow, that should affect the synchrotron maser model if it's, more compact or younger or something like that.
Yeah. Okay, we'll take one final comment by Naveen, and then we'll move on to the last topic. Yeah.
The shock that you mentioned, so Naveen from Stanford. So there are several shocks happening here. So there are multiple locations where shocks are happening. The shock that heats up the particles eventually that produce the pulsar wind, or the PRS, is expected to happen at 10 to the 17 centimeters, whereas the kinds of shocks that synchrotron maser models invoke to produce the FRBs happening at 10 to the 12 to the 13 centimeters, well inside the PRs. So they don't have a direct interaction in some sense. So the evolution of the shock that produces the PRS does not directly alter the bursts coming from deep within the PRS. No, they are not caused. They're not connected. As in, the engine is the same. The engine that's powering the FRB and the PRS would be the same. For example, at later times, the engine could get older and you would produce lesser and lesser bursts, and it would not pump enough material to power the nebula. But the location where the FRB is produced and the location where the particles are energized to produce the PRS emission are widely separated by over 5 orders of magnitude.
Okay, thanks, Naveen. Miles is going to take us through the last topic. And I see there's a lot of messages online, but is that just chat or?
No.
Okay. Yeah, no, take it away. I'll take the close to the laptop as well.
All right. So we'll go into the last topic of this discussion, which is on long period transients or long period radiated transients or whatever name you like the most. So we heard quite a bit about LPTs this morning. And so there are, I think I need to update this number, but there are somewhere around 11 or 12 long period transients with pulse periods that are above about 10 to 100 seconds that have been identified. Some of these are, tentatively associated with white dwarf, M dwarf binaries, but most of these are unidentified so far and don't have evidence of optical counterparts or high energy counterparts. I believe there's one that's associated with the high energy counterpart. But there's a lot of questions we can ask about, what these, first of all, just phenomenologically, I can never say that word. What lessons can we learn about FRBs that we can, learn about long period transients that we can relate to FRBs in terms of their subpopulation. So we know, just by the fact that we don't see M dwarfs associated with many of these long period transients, that they're not, at least they're likely not white dwarf, M dwarf binaries. So what, they must be another channel, whether it's a different progenitor, a different source mechanism, a different emission type. And so what can we, learn about distinguishing different types of LPTs and apply it to FRBs? How can we explore the link between LPTs and FRBs, and how might their progenitors be related? So I've shown a couple there, and just to give put a fine point on this, so we know that they have much longer pulse periods and fall into this region that we refer to as the death line, or further to the right, compared to magnetars and other pulsars. So it's clearly, a unique type of source, but how are they related to, say, typical pulsars, other neutron stars? If they are neutron stars, are they white dwarfs? So a lot that we don't understand about this population. But we know that they can be related to FRBs based on things like their coherent emission, the fact they have to come from a compact source. And there's some cases that we heard about where they show downward drifting structure or substructure that's very similar to FRBs, although on longer timescales. And then finally, how can we increase our sensitivity to extragalactic LPTs? That might be one way that we can learn more about the link between long period transients and FRBs. So does anyone want to start off the discussion?
Hello, Adam Dong from NRAO. I think the things we've seen are very tantalizing, and I'm going to shoot myself in the foot a little bit here, but I think the luminosities are just so different from FRBs. Like you're talking about, I don't even know, like more than 1 trillion from factors of luminosity difference. So and how are we gonna it seems difficult to bridge that, is all I'm trying to say. And to a point of like extragalactic LPTs, pulsars are brighter than LPTs in terms of absolute flux. And apart from some rumors, we haven't even detected it, true extragalactic pulsar yet. So that's my 2 cents.
Yeah, it's a great point covering that, like that really large luminosity range. And I don't have, let me see, I don't think I have the plot with, oh yeah, this one does have a couple of LPTs on it actually, so you can see where they fall on the luminosity scale again. And so covering that wide order of magnitude is difficult, but they do have some of these implied magnetic fields that are pretty high that could suggest that they have a large magnetic energy reservoir. So that's one way that you could, source that energy. But does anyone else have any? So if you have a couple of comments, maybe we can go to Mawson.
Yeah, it's Molson here once more. So I guess like a case study counterpoint to that is things like thermonuclear explosions, right? Where like in our galaxy, we see classical novae that are like probably dim enough to not really be observed over a cosmological volume. And then conversely, by like basically the same emission mechanism of blowing things up, we're seeing them over wide redshift ranges, even further away than FRBs. And so I think it's like, especially on a plot like this, where you're plotting all your data points, but what's important is the rate at which they're observed, which is completely obscured from this. I think it's easy to trick ourselves that that's a really vast gap that like maybe we can cover. And like your point's totally well taken in that, you haven't seen extragalactic pulsars. And so clearly there's some luminosity function that doesn't go all the way up to there. But like, I don't know, does that tell the whole story? It's hard to know.
I mean, there's such a wide range. It is definitely hard to tell. We'll go over this way next.
I'm going to disagree with Adam. And yes, before I disagree, I should introduce myself. I'm Calvin from UC Berkeley. I'm going to disagree with the point that a large luminosity gap is hard to explain on the basis that this is radio luminosity. But an easier way to get a million times the luminosity as a radio photon is to have one optical photon. So I want to emphasize that I think the multi-wavelength counterparts are going to be really important in figuring this out. And that if you made the same plot with total rather than radial luminosity, things might look very different.
We'll go over to Naveen.
Yeah, I have to introduce myself before I disagree with Calvin. Naveen from Stanford. So even though it's a million orders of magnitude or trillion more than the typical pulsars, you said it's just simple radio, but the more relevant parameter here would be the wave strength parameter, the amplitude of the waves as a ratio of the moment of the particle's mass, basically. That exceeds unity for FRBs, and that gives rise to completely new plasma instabilities and phenomena that you would never see in subunity or less than one wave strength parameter regimes like pulsars and so on. So this is entering a completely new physical regime. So you would need new ways for it to be emitted, for it to be transported outside certain regions and so on. So it's completely new physics, I think.
We have a hand online. Alex, you can go ahead and unmute.
Yeah, hi, Alex Cooper from University of Oxford. Just on the luminosity gap, I think in terms of the kinds of energies you need to perturbate a magnetosphere or the crust of a neutron star by, these are very gentle changes that you need to get to the kinds of radioluminosities that we see for LPTs. And so, increasing this to much more radical changes to either the crust or the inner magnetosphere of a neutron star, you can get to those FRB luminosities relatively easily if you're assuming that these are relatively violent events compared to the LPTs that we're observing in the galaxy.
So if I could poke the bear a little bit, if it is these gentle changes that we're looking at that can get us to higher luminosities, what could explain, why we're not seeing brighter, say, long period transients in our galaxy, or brighter magnetars, for example.
So I'm not sure I heard during the conference anyone like really explaining what the emission mechanism is for instance, the LPTs that have been shown to be in these magnetically locked binaries. It seems to me, especially since the pulses are seen at conjunction, that it has to do something with this magnetic bridge between the two stars, right? And to me, at least, that is kind of like a proof of existence that maybe you can get coherent emission from this kind of like almost like a linear accelerator between the two stars. And if so, you know, why not like a magnetic bridge between two white dwarfs that are in like a 5-minute orbit, or like two neutron stars, or a neutron star and a more massive companion? Like there might be some analogies to that would just be enormously more luminous than what we've seen in our own galaxy. And now the theorists can tear me to shreds. Okay, which one first? Okay.
And on that, and just on that note, as well, in I believe it was Iris Deruta's talk earlier today, where you can have emission at different phases of evolution as well, and that might give you a different luminosity or different behavior. Yeah.
So on the binary scenario, I would like to comment that our work, Alex's work and Zorawar's work, has shown that you need very small binary separations. Oh, by the way, I'm Om Gupta from UT Austin. You need very small binary separations to actually achieve the potential for accelerating particles to such high energies that we see the fluxes at large extragalactic distances. You need very small separations, especially for neutron stars. So for white dwarfs, that situation is further exacerbated.
Someone have a comment on that? Oh.
Just to continue Jason's line of thinking, maybe the theorists can tear me to shreds later.
Introduce yourself, please.
Barak Zakai. So maybe if you go into locked systems of compact objects, you are also tapping a new source of information, which is the orbital energy. And that could give you a source of information that is much larger than what you have from the rotation of the neutron star.
Over to you.
Thanks. You're even labeled from Astron, so if you will allow me to be provocative, I think much of the excitement is because we are discovering LPTs and FRBs roughly at the same time. If someone would discover the pulsar 0950 plus 08 next week, we would all be standing up, shouting and screaming in amazement because it has huge pulse-to-pulse variability. It has downward drifting, it has upward drifting, but it's been in that pile for so long that we kind of forgot. So let's be also realistic. How much of this is just the timeliness of it, and how much do they really tell us about FRBs?
Yeah, that's a great point. I mean, we'll go back to Wayang, and while you're doing that, the recency bias, I think, in astronomy is very strong, let's say. Yeah, okay, so we'll do 2 more comments.
Okay, just short comments. Wei Yang from University of CS. So I just gave a short comments of the periodicity search. So we haven't detected any confirmed periodicity. Even we have a large burst sample. So for instance, we have detected more than 10,000 burst samples from the FRB2024 0114. So, but we haven't detected any confirmed periodicities. So I guess here actually we have tried so many methods to find the periodicity, but but there is no confirmed signals here. So from the physical side, I guess there is actually no periodicity can be seen. Even the FRB source is a rotating pulsar or magnetar. So because the emission maybe came from random regions from the star's surface. So rather than the pulsars, they are confined into the polar cap regions. So that's short comments here.
Yeah, and I think we're just about out of time, so maybe we'll continue discussion over the coffee break. But just a hand for everybody who, for all of our great discussion here. And I look forward to continuing over the coffee break.
Yeah. So
that's my fault.
So it is not a coffee break.
No, that's my fault.
Not a coffee break. So there's gonna be a late breaking talk by
I'm not in charge of schedule.
yeah. So next up, there's going to be a late breaking talk by Marcin Głowacki, and then there's going to be a short announcement about FRB 2026. So
Hello.
Hi.
I will need permission to share.
Yes, I'll give you permission to. It should be good, so share whenever you want. All right, everybody. All right, whenever
Is that
you want.
coming through?
Yeah, we can see you.
Excellent. I'm just going to move this around. Okay, sorry to interrupt everyone's anticipated coffee break, but we have some breaking news, a discovery made within the past month. I'm Marcin Głowacki. I'm giving this talk from the UK on behalf of the Craft Survey Science team. There's a lot of people listed at the bottom who have been involved with this discovery and follow-up. I'd like to stress this was a team effort. A lot of other people here could easily give this presentation. However, a lot of the team are in Australia, which is a pretty unfortunate time zone for this conference, so it falls upon me. I also just like to pay acknowledgement to the native title holders and traditional owners of the land on which ASCAP works from, Ilyaramana Ilgara Bundura. And this is some artwork which depicts the craft survey as distant objects that burst and flicker. So that's a nice description of FRBs, if you like. So the FRB in question is 250613. You heard on Monday from UM Mink about the craft survey as well as the craft coherent or crackle system. But while that was in operation, we actually made this detection for the old system, the incoherent sum system, or ICS for short. And this was sufficient to get a detection. This was found during the EMU survey. So as a reminder, craft is a commensal survey, whatever ASCAP happens to be observing, be it spectral line, polarization, or radio continuum. This was the latter. We just piggyback and stare for FRBs. This was during our observation less than 20 minutes long. We had the trigger just late on the 6th, also late on the 13th of June by UTC time. And this was during ASCAP low observation, so centered at 920 megahertz and almost 300 megahertz bandwidth. The reported DM was just shy of 175 DM units, and the signal to noise was not super high, but 12, it was a firm detection. Another thing I should note, one of our PIs, Ryan Shannon, was overseas. We've actually noticed a trend where he or Keith Bannister or both will be away mysteriously, and then we'll suddenly detect a fast radio burst. So this is something that needs further investigation. But on a more serious note, since we're using the ICS system, we didn't have the initial position. We could identify which beam from the 36 beams of ASCAP that it was brightest in, and so we have a beam center position, but this meant that we had to do some offline processing to determine the localization, because at the time it was a one-off burst for us. So we used Celebi, which is a pipeline that we use to process on voltages. ASCAP is constantly recording now 12 seconds worth of voltages, and when we have a trigger for an FRB, we dump those voltages, move them to a supercomputer in Melbourne, and then we can process those voltages to get the localization, as well as get high time resolution data set. Celebi is also a Pokemon, but it's also called the Craft Effortless Localization and Enhanced Burst Inspection System. This was initially started by Danica Scott, a PhD student I've co-supervised. A list of several names here of people who have been involved in the continued development of Celebi. And I've bolded the names of Tyson, Apurba, and Adam because they use Celebi in this particular case to process the voltage data. So after we did some match filtering to determine in what time and frequencies the FRB was most visible in, we get this image of the FRB itself. And from there, we can determine its position, which is given on the bottom left. And the error means that we have a sub-arc second precision on this localization. And happily, this aligns very nicely with this optical image. So the background image is the legacy or Decals DR10 R band. and the ellipse is the FRB localization ellipse. This source is a 22 mag host galaxy. So if we stick it through path, which is what Alexa Gordon did, we have a probability greater than 90% that this is where the FRB came from. This source does not have a spectroscopic redshift. It has a photometric redshift of about 0.2. So if you assume that redshift is the real redshift, then this would apply when you combine with the magnitude a low mass galaxy. But we are currently looking into optical follow-up and analysis is in progress, so we can determine a firm redshift measurement for this FRB and hence its host. And as I mentioned earlier, Celebi also produces a high time resolution dataset. It can actually go down to 3 nanoseconds in resolution, which is very rarely needed, but quite useful if you happen to detect a dead satellite that goes off after 50 years in operation. But in this case here, we saw 2 pulses as part of this one-off burst, and it had the stereotypical sad trombone structure here, which made us quite excited. And then from the Celebi data products, we then also discovered that the rotation measure was a whopping more than 7,000 radians per meter squared. You can also notice, this is directly from the second component, around where the cursor is, there is an RM forest also appearing at around that peak. Dyson Dyer has also done some further investigation after doing some Faraday derotation. This is what the 2 pulses look like at this time resolution. The top panel is PA, middle panel is Stokes I, L, and V, and then you have the Stokes I dynamic spectrum at the bottom. And you can see from the first component, it lacks polarization. There's not even a strong linear polarization, which is unlike the second component, where it's much stronger there. We also did some quick checks. We were able to fit some scattering to the second component. We're still working with the first one, which is a little bit more complicated. We get about 57 microseconds of scattering timescale. And when we look at the power law index, it comes to -4. So roughly what you would expect a well-behaved FRB to be like. And we also looked at scintillation from both components. We get a modulation index of roughly 0.7. So these were the numbers that we had from our initial burst. We had strong evidence that this was quite some exciting thing to follow up. Firstly, we looked at the existing observations from the EMU survey with ASCAP. We didn't see any radio continuum, but ASCAP is a fantastic survey instrument, but not the deepest one, so this didn't rule anything out by any means. We were keen to get more time, but firstly, as a reminder, CRAFT is commensal with ASCAP survey. So whatever ASCAP is doing, unless we happen to have our own time and can request it, we're stuck with what it's doing, and they decided it's time for some maintenance. So we couldn't use ASCAP anymore, and in fact, it was a bad time to be a radio astronomer in Australia because even the likes of Parkes was also having maintenance for several weeks. Luckily, we're able to make a request to the Meerkat operators for some follow-up, and they allocated us some time for a DDT. So we were given 2 sets of observations. One of them was a 2-hour observation, and another one was a 6-hour block, which was split into 2 times 3 hours by the Swayo system. These were both daytime observations, and we did notice some RFI between the 2. Data analysis is currently ongoing for what we have transferred over. And while we didn't see anything in the first observation, and RFI didn't help, in the second observation, we saw this repeat here. This was the first one that confirmed that this FRB is a repeater, thanks to Misha Caleb, as well as Ben Stappers and the Meertrap team in general for this. You can see the parts that have been blanked out due to RFI, but we see a clear, 22 signal-to-noise detection of a single pulse. And that wasn't the only one. In fact, we found 16 bursts within that second observation. This is a particularly bright case, more than 100 signal-to-noise. And again, 2 pulses showing up here with the stereotypical sad trombone feature. Now, since Meerkat is deeper, we are firstly able to eye the surreal data-reduced images for each individual track. And even there, we were seeing hints of radio continuum. So myself and Andy Wang have combined the data sets and then reprocessed them. He used Oxcat, and I did a sanity check with the process Meerkat pipeline where we got similar results. So this is the image that Andy produced, which gives you a peak flux of 24.2 microjanskis. Now, this isn't necessarily PRS. It could be, but since we only have so good angular resolution of our observation, this could also be attributed to star formation within the host galaxy. So we will need higher resolution follow-up, but this is encouraging that there is a chance there is actually some PRS associated with the host galaxy of this FRB. In the meantime, while we're investigating optical follow-up, question was, can we also use that meerkat data to look for H1? This was a 4K resolution spectral line, so not particularly high resolution, but it will be sufficient. And this is something we have done before for an ASCAP FRB. Shameless plug here, where we had a FRB that was detected behind the galactic plane, so it was a bit harder to get immediate optical follow-up. But we were able to detect the H1 emission line, which then gives you a redshift, and that was later confirmed by the optical to be the redshift of the host galaxy.
Okay,
Two
minutes left.
Perfect. Unfortunately, there was no emission to be seen. I certainly wouldn't bet on any of these peaks to be corresponding to the host galaxy. This was a daytime observation, which is not ideal for spectral line astronomy, but I can say there's several actually H1-rich galaxies within the field that have popped up quite obviously from looking at the dataset, but nothing toward the host. So here is a plot showing on the y-axis log MH1 mass, and on the x-axis the redshift. So you can get a limit on how much gas would be in a galaxy depending on where redshift is, up to 0.09. Unfortunately, there's a lot of RFI, as you've seen on the earlier plot, just south of 1300 megahertz, which really hampers your ability to find anything of H1 higher than that. So while there could actually be a decent amount of gas in this galaxy, it might be just too high redshift for this H1 approach to work. So we're really going to have to wait for the optical, find out further. I also highlight that a few days ago, there was a separate ATEL following ours, where a team using GMRT have also seen repeats from this FRB, and they've found repeats all the way down to 300 megahertz. So we encourage further follow-up where possible of this FRB, and we're also exploring options as well. So I'll leave you with the summary slide. We've successfully detected a repeating FRB. It has one of the largest rotation measure magnitudes so far, and there is some tantalizing radio continuum emission aligned to the position and seemingly a small host galaxy, but we do need that redshift to confirm. Thanks again to Meerkat and also later GMRT follow-up to confirm this is a repeating FRB. Thank you very much.
All right, thanks a lot. Are there any questions? We have time for maybe one or two. Any questions online? Well, then I guess, I'll pass to Ziggy.
Hi, this is Siggy Pleunis at the University of Amsterdam. It seems like the Southern Hemisphere hasn't really been probed very well for repeating sources, so there might just be very hyperactive sources waiting out there to be discovered. Do you have any clues on how we could find them?
Short of more observations, not really. Maybe you could try targeting nearby clusters or the like. That maybe will be something that would lead to a repeater, more dense environments. But otherwise than that, we just need more observations.
Hi, Martin. This is Calvin from UC Berkeley. Great talk. I noticed that unlike the other FRB systems in dwarf galaxies, this one has a relatively low total DM. So I'm wondering if you can break down the DM budget a bit more for us. What's the ISM and Halo contributions in that direction?
I think the Milky Way contribution is, from memory, roughly 40 DM units. And so it could be, if you assume that given the high RM, that it might be a significant host DM contribution as well, which would place it roughly, from the rough approximation less than redshift of 0.1. But yeah, we need to investigate this further. And analysis of all the repeat bursts, which maybe will help us give us some more clues on that, is underway.
Great,
as
thank
well
you.
as optical follow-up.
Of course.
Oh, is that a direct?
Hi, I'm Kavya Shaji from University of Sydney. So I was just curious, since the bursts detected were like bright, were they were removed from the visibilities while doing the imaging?
I don't think we did any removal from the voltage data. We just localized what time they were happening and then imaged it directly from the voltage downloads. I'm not familiar with the data sets from Meerkat, how that has been processed.
Okay, sure. Thank you.
This wouldn't have been bright enough to see with a raw Meerkat image that we were looking at ourselves, at least to my knowledge.
All right, I think that's it for time. Let's thank the speaker again. Yeah, and before the end of the day, where we're going to, those of you who want, going to do the lab tour of Matt Dobbs's lab, we're going to have one special announcement about next year's FRB 2026. It was Google Slides, yeah.
Yeah. The FRB2026, then yeah, in China.
I did. I'm blind right now. Yeah.
Yeah.
Yes.
This one. Yeah.
Yes. Oh, and I'll share it for the people online.
Okay, so I'm Wei Wang from University of CES. On behalf of the whole SOC and LOC, I'm honored to be here to announce that the FRB 2026 will be held in Guiyang in China. So actually in China we have so many selections like Beijing and Shanghai, and they are big cities, big and modern cities. So, but we finally decided to hold the meeting conference in Guiyang because we think that the Beijing and Shanghai, even they are famous cities, but they are so boring because they're just big, large cities with modern buildings. So we select Guiyang because Guiyang are surrounded by by green mountains and rivers and limestones. So the Guiyang is a typical coastal landscapes, which was caused by some dissolution of the soluble rocks. So you may find that there are so many beautiful places like like the lakes are with green and blue colors, and also so many beautiful caves. And there are also some ancient Chinese buildings in Guiyang. So it's a very beautiful city. I think people don't worry about the security because China is very safe. And also don't worry about the visa because the China allows the people, the ordinary passports to retire for visa-free tourism within 10 days for some countries. So and very major highlights to announce in the conference is we have a chance to visit the FAST telescope site. So as you know that the FAST is the largest single dish telescope in the world. Due to the great sensitivity, the FAST is it's a very powerful instrument to monitoring FRBs. So we will have a chance to visit the real platform of the FAST site. So whenever you are tall member or short member, you will be roughly this size here. Yeah. So under the you will go to the platform here, and the FAST site is under your feet, and then you can see the whole site. That is so impressive. So bienvenue en Guiyang, bienvenue en Chine. Welcome to China, welcome to Guiyang. So thanks. We really hope you're coming.
Thanks. So yeah, I think that wraps it up for the talks for today. For the guided tours, Matt, are you going to be taking people over to Rutherford or? we'll divide it into 3 groups. Yeah, and then the conference dinner is at 6:30 at the Thompson House. So thanks everyone. Wait, is that right? Thompson, okay.